Okay, it is a great honor and pleasure to deliver this opening lecture at our celebration of Pat's birthday. I begin on a personal note. Although I was acquainted with Pat's work in the philosophy of science, philosophy of physics, foundations of measurement, and foundations of probability, before coming to Stanford in 2002, the best of the many good experiences I have had since arriving here has been becoming better acquainted with Pat himself. Working with him in connection with the Suppes Center for the History and Philosophy of Science, and even more, getting to know him personally through many, many stimulating conversations, stimulating, I underline, concerning, among other things, the relationship between science and philosophy. This is the topic on which I shall speak today. I shall try to delineate Pat's unique perspective on this issue, and more generally to show that Pat's extraordinarily broad-ranging and diverse body of work amounts to a new and not yet sufficiently appreciated, at least among professional philosophers, contribution to the ongoing development of the tradition in scientific philosophy that began with the efforts of the Vienna Circle and related groups in Central Europe in the 20s and 30s, the 1920s and 30s, and continued in this country after the great intellectual migration that took place before, during, and after the Second World War. Here it was enriched by the tradition of American pragmatism, a healthy dose of which Pat absorbed as a graduate student in philosophy at Columbia after the war. He was there influenced especially by Ernest Nagel, who was one of the most important creators of the subdiscipline we now call philosophy of science during this period, along with Rudolf Carnap, Peter Hempel, and Hans Reichenbach. The first point to make about Pat, however, is that although he has in fact made central contributions to this subdiscipline, the philosophy of science, he is not a philosopher of science in the standard sense. The concept of scientific philosophy, which I've already used, fits better, insofar as it implied, in the late 19th and early 20th century context in which it was developed, a revolutionary effort to replace the entire academic discipline of philosophy, as it had come to be practiced, with a new orientation devoted to much closer cooperation with the sciences themselves. Yet even though it makes good sense to take Pat to be an inheritor of this tradition, the concept of scientific philosopher, as it was used by the Vienna Circle, may still seem too narrow in his case. For Pat, as we know, is equally or even more devoted to making original, ongoing contributions to science, and indeed to a number of scientific disciplines. Thus, Pat is one of only 3 contemporary philosophers who are members of both the American Academy of Arts and Sciences and the National Academy of Science, together with our own Brian Skyrms and Alan Gibbard at Michigan. And one of the things of which Pat is justly most proud is being awarded the National Medal of Science in 1990. That's the first thing on your handout, the statement there. I don't think I need to read it. Although this is an excellent summary of some of Pat's important contributions, this certainly does not sound like the profile of a typical philosopher of science, or even, if there is such a thing, a typical scientific philosopher. Pat is well aware of the unique nature of his enterprise. He puts it this way towards the end of the second part of his intellectual autobiography. The first and second parts are available online at his website. All the quotes you see, except the ones that are marked otherwise, come from that. He says he had worked both in philosophy and science. He continues to do and continued to have great interest in the philosophy of science. But it's certainly true that in many respects, most of my energy, he says, has been devoted to scientific activities. The 2 main areas are psychology above all and physics. He says, I could take another line and say that a distinction between philosophy of science and science is in itself incorrect. In many ways, I am sympathetic with such a summary of Quine's view, namely that philosophy should mainly be philosophy of science, and philosophy of science should mainly itself be science. I shall return to Pat's relation to Quine, and also to his relation to Carnap, Quine's teacher and later great adversary, below. My second point, however, concerns Pat's distinctive brand of philosophical empiricism, which, once again, is also quite unique. The next thing on your handout. Here, Pat says, charmingly, he sometimes liked to describe this influence in a self-praising way, that is, of his scientific work, by claiming that I am the only genuinely empirical, empiricist philosopher that he knows. It is surprising how little concern for scientific details is to be found in the great empirical tradition in philosophy. It has been a point with me to cite scientific data and not just scientific theories whenever it seems pertinent. Pat's philosophical empiricism thus involves a commitment to empirical science as a paradigm of knowledge and a consequent commitment to closely attending to the details of this science, both theoretical and empirical. And here, Pat's philosophical practice could not be more different from Quine's, who, although the most celebrated recent proponent of philosophical empiricism, Quine, appears paradoxically to be wholly uninterested in the details of any real empirical science, with the possible exception of a rather superficial fragment of behavioristic psychology. That could almost be a quote from Pat. However, and this is my third point, although Pat's philosophical practice is unusually attentive to empirical data, and his scientific practice is centrally concerned with developing detailed ways of testing theoretical hypotheses, a very large part of Pat's intellectual practice, both philosophical and scientific, revolves around formal mathematical work on axiomatic foundations. Much of his early work in the 1950s, for example, concerned the axiomatic foundations of mechanics, including axiomatic foundations for special relativity in the tradition we now identify as beginning with A.A. Robb. Pat then turned in the 60s to the foundations of probability in connection with the foundations of quantum mechanics, and embarked on a program for analyzing the phenomenon of non-commutativity, or incompatibility, between conjoint quantum magnitudes or observables, such as position and momentum, for example, or different directions of spin, in terms of the non-existence of joint distributions for the associated random variables. During this same period, moreover, he embarked on an ambitious and wide-ranging program in the foundations of measurement theory, which culminated in the now classic 3-volume treatise, Foundations of Measurement, appearing in 1971, 1989, and 1990, respectively. I think the 89 one was Pat's responsibility, which is why it was delayed so long. Written with David Krantz, Duncan Luce, and Ernst Fenstad. This work both created the formal axiomatic theory of measurement and developed it in extraordinary detail. This is Pat, believe it or not. The central concept of this theory is that of a representation theory, which formally explains the connection between the qualitative relations characterizing a given empirical domain, such as the relation of heavier than between different masses or weights, warmer than between differently heated objects, and so on. The relevant representation theorem says roughly that for any model satisfying the appropriate axioms for these relations, there is a function from the objects in the domain into the real numbers that is unique up to a certain class of transformations, characteristic of a ratio scale or an interval scale, and so on. Or, to put it another way, any model for these axioms is isomorphic to a purely numerical model, which is again unique up to the same class of transformations. The historical source for this type of axiomatic foundation is Hilbert's celebrated work on the foundations of geometry, first published in 1899, which aimed, among other things, thereby to explain the connection between synthetic and analytic geometry. Thus, any model for Hilbert's axioms of incidence, order, congruence, and so on, in general, a qualitative or synthetic model, no numbers in it, is isomorphic to a model in the domain of pairs of real numbers, a numerical or analytic model, where the appropriate class of transformations under which the relations in the model are invariant, in this Hilbert case, is given by the Euclidean group, rotations and translations, plus dilations, where the latter signify an arbitrary choice of unit of measurement. This extension and generalization of the Hilbertian style of formal axiomatics, that is, by Pat and his coworkers, to a formal theory of measurement for a great variety of possible physical magnitudes, including not only classical extensive magnitudes like length, but also what we now call intensive magnitudes, like phenomenological temperature. And even more notably, extending to the measurement of psychological magnitudes, such as subjective probabilities and utilities as well. This, I say, was a magnificent mathematical achievement, and I don't expect much argument, at least from Pat, on this score. Moreover, it is perhaps not too much to say that the fundamental ideas of representation, isomorphism and its generalizations, and invariance lie at the core of all of Pat's scientific and philosophical work. Indeed, his 2002 book, Representation and Invariance of Scientific Structures, uses precisely these ideas as a framework for systematically organizing virtually all of his work, from his earliest work on mechanics and the foundations of physics, through the foundations of probability, language, and linguistics, up to his most recent and very empirically oriented work on the representations of language understanding via electromagnetic waves of the brain. You'll hear more about this, not from me, but later. This predominance of formal axiomatics in Pat's thinking is extremely striking, and it is especially striking against the background of his avowed commitments to philosophical pragmatism and empiricism. This is not the kind of framework that one typically finds in the work of philosophical pragmatists and empiricists, or for that matter, in the writings of typical working scientists, whether theoretical or experimental. Pat recently told me a delightful anecdote in connection with another of his scientific contributions, of which he is justly most proud. The publication of his work, co-authored with Acaccio de Barros, on the extension of Pat's no-joint distribution approach to quantum non-commutivity to Bell-type inequalities involving three entangled particles in Physical Review Letters in 2000. The centerpiece of this work, as they originally wrote it, involved two rigorous theorems, labeled as such, and the editors had only one request for changes: that the theorems be removed, and that the authors merely state their results without giving proofs or even using the word theorem. The point is that not even theoretical physicists, as such, are interested in such attempts at mathematical rigor. Pat's work in this respect resembles that of no one in the previous tradition of scientific philosophy so much as Carnap's. For Carnap, too, devoted himself to the formal analysis of scientific concepts and principles. And Carnap, too, was deeply influenced by Hilbertian axiomatic method, although refracted in Carnap's case through the lens of Frege's Begriffsschrift and Whitehead's and Russell's Principia Mathematica. Moreover, Carnap, like Pat, began his career with a strong interest in the axiomatic foundations of relativity theory, and then spent a large portion of his career on the foundations of probability and statistics. Yet the formal framework within which Pat constructs his analyses of scientific concepts and principles is very different from Carnap's. While Carnap focuses on formal languages, Pat focuses on set theoretical models. And accordingly, Carnap's approach is paradigmatic of what one now calls the syntactic view of scientific theories in the philosophy of science business, while Pat's is paradigmatic of what we call the semantic view. The crucial question, however, is why is this important? The point is not, as it is sometimes suggested, that Carnap is committed to the restricted resources of first-order logic, while Pat, at least for this purpose, is happy to presuppose all the set theory that is needed. For Carnap is not committed to first-order logic at all. That's actually quantum. And Carnap's preferred formal language is a strong version of higher-order type theory, essentially equivalent to Zermelo-Fraenkel set theory. Carnap worked closely with Fraenkel during the late 1920s and early 30s. He took his logic and Fraenkel set theory to be basically the same. The point, I believe, is that Pat's distinctive generalization of Hilbert's axiomatic approach is one significant step closer to the style of mathematics used by actual working mathematicians. While Carnap's approach remains at an excessive level of logical abstraction, and accordingly yields very few useful mathematical results, if any. Pat illustrates this without naming Carnap explicitly by contrasting the perspectives on the empirical interpretation of the theory resulting from the two different approaches. While Carnap appeals to the very abstract and general notion of a correspondence rule, which is just any sentence containing both observational and theoretical terms, Pat appeals to the representation theorems that one may attempt to provide for any qualitatively formulated scientific theory, which explain these theorems, at least in principle, how quantitative measurement of the corresponding empirical magnitudes is possible. Indeed, since the qualitative relations in question correspond to idealized experimental procedures often, such as placing weights in a balance and the like, we thereby obtain a useful and unproblematic perspective on how mathematics applies to the empirical world. A perspective that is entirely missing, I might add, not only in Carnap's excessively abstract and schematic account, but also in the more currently popular model theoretic account, if I may use the word account, according to which purely mathematical models are supposed to be directly correlated with purely empirical models, thereby making the application of mathematics a complete mystery. On Pat's approach, by contrast, there is no sharp distinction at all between pure mathematical theories, like Euclidean geometry, and empirical theories. Both are equally in need of appropriate representation terms. And here, from Representation and Invariance, page 3, Pat is saying it's a consequence of his view that there really is no sharp distinction between mathematics and theoretical science, pure and applied mathematics, and science in general. This is one thing I take it that he means by this quote. A further, and perhaps even more important point, is that Pat's axiomatic approach is directed towards the concepts and principles of developing theories at the cutting edge of scientific research. Theories whose conceptual, mathematical, and empirical foundations are still quite unsettled. I'll pause for a moment. This, for example, is why psychological concepts and principles are especially important in foundations of measurement. For there's been a strong tendency to question even the possibility of the fundamental measurement of intensive as opposed to extensive magnitudes, and thereby to question the possibility of a proper application of mathematics to psychology in particular. This point of view, as Pat emphasizes, simply ignores the strong tradition in 19th century psychology, beginning with Weber and Fechner, and continuing through Helmholtz and beyond, focusing on the experimental measurement and mathematical modeling of psychological phenomena. So here, one of his famous whipping boys is Norman Campbell in this respect, who thought that psychology could not be measured under physics. Pat says, kindly, Campbell had some wise things to say about experimental methods in physics. Nevertheless, he seemed to have only a rather dim grasp of elementary formal methods, and his work in measurement suffered accordingly. He did not know of the work of Helmholtz or others. You'll be hearing about some of this work from Duncan Luce, I believe, tomorrow. So Pat's use of formal axiomatic measurement theory is intended not only to clear up philosophical mystery mongering concerning how mathematics can possibly apply to the empirical world, it is also intended to help set a still embryonic theoretical and empirical discipline, like psychology, on a secure path that would ensure science. Judging from the award of the National Medal of Science, quoted in your quotation number 1, it is clear that Pat has indeed made substantial progress in this direction. And if his work on the brain pans out, even more progress. Yet Carnap is not interested in furthering, Carnap is interested in furthering the ongoing progress of empirical science as well. Indeed, Carnap's commitment to philosophical empiricism, like Pat's, rests simply on the conviction that ongoing empirical science is the best example of genuine knowledge that we have. Carnap intends the formal discipline that he recommends, which he calls Wissenschaftslogik, the logic of science, to provide the best means for fostering fruitful cooperation between philosophers in this sense, logicians of science, and ongoing empirical research. In particular, such logicians of science, for Carnap, are supposed to cooperate with applied mathematicians in constructing and formally investigating a variety of possible axiomatic foundations, so that the most fruitful ones for actual empirical research can then be chosen on basically pragmatic grounds. So far, therefore, Carnap's enterprise does not sound so very different from Pat's. The crucial difference, however, emerges in what comes next. For it is centrally important to Carnap that what he calls Wissenschaftslogik takes place at a fundamentally different level from empirical science itself. That it constitutes a meta-discipline relative to empirical science, rather than a part of this science. In particular, while the sentences of empirical science are paradigmatically contentful and synthetic for Carnap, those of Wissenschaftslogik are contentless and analytic. They make no substantive assertions about reality, but either concern what follows from what in a given linguistic framework, a purely logical question, or they express purely practical or pragmatic decisions to adopt one or another particular such framework. Carnap's insistence on such a sharp distinction between synthetic and analytic questions, or more or less equivalently, between internal questions, decidable in principle within a given linguistic framework, and external questions involving the choice of one such framework over another. Carnap's insistence on this does not rest, following Quine's picture of Carnap, on the desire to explain or secure the special epistemic status of logic and mathematics. That's not what Carnap's doing. It rests, rather, on a desire systematically to avoid metaphysical pseudo-problems once and for all, by appealing to precisely the distinction between internal and external questions. Thus, for example, the choice between classical and intuitionist logic for the language of science involves no substantive issue at all for Carnap, and in particular no metaphysical issue, but merely a practical choice that can only be settled, in turn, on the basis of long-run scientific fruitfulness balanced against the desire to avoid possible inconsistencies. At the end of Two Dogmas of Empiricism, while applauding Carnap for this pragmatic attitude, Quine famously goes on to criticize him for continuing to maintain a boundary between the analytic and the synthetic. In repudiating such a boundary, Quine says, he espouses a more thorough pragmatism, unquote. There is no doubt that Pat agrees with Quine on this point. This is already clear in the passage from Representation and Invariance, already cited, and it's now in number 4 of your handout, maintaining, quote, in Pat's words, there is no theoretical way of drawing a sharp distinction between a piece of pure mathematics and a piece of theoretical science, directly against Carnap's view. A more illuminating example, however, of his fundamental divergence from Carnap here emerges in Pat's substantive discussion of Carnap's logical approach to the foundations of probability, which culminates in Representation and Invariance in a characterization of Carnap's original unique confirmation function based on the measure M star by a representation theorem, page 194. Pat concludes with a number of critical comments after this, the most important of which, for our purposes, is the last, which expresses Pat's skepticism concerning Sharp's distinction between Carnap's sharp distinction between two different concepts of probability, one being analytic and the other being synthetic. Synthetic relative frequency, analytic degree of confirmation. Here, Pat mildly expresses a skepticism, which has behind it a lot of ammunition. This, I think, is perhaps most incisive criticism of Carnap's whole logical linguistic approach to the subject. Why? Carnap had originally introduced his distinction between two-concept probability in the late 1940s as a way of attempting to dissolve once and for all what he saw as a typically fruitless metaphysical dispute about the true nature of probability between Harold Jeffreys, representing degree of confirmation, and Richard von Mises, representing long-run relative frequency. Although Carnap expanded his frame of reference in the 50s to include, among others, both the statistical likelihood approach of R.A. Fisher and the Bayesian approach of Bruno Di Finetti, the point of Pat's skepticism, at least as I understand it, is that some of the most interesting, more recent work in the field involves entangling the two concepts that Carnap wants to keep apart in ways that entirely escape Carnap's framework. For, on the one hand, the deep mathematical investigations inspired by Poincaré's method of arbitrary functions for analyzing the chaotic behavior of deterministic dynamical systems, much of it carried out here at Stanford by Joe Keller and Percy Diaconis, and Pat has a very substantial and wonderful discussion in his chapter on probability of this work, shows precisely how certain classical long-run relative frequencies, that is, limiting relative frequencies, such as those underlying the probability of heads in tossing a coin, emerge from the symmetries of the fictional situation in these deterministic systems. And on the other hand, some of the most interesting modern Bayesian approaches involved interpreting distinguished measures like Carnap's M star as precisely objective propensities, here reflected by the assumed symmetries of such measures. These measures therefore appear as nothing more nor less, from this point of view, than privileged prior probabilities adopted on the basis of certain empirical assumptions concerning the underlying dynamics. Pat mentions that explicitly in the section of Carnap. This undermines the philosophical motivations for Carnap's logico-linguistic approach. The guiding ambition, remember, was to develop a platform upon which the scientific philosopher could stand while simultaneously carrying out two distinct aims: to cooperate with applied mathematicians in developing appropriate mathematical frameworks for articulating and testing empirical scientific theories, and at the same time to ward off fruitless metaphysical disputes by systematically distinguishing between internal and external analytic and synthetic questions. This is why, in the present case, Carnap insists on a logico-linguistic approach to probability. It now appears, however, from the remarks I made before, summarizing different parts of what Pat says in his book, that Carnap's approach interacts only weakly with ongoing mathematical research, and in connection with his sharp distinction between the two fundamentally different concepts of probability, thereby fails to engage with some of the most interesting recent developments. One might then reasonably harbor the suspicion, more generally, that this is also true of other attempted applications of Carnapian Wissenschaftslogie, including to the so-called crisis in the foundations of mathematics of the late 1920s and early 30s, that was caused by the paradoxes and intuitionism and so forth, to which Carnap was originally responding in logical syntax of language in 1934. My final question, then, is what does Pat put in place of Carnapian Wissenschaftslogie? The answer is a version of pragmatism, but one that is again completely unprecedented and unique. In particular, it has very little in common in the end with what Quine calls Quine's more thorough pragmatism. For what Quine comes up with is an extremely broad-brush version of philosophical naturalism and empiricism, featuring a physicalist ontology and a vaguely holistic picture of empirical scientific methodology. And this version of philosophical naturalism and empiricism, as I said at the beginning, is paradoxically wholly uninterested in the details of virtually all extant empirical science as it is practiced. What Pat puts in place of Quine's hazy holism, to use my friend Mark Wilson's apt phrase, is an astonishingly detailed engagement with real empirical science in all of its variety and complexity, from the level of abstract mathematical foundations to that of the most concrete empirical applications. Pat's focus, to be sure, has been on the mathematical sciences, beginning with the physics in which he majored as an undergraduate. But his view of this physics was always of a science distinguished more by the complexity and subtlety of its interaction with empirical data than any special foundational character, again, whether ontological or epistemological. His position as a military meteorologist during the war naturally encouraged such an attitude. We shouldn't be misled by thinking physics as a model of precision and perfection, not if it's meteorology that you're doing. Meteorology is in theory a part of physics, but in practice more like economics, especially in the handling of a vast flow of non-experimental data. As I understand him, therefore, Pat sees even our best mathematical science as proceeding entirely without foundations, whether ontological or epistemological again, and also without any claim to ultimate truth. Mathematical or axiomatic foundations, by contrast, are quite a different story. For this enterprise, from Pat's point of view, has less to do with securing our situation against future uncertainty than with developing entirely new concepts at junctures where we are quite unsure of the right direction in which to go next. As in the attempt to develop a satisfactory mathematical psychology, for example, or to appreciate the tension between quantum mechanics and relativity created by the phenomenon of delta entanglement. Pat's version of pragmatism is thus essentially pluralistic, with no particular approach singled out as definitive. The enterprise of modern science, accordingly, is entirely tentative and continually open-ended towards the future. Here's another quote from Pat, and he says, we have to realize that the highly schematic character of modern scientific knowledge, the tension created by a pluralistic attitude toward this knowledge, and skepticism about achieving certainty is not, in my judgment, removable. Explicit recognition of this tension is one aspect of recent historically oriented work in the philosophy of science that I like, Pat says. Pat's reference to historically oriented work leads me to my last observation. Namely, that Pat's version of scientific pragmatism also contains an important place for detailed study of the history of science, and indeed of the relationship between the history of science and the history of philosophy, figuring Aristotle, William James, and others. Pat's conception therefore essentially involves a very long-term historical perspective, together with a broad appreciation of the surrounding intellectual context. This comes out most clearly, perhaps, at the very end of the second part of his intellectual autobiography, reporting on a conversation with the historian of astronomy Knowles Fairbairn, one of Pat's favorite historians. This is my last quotation. It's long, I'll just go ahead and read it. After the conversation, Pat says, I tried to push a pragmatic theory, looking at the broad history from ancient astronomy to Kepler, to show how many concepts that were important to Babylonians for making omens and the like, and later many aspects of Greek thought as well, were simply pushed out of the way and ignored. But the varied and detailed observations made by the Babylonian astronomers and used by Ptolemy more than 500 years later are even of some use today. Ptolemy's own central work was preserved in tradition of a millennium and a half span, leading up to Kepler, and including, of course, the less important work of Copernicus. Less important than Kepler or Ptolemy. In this long period, two important things were preserved. The observations reaching back to Babylonian times, and many of the Ptolemaic methods of computation, which Copernicus himself continued, and were only changed by the new astronomy, as Kepler called what he introduced. The whole subject was then given a much greater perfection by Newton, with the introduction of gravitational dynamics. But much of what Kepler and Newton did rested on the shoulders of these observational and calculational giants of the distant past. It is this that is pragmatic, keeping the useful and letting go of the rest. Note that there is no hint of convergence towards any ultimate truth in this description. Just the ever richer accumulation of empirical data and the development of ever more powerful methods of computation for predicting and accommodating such data based on whatever mathematical models are presently most useful. Nor is there any systematic way of drawing the limits of scientific knowledge and placing fruitless metaphysical controversies forever outside this boundary. Such controversies, if Pat is right, will simply be let go on pragmatic grounds as the observational and mathematical progress distinctive of modern science continues. But scientific philosophy still remains. A scientific philosophy for our own time.
Well, we have a few minutes for comments, especially from Pat, should he wish to...
Well, I can't resist it.
I didn't think so.
You shouldn't resist.
Well,
It's your prerogative.
yes. Let's see. Do I need to stand up? My voice will carry it. Yeah. So I actually find Michael's talk very congenial. Absolutely. And I only wanted to make a couple of comments about my own aspects of my own career and the wonderful conversations I had with Carnap about, for example, the foundations of probability. I'm old enough now that it's a much bigger world than it was when I started in 1950. So I know a huge collection of people. For example, the physicists here at Stanford who are now gone, who are so important to the physics. I'm not gone. I'm talking to Lenny Seskin, our favorite string player, physics department. So my comment is that, I think that in a way, Michael made clear, what I want to do is express some indebtedness here to people. I've made clear my indebtedness to both Ernest Nagel, who was my mentor, and it took me a long time to realize he had really spoiled me as a graduate student. He was very much more attentive to me than I am practically ever attentive to graduate students, it seems to me. I feel guilty about that. So, and then I got a sort of new education, what used to be called the logic of the West, namely Tarski. And I was lucky. I had a very good relation with Alfred. Now, if you know Alfred, I mean, Alfred was very tough on students. So I had a more relaxed relation with him. I wasn't a student. I was very much his junior. And of course, when the phone would ring and he'd say, "It's Alfred," he called up to ask about something to see if I might do, and which I did whenever I could. But I learned a tremendous amount from Alfred and his students. And in fact, Dana, where are you? Well, for example, as a very beginning teacher of philosophy in 1952, what was his name? At that time of teaching that philosophy course. Can you remember, Dana? Anyway, the man teaching the philosophy of science at Berkeley unfortunately died just as the term started. And so they asked me to come over, and lo and behold, I had Dana Scott and Richard Montague as undergraduates. And they taught me much more than I taught them, I think. And furthermore, about every 2 sentences, they had to correct some minor error, I think. It was quite an experience with both Dana and Richard. Now, the really big-time experience I had in this course was something not mentioned here, but actually had a very big impact on me. So, I came to Stanford in 1950, and to those of you who are concerned about salaries now, my initial salary as a full-time faculty member was either $300 or $350 a month. So my wife, and we had one child, she had worked when I was a graduate student, and I've always been somewhat entrepreneurial. So our income as a graduate student was exactly halved when she stopped working, coming to Stanford. So we were really in poverty then. Now, I came from a family that had some resources, but we'd had tremendous battles. I was much too independent to bend the knee to my father. It took a long time for reconciliation to take place. But so I independently first started looking for a little more money. And fortunately, I ran into Al Bowker, many of you know, who was the great organizer and creator of the modern mathematical statistics department here. But in general, organized what was then called the Applied Mathematics and Statistics Laboratory at Stanford. Well, now it's characteristic of me that I spent my first year in philosophy, and the second year, independently, I moved into the Applied Math and Stat Lab, because I felt very congenial there with the characters. But the important thing about that move is, Al then looked for some money to support me in the summer. Now those were days when money was really scarce. I know there are real complaints now, but it was really scarce then. So he found it in working with David Blackwell and Abe Gershik on their book, Game Theory and Decisions. And that was my real additional education. That was an education different from Ernest Bacon, different from the background from Tarski. This is where I really learned something serious. Now, what was interesting, what I actually worked on, and what joined me in this, some of you, only the aficionados around here, know the name of Herman Rubin. How many people remember Herman? Oh, well, there's quite a few people. Well, Herman was an enfant terrible. We used to have a joke when Herman, how come it took you so long to get your PhD at 19? Well, I had to spend a year in the Army, his response. So Herman was something else. We used to say, the door jams of other people were his office. So both Abe and David, of course, a very well-known probabilist who had a number of great contributions to probability. But David didn't like to write in extenso, and Abe couldn't really write in a detailed scientific way, was an enormously experienced and wise statistician. So they were writing this book. So this is the days when O&R had extra money, so they got me to rewrite almost all the formal material in a set theoretical fashion that would satisfy, for example, Alfred. So it's a little bit too formal, that book, in a way. And Herman had to check everything to make sure there weren't any errors in any of the proofs. So he and I worked together very extensively, and they generously acknowledged this, by the way. But the important thing about it was the effect on me. That had absolutely a tremendous effect of having to get right down into the nitty-gritty of all these questions about game theory and about probability and Bayesian strategies, etc. And that's where I learned a lot. That's my other education. And it's against that background that when I met, not too much later than that, Carnap, that I had been educated by then, hanging around not only the applied math and stat lab doing this work, I had an attitude to probability very different from what was going on in probability and philosophy. And so I had very good discussions. Now, I want to say something wonderful about Carnap that Michael didn't say because he omitted it, but those of you who knew Carnap just had one of the most generous and outgoing personalities possible. Dana, I think you knew Carnap a bit. Now, you agree with me, I'm sure. Who else knew Carnap in his days at UCLA? Maybe not. Duncan, you did?
Jaco.
Huh? Jaco did. Yeah, I'm sure you agree with me, Jaco. Wonderful to talk to. And wonderful conversations. And I was critical, and it came out fairly early, of Carnap's big treatise on probability. It was too much ado about too little. When it came to the subject of probability, I was a bright young man who was talking to Carnap, and I liked him. So I was careful of my criticisms. But he told me then, after we talked a lot, he said, well, you know, in many ways, you're coming at this from the right standpoint. That's the kind of generous spirit of Carnap. I just want to tell this Carnap story. I think you'll find it interesting. He said, von Neumann told me when I was at the Institute, what you should do is go and study how probability is used in statistical mechanics. You'll have a much better feeling for it theoretically if you do that. And he said, I've come to realize that that was good advice, but I didn't carry it out. And now my big regret is that I didn't take more of a turn in terms of my reflections on the foundations of probability. And I think, in other words, what I'm saying is I think Carnap himself, in retrospect, had regrets that he hadn't made his work in the foundations of probability have a more intimate association in relation to the use of probability in the mathematical sciences, particularly in statistical mechanics. And that's, I've always taken that as a kind of, that was a very good response of his and one I very much agreed with. And what I feel, what I'm really wanting to communicate here, how lucky I was to have, I'm really somebody who's been very fortunate and lots of good supporters when young. I got wonderful direction from Nagel. I got great help from everything from Dana, who's younger than me, of course, but which always going to tell me when I need correction. That kind of correction. And then the work with Garcia and Blackwell and that work. So I've benefited from I'm one of these people who have been very lucky in benefiting from learning a lot from other people. As I still say, when I give a seminar, really the seminars I tell the students like to, the real purpose of this seminar is to educate me. And that usually happens. I do get educated by good students. So I very much believe in that, but it was especially important. In order to break, I could have come out in a mold that was too philosophical, that is too narrowly philosophical. And so although I'm sort of a dilettante and scatterbrained in a lot of different interests in many ways, as far as I'm concerned, I've benefited from that. I'm one person that has. Now, the second remark, I'll make this very quick. I wanted to say that. I got a couple of minutes.
You got 10 minutes?
Yeah, you knew if I got it. Yes. So I want to make a remark about Quine. Quine I found very congenial, but I had much more respect for Carnap. Quine, you see, I think was probably in some sense more able than Carnap, if I had to make a kind of absolute judgment. But Quine really shut down on working seriously. He became a kind of horror philosopher. And I mean that seriously, because I have great respect for Quine intellectually. And I think it was just too bad that Quine didn't follow the tracks more of contact and have greater interest. I think it was too bad for American philosophy. Quine had very great influence and properly had influence. But we'd been much better off if Quine had been more willing to dig into the details of the various sciences. And it would have been very useful if his pragmatism, which I very much agreed with the general spirit of, reflected more details of what was going on. So, but those things happen, and that's the way it is. I mean, and Quine remains and should be, you know, as a great American icon of philosophy. And certainly his heart and his head were in the right place. He just sort of filled his head with a little more details of various sciences and commented, because his comments would have been great. What else did I? Oh, yes, about that publication of the second volume. Foundation of Debation. Duncan, where are you? I saw you a minute ago. There he is. Well, Duncan and I agreed to write this 3-volume with 2 younger collaborators. And one of them,
we agreed to write a volume.
Huh?
We agreed to write a volume.
Right. And it expanded into 2, and because one member sat on the manuscript, not me and not Duncan. 17 years, volume 2 was a little late. And then when we got to volume 2, there was so much material we had to put out 2 more after the 3rd volume as well. So I wanted to say,
I stand corrected.
well, I'd say my fault. If I were to say my fault, I often publish too soon. I mean, I'm too impatient and send things out for publication. Been better off than if I'd sat on them longer.
You waited a good amount of time for representation and impairment.
Yes, I did.
That was just the right
no,
time.
that's different. That I wrote over 40 years. I kept adding things. That's why it's so unreadable now. I put way too much into it. So there's something else you said that I wanted to comment. These are all good comments. I mean, Michael was. I love to disagree with Michael.
Should I say something about Kant?
Yeah, I just think. But I think not. I think that's more than time for me to shut up. I'll have more to say later.
Right, well, it's great to be here. And it's a little bit of a weird occasion for me. If you don't know, Pat was my dissertation supervisor, and I'm looking around the room, and there are some of my former teachers here, so I hope I get a good grade for the lecture. I'm going to talk today about a paper that Pat published exactly 50 years ago, 1962. It's an absolutely terrific paper. In my view, it's one of the great classics of 20th century philosophy of science. And I want to just briefly tell you what the core themes of Pat's paper were, and then transfer that to a contemporary example to see how you can apply this to some issues that are important in philosophy of science today. So here's some of the main themes of the 62 paper. One of the essential features that Pat was emphasizing was that in order to get from high-level abstract theory down to the data, you have to interpolate a hierarchy of models. And some of those are going to be of different logical types. Second thing there, which in fact was picked up later by Bogan and Woodward, that there are theoretical notions in the theory which don't have any direct observable analog in the experimental data. That means that the mapping from the models to the data is going to be complicated. The third point is the really important one, in that models of the data are selected from possible realizations of the data on the basis that the theory of the experiment tells you what constraints there have to be on the data in order for them to be models of the data. Now, I'm going to generalize this a little bit because I want to focus on some issues that are outside traditional experiments involving computerized instruments. I'm also interested in simulation, so I'm going to talk about models of data-generated conditions. Now, there's an ongoing issue in philosophy of science about the relationship between experiments on the one hand and simulations on the other. One way to approach this, which I find fruitful, is to ask oneself what the epistemic differences are between the data that you get from traditional laboratory experiments and the kind of data that are cranked out by simulations. It's obviously, at least I think it's obviously, that there's going to be a difference, but one's got to articulate that, and it turns out not to be so easy. The second question here is to ask what the nature of the relations are between the bulk of the data that Pat was talking about and the actual concrete data that you're getting from the experiment. And the third question is, once you've got answers to those, what does that say about the nature of biomechanics? And we're going to walk through some stuff and then we'll come back to these questions. Here's the running example that Pat used in the paper. It's beautifully simple and illustrates the points in a very transparent way. For our purposes, the thing to focus on here is that theoretical parameter theta, that's the learning parameter. And one of the things that one is trying to do in these situations is to provide an estimate of the value of theta. Now, here's one of the things that Pat did that I thought was really insightful and people have not properly appreciated. When people are talking about models of data, they tend to think that we're going from the top down. What Pat said is that frequently what you're doing is you're starting with the data, and what you want to do is to find some kind of learning theory and evaluate the parameter that's going to appropriately represent it. And the focus of Pat's own paper was on the statistical methods that you use, the statistical models that you're using to appraise the data and see which of those data streams actually count as models of the data. Now, again, I'm going to generalize. I'm going to go to a different context. That's context of instruments that use computed tomography. Now, you're all familiar with these from medical context, but I want to emphasize that these methods are very widely used. They're used in radio astronomy, they're used in ground sending radar, and a lot of other areas. And if we think about the images that they produce, you can think about that as a function that's justified in a plane, and the value at some point in that plane represents the value of some problem possessed by the target. So the analog between Pat's theta and these things is that what you're trying to do is to estimate the values of G. And the second parallel is when Pat was saying that what you often do is you go upwards from the data to the value of theta. In these cases, what you're doing is using a very sophisticated set of methods of inverse inference to get from the data to construct the image. So you're actually going backwards from the data up to the feature. And here, in general, we're going to focus on the property of interest being the X-ray attenuation coefficient. And here's just a bare rudiments of what's going on. So you're looking at a slice through a target, slice through the body, something like this, a two-dimensional situation here. Here's the target. One side you've got an array of M emitters of X-rays, and on the other side of the target you've got a corresponding set of M detectors. The X-rays are emitting, the sources are emitting the X-rays of the known intensity as they traverse the target, and the target has differing densities according to different kinds of tissues. They will be differentially attenuated, and the values of the resulting intensities will be picked up on those detectors. The whole apparatus here is rotated then through an increment of theta. The target stays where it is. You get a different set of projections for the next value of theta. And so you end up with rotating the detectors and the emitters through pi degrees. And the data that you get then is an m by n matrix, m being the number of detectors and n being the number of values of theta through which you've rotated the apparatus. So that's the basic setup, and the task is to reconstruct the interior constitution of that two-dimensional slice. All right. Here's the mathematical techniques, and this is corresponding to that high-level learning theory case that Pat was giving you. So this is at the top of the hierarchy. What you've got here is the projections at the value along the detector framework of R at given value of theta. And you get that by picking out that value of R by using the delta function. Here is the target frame value for the attenuations. And what you're doing there is simply accumulating all the values of the attenuation along the ray that corresponds to the value R that's picked out by the delta function. And that's the radon transform of G over the projection. Right? And so that's how you get from the values in the target to the data. This thing here is representing the data points that you've got in the matrix. Your task is to reconstruct the interior values of G. That's the image that you want. And so you're going to use the inverse radon transform. Problem is that if you just do that straightforwardly, the image is blurry because of noise coming from various sources. And so what you do is you convolve that with some appropriately chosen filter. And of course, Pat knows all about this because he uses filters of a rather similar kind in his brain research. So what you can do is reconstruct the value of G using the data values that you've got from the experiment. Right. Now, one of the important things about these instruments is that you've got a physical system that I described there with the X-ray emitters and so forth, coupled with a set of computational processes that are integrated into the instrument. And so what you're doing is stepping down from that theory to this discrete level where you can apply the computational processes. And so what you do that convolution process, and then you Fourier transform the results into the frequency domain. The reason you do that is that convolutions are computationally intensive. If you transform into the Fourier domain, they become multiplicative. Multiplications are much easier to do, so you do the multiplications over there. You then inverse Fourier transform back to the spatial domain, and then you compute the inverse radon transform. So that's a sprint through the basic theory of these approaches. So back to the questions. And let me drop the pace down a little bit. Just talk about what's going on here. So here's the question. What are the differences between the data that you get from empirical observations and experiments on the one hand, and data from computer simulations on the other? Now, remind you, what you've got here, and this is the reason why I find these particular kinds of instruments interesting, is that you've got hybrids. You've got a combination of something that is a traditional physical instrument on which you're getting physical data on, together with something that is computational. And when these things are calibrated, they're calibrated on what are called phantoms, and you can have physical phantoms and you can have simulated phantoms. So instead of putting in physical data that's coming out of the experiment, you just substitute it for simulated data, and the constructed image that you get, if you're calibrated the thing right, the instrument and the algorithms are working okay, you'll get an image that is almost indistinguishable from the image that you would get from a real object. So here's a nice test bed for these kinds of things. Now, here's the background. Remember the hierarchy that Pat directed our attention to? Lots and lots of models playing a role in getting from the abstract theory down to the data. For example, you've got competence scattering, an X-ray that starts out on a given ray will be deflected sometimes and picked up by a detector. The detector is off that ray somewhere else. You've got to correct for that. There are inefficiencies in the detector that have got to be corrected for. There's beam hardening. That is that low-intensity X-rays never make it to the detectors, so you've got to correct for that. There's noise, which I've already mentioned, and there are many, many others. So there's lots of models involved just in appraising the physical processes. Mathematical approximations, you've got to go from continuous radon transforms to discrete versions of them. You've got finite rather than continuous Fourier transforms. The filters get truncated after a point, and so forth. And then you've got the familiar computational approximations. You've got the truncation error for real numbers, precision decisions to make. You've got the fast Fourier transform approximations. You've got trade-offs, very important trade-offs between the amount of computational time you're willing to devote and how much accuracy you want. There's a patient there, you've got to produce the image. That trade-off is crucially important. And the point here is that all of these models are feeding into your understanding of whether something is, in fact, a correct set a correct model of the data for you to be reconstructing the image of. There are statistical versions of this, but here's the sort of application of Pat's hierarchy to another case, very complicated, but all of this goes through in a very straightforward fashion. Okay. Second question, what's the nature of the relations between the models of the data and the actual data? And the third question, what does this say about the nature of applied mathematics? All right. So, here's the time to say something provocative. I knew you would probably think you were talking about giving you something to respond to. So here's a quote which mirrors a couple of things that Michael Friedman picked out from some of Pat's writings. And let me read this. He said, from a conceptual standpoint, the distinction between pure and applied mathematics is spurious. Both deal with set theoretic entities, and the same is true of theory and experiment. Right, now, another of the running themes in Pat's paper was his claim that if you want to understand the route from theory to data, formal methods can be employed at each of the steps in that hierarchy. And the details of the design of the experiments that were informal are things that philosophers of science should probably stay away from and focus on the things that can be represented sharply. Now that's a fine model, but here's a little complication that I think maybe we might need to get a bit of daylight between pure and applied mathematics. So I mentioned that computerized tomography instruments are hybrids. They generate physical data, and then they go on to data processing. That data processing is automated. So think the following situation. Right? You've got a target in there, you've got a purely physical process that leads to counts in the X-ray detectors. These are fed into computational devices, which in some cases, for example, there's out there a wide variety of commercially available chips on which fast Fourier transforms can be performed. Software is being transformed into hardware. So in some cases, what you get is a purely physical process from the input to the output. Now, this is an issue that people in computer science have dealt with for a long time, but I think that philosophers of science have not paid enough attention to it. And it's this. If you can bring to bear this apparatus in a way that is purely physical from the input to the output, but it's clearly applied mathematics in some sense, the kind of things that Pat was emphasizing, formal representations, pure and applied mathematics, I think perhaps don't obviously apply there. And that a purely physical account of computation is something that we need to say something about. So that's the challenge. It's the end of the talk, except for one thing. There's a guy who used to own a company down the road who used to end his presentations with, oh, there's one more thing. There is one more thing here, and it's very important, and it's to say thanks to Pat and happy birthday.
Well, the speaker starts, excuse me, stayed within his time, and we have a few minutes for questions. Pat, you have a comment?
Well, I think it is intriguing what your comment, of course, and that is in fact, a general thing now is the distinction between abstract computation and actual physical computation. And that, one axiom of physics sometimes claims all computation must be physical. And I agree with that.
With a pencil, how do you prove without a pencil?
Or something.
Something like that.
Exactly. But I think still, the way theory of computation is done, that's an important distinction. And it needs to be pushed on more than has been. So, for example, a very good example of things I'm thinking about these days is not just how does the brain make a computation, where you may use anything possible, but can you give a physical account of how that computation is actually being made, which is different from applying statistical and mathematical techniques that you have no evidence have anything to do with the actual processing of the brain. And I think that kind of concept, what you have in mind, I believe.
Yes. At a much more elementary level, because we understand those sort of shapes better, because we can't understand the brain.
Questions, comments? I'll give you a chance. Yeah, go ahead.
Well, at some point, you're going to have to prove that these different transforms have the properties you want them to have.
Mm-hmm.
So that'll be the mathematics, the applied mathematics.
Right, but it's the mathematics made concrete. Obviously, there's a lot of traditional mathematics that has gone on before you get to the hardware stage. But once that's been reached, the claim is that there's applied mathematics, and it's not just an application of a bit of pure mathematics in the representational sense of that. So wonderfully challenging patterns.
What's the difference between applied and pure mathematics? I missed that.
I only had 15 minutes.
No, I know.
Wait, I'll explain afterwards.
Okay.
It's a long story. Okay?
Okay, yes.
Yeah.
You are released.
All right, it's an honor to speak here today about work which I actually did in collaboration with Pat. I met Pat first at a congress in Florence in 1994, and a student of his attended my talk, and the next day Pat wanted to speak to me. I was delighted, and since then we had many conversations, mostly about physics, but also about many other things, and this work started about 2 years ago. So here's a quote from the Stanford Encyclopedia entry on quantum logic and probability theory. It says that it's uncontroversial, though remarkable, that the formal apparatus of quantum mechanics reduces neatly to a generalization of classical probability, in which the role played by a Boolean algebra of events in the latter is taken over by the quantum logic of projection operators on Hilbert space. That's what the Stanford Encyclopedia says, but I think Pat disagrees with this. He has been defending a different view, according to which we should keep the algebra fixed and change the probabilistic structure. More particularly, Pat works with upper and lower probabilities and shows that things work. At least that's what he wants to show. However, it's fair to say that despite all his efforts, upper and lower probabilities are not so popular in physics, and they are also not so popular in the foundations of physics, at least so far. So instead, quantum logic is booming. Certainly, again, after quantum computation became a hot topic. What I want to do in this short presentation is to add another reason why one should look at and take seriously upper and also lower probabilities in quantum mechanics, and that the research program that Pat kicked off is certainly worth following. I can't go into the details, so I will focus on the big picture, and I apologize to the experts who know much more about this than I do. Here's the structure of the talk quite straightforwardly. I first talk a bit about uppers and lowers, then about quantum mechanics, and finally I bring the two together. So what are imprecise probabilities? The idea is that we want to represent ignorance about a probability value. And the idea is then to introduce a lower probability and an upper probability, which could, for example, be 0 and 1 if we don't know anything, but then in the course of learning, the two converge to the true probability value. If one axiomatizes this, and Pat likes to axiomatize things, then we come up with a structure where upper probabilities are sub-additive and lower probabilities are super-additive, so it can be nicely formalized. The interpretation is also quite straightforward. Wally argued that upper and lower probabilities reflect minimal and maximal betting odds. Yeah, so that's sort of a Mickey Mouse picture that illustrates the situation here. Question is, of course, what has all this to do with quantum mechanics? So I talk for a minute about quantum mechanics. Consider 4 random variables, A prime, B prime, which can take 2 values, +1 and -1. Then one can define this quantity F here. E is the expectation value of this product, A, B, which measures the correlation between A and B, can also take 2 values, and anything in between, actually. And these expectations can be observed. Now, Clauser, Horn, Shimoni, and Hole generalized the Bell inequality and showed that if there is a joint probability distribution over these 4 variables, then this quantity F is smaller or equal to 2. It's just, it follows from the existence of a joint probability distribution. Now, it turns out that quantum mechanics violates this inequality. That is, there are systems which have stronger correlations that where this F is greater than 2. Right? So standard example is the EPR state, which is this kind of superposition of, for example, spin up and spin down for a 2-particle state. Now one can define angles alpha and alpha prime on one side, and beta prime on the other side, measure the 2 systems and just detect the correlations that hold between these measurement outcomes. And it turns out that if one sets the angles appropriately, then one gets a value of 2 square root of 2 for this quantity F, which is, of course, greater than 2. So quantum mechanics violates those inequalities. Typically, the experiments are done with photons. For various reasons, I think it's nicer, Pat disagrees, to do this with atoms. So one can look at 2-level atoms, one can bring them in an EPR state, and define quantities, measurement operators A, B, A prime, B prime in this way through the Pauli matrices. And if one does so, and do the experiment, it turns out that again the quantity F is 2 square root of 2. We have a maximal violation of the Bell inequalities. So that's all well known. The new concept I would like to bring in this context here is the concept of decoherence. The idea is if we have such an entangled state of 2 atoms, it will sooner or later decay. So sooner or later, all atoms will be in the ground state. Right? And one can describe the dynamics of this state, and one can use this to calculate the correlations, A, B, A prime, B prime, and so forth, as a function of time. Plug it in the Clauser-Horn-Shimoni-Hole inequality, and one will find out that after a certain period of time, actually very shortly after the state starts decaying, these inequalities are satisfied, which means that a joint probability distribution exists, which also means that a classical description, a classical story can be told, which tells us how these correlations come about. So that's quite remarkable. The question is, however, what happens before? Yeah? Before a joint distribution exists, how can we account for the correlation in this regime? How can the rather strong quantum correlations be explained here? And as you might have guessed already, that's how imprecise probabilities come in. To cut a long story short, what one can show is, at least for this Bell EPR case, that there is always a typically non-unique upper probability distribution that converges to the joint distributions once the Clauser-Horn-Shimoni-Holt inequality is satisfied. Yeah? So we have here a situation, unlike in the classical case, where we always have a joint distribution, we just don't know it, and we define uppers and lowers to reflect our uncertainty about it. Here we have the situation that there is no joint, at least for a certain time, and once it exists, we can show that the uppers and lowers converge into that joint distribution. To qualify this, we can always find an upper, often also a lower, but not in all cases. And certainly the lowers will not follow this law. The lowers will not follow this law, which is typically assumed. So one has to define or calculate the lowers independently. So uppers and lowers seem to have a place in quantum mechanics. I don't think it's trivial or obvious that we can always find such uppers and lowers in the quantum context. Yeah? So that's the situation in a sketchy picture. So the upshot or the point I would like to make here is that decoherence, which is an important phenomenon recognized everywhere as a fundamental property of quantum systems, they decay, they evaporate entanglement in the environment. Decoherence fits well into the picture of upper and lower probability distributions, as we can precisely understand how upper and lower probability distributions evolve over time and eventually degenerate into a joint distribution once a classical description of the system is possible. This transition from the quantum to the classical is much harder to understand from the point of view of quantum logics. Yeah? It's not at all clear, at least to me, correct me if I'm wrong, what it means that a non-Boolean algebra somehow degenerates over time into some Boolean algebra. Yeah? One may be able to model it, but I haven't seen these models. Yeah? So typically what people are doing is they look at a quantum domain and describe it with a non-Boolean algebra, and they use a Boolean algebra for the classical part. Yeah? But the two are connected. There is a transition between the quantum and the classical, and playing around with the probabilistic structure which is defined over an algebra and not with the logic beyond seems to be the much more natural approach here. Yeah. I'm doing well on time, I see, so I can take a bit of time with my last substantial slide here. There is, of course, lots of open questions. I said in the beginning that that's a research program that had somehow kicked off, but that's not yet terribly popular. So there's lots of things to do. For example, what one would want to do is to generalize the results that we obtained for EPR states to other states. Pat did work on the GHZ state that was mentioned before, so it's natural to do this and to look at more complicated states and see how they behave over time and which uppers and lowers are associated with the dynamics of these systems. The most important question, perhaps the most pressing question to me, however, is that one should better understand what upper and lower probabilities in quantum mechanics actually mean. Yeah? Remember that classically there is this Wally-Betting interpretation, yeah, which is fairly straightforward, but it presupposes that there is a joint distribution. So if there is no joint distribution, what are you actually doing here? So that doesn't work. If we simply consider uppers and lowers as some kind of bookkeeping thing, yeah, which that produce measured correlations or so, then we don't have to go for uppers or lowers. We could also go for negative probabilities, which Pat likes a lot these days. it would be interesting to understand better what uppers and lowers mean. Pat seems to have a theorem that shows that the upper-lower language is sort of equivalent to the negative probability language, in which case we probably don't have to worry too much about the interpretation. But anyway, so that is something to look at. And as I said already, the relation to negative probabilities, which of course also fit nicely into the decoherence picture. It seems intuitive that we can also propagate negative probabilities somehow over time. They will, of course, become zero or whatever at some point. Another interesting question which I'm currently working on is this regime between 2 square root of 2 and 4. Yeah? Remember, we are looking at this quantity f here, yeah? And the expectations values are between -1 and +1. So in principle, this guy could be 4. Right? It turns out that with quantum mechanics, we only get to 2 square root of 2, not higher. Yeah? But there is recent interesting work by Popescu and collaborators which show that you can get quantum speed up also if you explore this regime greater than 2 square root of 2. So that's quite interesting. And from our point of view, it would be good to see how qualitatively uppers and lowers change in that domain. Yeah? So we can also fit uppers or so for correlations which give us an f greater than 2 square root of 2. But it would be interesting to see which physical property has to be added to account for the quantum regime or so. Yeah? Otherwise, it's not quite, I mean, it would be surprising that a mathematical structure fits so nicely directly onto the quantum regime. Anyway, so there is things to do. And what I also find interesting to explore in future work is the analogy between learning and decoherence. Yeah? So these intuitive pictures that I showed you here, that if you toss a coin, yeah, so initially you don't know anything about this coin. So you would say, okay, lower 0, upper 1, then you will flip your coin, and as a result of this, the uppers and lowers converge to 1/2, for example, if it's a fair coin. Yeah? So learning, yeah, leads to this convergence of uppers and lowers to a joint probability. Yeah? This quantum picture is quite similar, with the only difference that at least till they converge, there is no joint. Yeah? But the interaction of the quantum system with the environment somehow has the same effect as learning. Yeah? So anyway, I mean, that's just a speculation which might be interesting to explore in future work. And that's already the end of my talk. Happy birthday, and thanks for listening.
As usual, you get first.
Well, I think the question we've discussed a lot, because we have these very simple computations of decoherence time, decay, using either the upper and lowers or the negative probabilities, much simpler than the Hilbert space computation. And the question is, can that really be defended on its own physically? I think is really an interesting question. Because the computations are so much simpler. But can they be defended as physically correct? What do you think?
No idea. I hope so. But yeah, that's a good question.
Can one be derived from the other?
Well, they're on sort of independent tracks, in a way. I mean, they clearly have, they're going to be close. In fact, we show in one paper we wrote that we can get, they do essentially the same thing. But it isn't it's the fundamental derivation of that decoherence time. I think it's the most interesting physical question here. It's so simple and elementary in the case of the upper probabilities or the negative probabilities. And that same computation, numerically, is tortuous carried through the Hilbert space formulas.
but well motivated by quantum mechanics?
You know, that's perhaps also a question. That could be discussed. So we'll leave it as a question.
So one of the advertisements for decoherence, it was going to deal with this mysterious collapse of the wave function, okay, by having a continuous transformation going forward. You know, these upper and lower, the calculations easier is Pat's basic claim here, but you're going to get the same answer as the Hilbert thing when you carry out a decoherence calculation. It's just an easier calculation, but basically the mysterious collapse has still gone away via decoherence.
No, the collapse is still there. Decoherence doesn't solve the measurement problem. What you show is that you end up with a mixture, so about which of the options is realized is then still not explained. Yeah? And our work on uppers and lowers doesn't contribute at all to this. Yeah? So we are operating in the framework of standard quantum mechanics. We are not changing anything. We are just, well, it's about the foundations of the theory. Yeah? And that was the point I wanted to make, that we can mess around with the algebra or we can mess around with the probability. Yeah? Both lead to the same predictions, which are confirmed and which are, that's quantum mechanics. But we think it's more interesting to keep the algebra fixed and to play with the probabilities. But that doesn't solve any problems that one would not be able to solve with standard quantum mechanics. And the measurement problem is a problem. That's all. Good loss.
One more question?
I guess I'm a little confused about what it means to keep the algebra fixed. I mean, one is you start with the Hilbert space. This is the classical thing. I mean, you have the probabilities defined there. You have Gleason's theorem as some kind of representation theorem. That all fits with this quantum logic in this very abstract way. So as long as you've got the Hilbert space, what that guy said was right, namely you can represent it that way. In many ways a natural way. Yeah. So now what we're going to do is we're going to have axioms for probability, just that are abstract, no Hilbert space anyway. Right? But I don't know if this was the question. I mean, is there going to be a representation theorem for that probability theory that says there's going to be some kind of Hilbert space?
Or vice versa.
Huh?
Or vice versa.
Or vice versa. Right? I mean, so that if the Hilbert space is still there, I mean, what is it in your gut feeling about this? Do you think that you're going to have a more general structure than Hilbert space, and that's the algebra now? Or are you going to have a representation theorem that's just going to get you back to Hilbert space? Or what?
I think it's the latter.
The latter. But then there will be some answer, maybe it will be complicated, to your question about how do we get this convergence. I mean, it will be some kind of convergence from the Hilbert space where, you know, some planes get really close together so that it's almost classical, just like you almost have joint distributions.
I mean, what I was focusing on was this claim of quantum logicians to use a non-Boolean algebra.
Right. But there is a non-Boolean algebra in the Hilbert space. The whole algebra is not Boolean. Where did it go?
Okay. Well, I think the interesting question, I mean, the apparatus is very much simpler. You certainly cannot derive the Hilbert space within that. You have to have something much extra go. And I'm more skeptical than Stephan is about the Hilbert space. I mean, I think it's not very natural in many ways for many problems. And so that doesn't mean, though, I'm not suggesting I have a good quick answer, but how are you going to replace it? I mean, in a way, you see these computations, we accept them because they can agree with the Hilbert space, and we need to have a deeper understanding than we do now.
Well, there are contexts where you can really isolate a system from its environment and make decoherence a very, very, for example, very slow and very, very controlled process, where you can study it in detail. One photon comes in at a time, and slowly, the system is made decoherent. Isn't that a context where the Hilbert space representation of everything is completely under control and where you can really calculate and do things?
I mean, that's what we are using here for the atoms, and a cavity or so.
And we know that it's correct, experimentally correct. So it looks to me like there's only room for reinterpretation, but I'm going to button my lip right here.
Yeah.
Okay, if there are no more questions, I assume there are no more. We'll move to the next.
Turbulence or something. So I'm going to talk about Pat's role in something called structuralism in physics. This is my talk. It's a quote from Pat. Data that Paul Humphreys discussed. Now, philosophers of science will know that the structure of science is the title of Ernst Nagel's book of 1960, which at the time, as an old Columbia student, I was around when Nagel was still alive, and I certainly thought of it that way. And I see as in Pat's work a lasting influence, if not a partial isomorphism, of Nagel's particular combination of what he called, or what was called about him, critical naturalism and philosophy of science. And that's despite the fact that Nagel frustrated Pat's desire to write a dissertation on axiomization of physical theories. Now, I have in mind Nagel's quite skeptical approach toward the then quite prevalent syntactic characterization of theories. Nagel's refusal to engage in grand philosophical pronouncement, his philosophical modesty, as it were, not a word you ordinarily associate with Pat, but, and his emphasis, departing in this regard from the Deweyan naturalism to which Nagel was so close otherwise, that formal analysis is an effective tool which should be used wherever possible, particularly in that area of scientific methodology Nagel himself said was characterized by a general fuzziness, the application of theory to empirical subject matter. I shall say more about this in a minute. But for the moment, I only want to observe that the context of this statement, in the context of the statement that we saw, structure of science is used in the Nagelian sense as referring to, quoting Nagel, the logic of scientific inquiry and the logical structure of its intellectual products. Now, the term besetting sin evokes the implacable moral ferocity of an Old Testament prophet. An association perhaps not completely unsuited to Pat's frequent complaints, which we're all familiar with, about the lack of, quote, unquote, any serious discussion in the philosophy of science literature of many issues arising in the methodology of experimentation and testing of scientific theories. While but few philosophers of science have risen to Pat's challenge to produce interesting descriptive analyses of actual experiments in science, Paul Humphreys is an exception, a large number have followed his lead in thinking about the formalization or representation of scientific theories. And whether Pat sees himself this way or not, to many philosophers, Pat is the Elijah of structuralism in philosophy of science, proclaiming the language of models while powerfully preaching against the Philistine idolatry of the linguistic or syntactic view of scientific theories. Oversimplifying. A recurrent theme in Pat's work and conversation is how very distant, abstract, and inaccurate are most philosophers of science's conception of science and of scientific theories from the practice of science, that is, familiar to the working scientist. In a forceful attempt to rectify this disciplinary shortcoming, Pat somehow managed to publish a paper in 1960 that opens implausibly with several pages of longish quotations from the scientific literature where the term model is employed. Despite the various seemingly quite distinct senses of the term in fields as far apart as economics, psychology, and physics, Pat argued that all these uses could be subsumed under Tarski's sense of model. Moreover, in understated Hegelian fashion, Pat suggested that even radical instrumentalist conceptions of theories must also, quote, yield the ordinary talk about models and theories as first approximation. Here, a model or structure is a non-linguistic object of the appropriate type in which a theory is realized or satisfied. A characterization sufficiently broad enough to encompass both the mathematician's sense of model and the great diversity of uses of the term model in the empirical sciences. In brief, the set-theoretic conception is the, quote, basic and fundamental concept of model needed for an exact statement of any branch of empirical science. And it is more fundamental than the various concepts of model employed in the empirical sciences in the sense that one can use it to give an exact statement of the theory or use it in exact analysis of the data under investigation. In Pat's conception, a theory is presented by the specification of a set-theoretic predicate, essentially an ordered n-tuple of set-theoretically defined objects. The theory can then be viewed as the collection of structures picked out by the set-theoretic predicate. Now, it would appear that considering theories in the empirical sciences as set-theoretic structures is a reflection not only of Tarski's model theory, but also of the significant impact of the Bourbaki mathematics text in the immediate post-World War II period, and influence both pedagogical and broad enough to be considered cultural. Thus, an observation frequently made by Pat, the mathematician's statement of a theory, say the theory of abelian groups, is quite distinct from the syntactic account of an axiomatized theory. This mathematician's sense of axiomatization underlies Pat's well-known papers on axiomatization of classical particle mechanics with McKinsey and Sugar, and relativistic mechanics with Ruhmann. A methodological theme of these papers, and in Pat's logic book of 1957, is that formalization of theories under restriction to first-order logic is like boxing with one hand. One might possibly do it, but the result can be neither pretty, nor pleasing, nor efficient. The language of set theory, which can, of course, be given first-order formulation, is required. Now, in the 1950s climate of American philosophy of science, this was something of a heresy. After all, it was only in the 1950s that a passing familiarity with first-order logic became a requirement of the philosophical curriculum. Moreover, there was a widespread perception, prompted, among other influences, by Quine and Goodman's Steps Towards a Constructive Nominalism paper of 1947, which held that responsible philosophers of science must eschew abstract objects of which sets or classes are exemplars. That Quine quickly, but sub rosa, backtracked from nominalism was not generally apparent until much later. Tarski, whose model theory was a principal stimulus to the conception of models of empirical theories that Pat pioneered, certainly also had strong nominalist leanings. But Saul Pfefferman has observed that set theory was, for Tarski, the paradigmatic instrument for purposes of conceptual analysis. Tarski early on submerged any nominalist metaphysical qualms by appeal to something like the pragmatic indispensability argument for the use of classical mathematics in empirical science that we associate with the later Quine. Pat, so far as I can see, has never allowed any metaphysical qualms to impede conceptual analysis. The upshot is that scientific theories are to be presented using mathematics, that is, set theory, not logic. This message to philosophers of science was in any case fully in step with the developing practice of how theories are represented for certain purposes in physics. And I'll just could point to the book of Hawking and Ellis in 1973, The Large-Scale Structure of Space-Time, which is a text on general relativity. Now, to my knowledge, this is the first, if not the first, but it's the most influential, explicit presentation of any modern physical theory in structural form. It initiated what's now called the space-time theories approach. Broadly speaking, space-time theories are presented within the model theoretic framework. Now, the so-called semantic view of theories. Pat is widely cited as an originator, if not the fons et origo of this view. But I think he will exclaim, as did Newton in response to the ascription of a belief in action at a distance, "Pray do not ascribe that notion to me." One readily sees the reason for the attribution by encompassing but generalizing upon the sense of the term model in the empirical sciences under the Tarskian conception. The term semantic view appears altogether natural. But Pat's understanding is not the semantic view, as that view is widely understood. For that idea, commonly relies either on the idea of truth-making structure or a truth-making map. In the latter case, models are not non-linguistic objects, for they invoke an interpretation function whose domain is the non-logical vocabulary of a particular language. As for truth-making structure, let's recall the fact that philosophers know, but always seem to forget, that set theoretic relations hold only between mathematical structures, not between structures in something called the world. The idea of truth-making structure in the realist sense of a correspondence has no clear meaning. Now, one productive use of the structural views of theories concerns intertheoretic relations, an issue to which Nagel devoted much attention. It's fair to say that some of the best current thinking about reduction of one theory to another, I think of Bob Batterman's work, is not in the Nagelian, but in the structural tradition pioneered by Pat. So in the Suppesian sense, a model of an empirical theory is a mathematical model, a set theoretic structure used to represent a system or kind of system and its behavior. And the theory itself is illuminatingly thought of as a collection of such representative mathematical models. To say then that a representative mathematical model realizes an empirical theory is to say that the model satisfies the description given by the theory's characteristic set theoretic predicate. It fits the description of a certain kind of mathematical structure. And I'm going to follow Pat in a recent paper of 2011 in calling this view the informal structural view, to distinguish it from the semantic view, with its often implicit reference to truth-making structures or maps. So data models. The semantic view commonly is understood to tell us what a scientific theory is. It's just a collection of its models. Pat, on the other hand, has maintained that this is not a definition, I think, but a perspective on theories more in accord with scientific practice. And he's long held that too much philosophy of science is theory talk, as it is as if science were only about theories. And his advocacy of the informal semantic view of theories should be understood in this spirit. His Models of Data paper of 1962 showed us, as Paul has recently reminded us, that if we attempt a precise analysis of the relation between a model of a theory and what Pat called the complete experimental experience, we should have to consider a whole hierarchy of models interposed between that experience and the model of the theory we're attempting to test. Well, anyway, I think Pat has shown us that we can use formal set theoretic tools to display the relations between models in this hierarchy, bringing illumination to an area of scientific methodology that Nagel characterized by a general fuzziness, the application of theory to empirical subject matter. In the past decade and a half, structural approaches to physics among philosophers of physics is a rocketing industry with almost exponential growth. Surely it's a good time to get out of the market. For what the most prolific faction of these folks claim is that physics tells us not about objects of which the world is made, but about the structure of the world in its most extreme form. The claim is that the basic ontology of the world is pure structure. Out with the objects, they're just epiphenomena. The world in and of itself is structure. One can find cosmologists at MIT with this view. This is intended not only as a radical revision of fundamental ontology, but also, in Oxford at least, a necessary component of taking quantum mechanics seriously, quote unquote, the ever or many worlds interpretation. For present purposes, the point is that the originators of the so-called structural realism claim descend from two sources. First, an observation, going back to Poincaré and Duhem, and even earlier, that experimental laws are preserved across theory change. This is needed to protect realism from the discontinuities of what Kuhn called paradigm shifts. The second source of structural realism, as they see it, particularly in its virulent ontic version, is the semantic view of theories, that theories are just structures latching on to ontological structure in the world. Pat is widely revered as their ancestor, foreshadowing their claim that everything ultimately is structure. I hope to have made clear in these brief remarks that this idolatry is misplaced, that structural realists are sacrificing their ontological calf at altogether the wrong altar. So I would just like to conclude by saying, Pat, it's been a great experience in my 9 years at Stanford to get to know you. It's been a real pleasure in my life.
Well, I want to make, I very much like your remarks and agree with them, and I want to quite second what you say about pure structuralism. I mean, I'm very much an Aristotelian. Structure, yes, but matter also. Aristotle had the story, both form and matter, and recently, in fact, in discussing, in fact, Jens-Erik Fenstad and I have been talking, things about the creation of mathematical concepts. And Wigner's, there's a well-known physicist, Wigner, who wrote a wonderful paper on the unbelievable, what is it? The surprising effectiveness or something. Unreasonable effectiveness of mathematics in the physical sciences. And this response that I wrote was to say, it's not surprising. It's the way humans have developed since the age of the cavemen. And I used as an argument there the sophisticated views of Aristotle in the De Anima. The De Anima is the famous Aristotelian treatise on what we would now call psychology. And he has a very sophisticated analysis of the place of both form and matter. And I think that's needed there. That's needed. I mean, I couldn't believe for a second it's pure structure all the way down. And I could find that quite unbelievable, and will affirm my Aristotelian heritage very much. Now, I'll make one final comment. Part of my part of this kind of religious view he gave here is to emphasize that when I was raised as a graduate student, the winds of doctrine were quite ferocious. And so it was seen both in Tarski's view, he was very firm about what was really important, what mattered and what was not. The same was true of Ernest Nagel in a very different way. So Ernest would love to criticize in our conversations, and he wrote very good skeptical reviews of one of the books of Reichenbach's on probability, a skeptical review of Carnap's book, and a similar skeptical view of Quine. So I received an education that encouraged a different form of what you might say, modern religious naturalism. That had a big impact on me.
So do these structures then supervene on the natural world, so that if the natural world were different, the structures would be different? Or are they independently existing things? In which case, how does Pat reconcile that with his empiricism?
Are you talking about the structural realist view?
No, the view that you attributed to Pat about these pure set theoretic structures. That already, suggesting that they're pure set theoretic structures, suggests there's a distinction between pure and applied mathematics. And then, but whether or not it's pure or not, the question is, are the structures eventually dependent on the physical world?
Well, of course they are. Absolutely. Yeah. I mean, and to say that there are pure structures is only to say that we use the language, as it were, of set theory to describe in a convenient, compact way what the theory is trying to tell us, as we understand and formalize the theory. That's all.
So if the natural world doesn't exhibit that structure, then the structure won't exist?
Oh, I'm sure that there's, you know, large cardinals exist, and we're not going to find those in the natural world. So, yeah.
I have a question. The language to me is a little bit foreign, so I don't always know what you mean when you use words. No, that's not criticism. It's much worse with mathematicians, incidentally, for me. How much do you think that the structures that we use to describe the natural world are functions of our own heredity, functions of our neural architecture that was created by evolution and that we simply are stuck with, and these things simply make describing the physical world, especially in contexts like quantum mechanics, relativity, and so forth, 11-dimensional string theory, God knows what, where we are simply stuck with the architecture that nature gave us, and therefore we have to approach these problems with a degree of abstraction and mathematics that we might not recognize as coming from our evolutionary architecture. That was a question, but I forgot what it was.
You're asking for my personal opinion?
Yeah.
I agree 100% with you. There's no other possible explanation.
I don't know how you can agree with a question, but
But wasn't the question how much?
well, the question was a pointed question.
Well, what's the alternative then?
Well,
There is none.
I would disagree, Rennie, with too much dependence on the neural structure. I think what the human brain is capable of is wonderful and fantastic and magical in terms of relation to the real world.
Yeah.
And by no means would I think that the way we think about these things is much constrained by the brain.
Well,
But from the neural standpoint.
well, let me give you an example. I agree with you, but let me give you an example. We can visualize 3 dimensions. I can close my eyes and I can see 3-dimensional cube or something like that. I cannot close my eyes and see a 10-dimensional cube. Some people claim to be able to see 4 dimensions. Well, maybe. But it's worse than that. Can you visualize 2 dimensions? How many people here think they can visualize 2 dimensions? I don't think so. I think when you visualize 2 dimensions, you see a 2-dimensional surface embedded in 3 dimensions. Yeah. You can't visualize a 1-dimensional space for the same reason. Your neural architecture has you stuck with it, 3 dimensions. There's nothing special about 3 dimensions mathematically.
That's the case of throwing away information, which is okay.
Okay.
The other direction is you don't throw away information, you're losing it.
My point is that the neural architecture does, to a large extent, determine what we can and what we cannot visualize. And we supplement that in order to be able to do the things you say, we supplement it with abstract mathematics. A 4-dimensional sphere is just x squared plus y squared plus z squared plus w squared plus u squared equals 1. So I think somehow missing out of a lot of this discussion is the constraints of biology. To me, I find that so. But never mind, I'm a physicist, I'm not a biologist. And we should go on to the next lecture. Thank you.
All right, I'm going to be a little bit rude in the sense that what I'm going to do is a continuing conversation with Pat that ended last June at the end of a dissertation defense with what I considered a question on the floor, and now I get to answer that question. But I'm going to spend the first few minutes trying to put the audience in a position where the question was asked and then give the answers. So the topic is indirect or derived measurement. That's measurements in which we assign values to one quantity. I'm only going to be concerned with physical quantity, by measuring something very different and using some kind of a theoretical principle or a theoretical assumption to infer the one from the other. So the examples, particularly the examples of primary concern to me as partly a historian of science, are things like using a mercury column to measure atmospheric pressure, using the length of a mercury column to measure temperature, using a particular spike on a particular kind of seismometer to measure the magnitude of earthquakes in the Richter scale. And the question that I put a good deal of time into in the last few years is, under what circumstances do well-behaved results in the values for the inferred quantity give you evidence for the theoretical principle that's being presupposed in the inference? I'll wait just a minute. That this kind of evidence is important in 20th century microphysics is just so automatic that it scarcely needs to be stated. I've chosen one example from CODATA 2006. CODATA is the regularly published, I think it's about to be published again, it may be out, I don't know, committee on data that give the preferred values for the fundamental constants. In this particular case, what you're looking at in the graph is the inverse of the fine structure constant starting with the 7th significant figure. So you're plotting different data and the uncertainty in those data from the 7th significant figure forward on a series of measurements. And the quote is the only place I'm going to quote. The good agreement of the highly accurate values of the fine structure constant inferred from the ratio of H over M for cesium and also for rubidium isotope, which are only weakly dependent on QED theory, with the values inferred from the electron anomaly, Munonium transition frequencies, and the hydrogen and deuterium transition frequencies, provides support for the QED theory of the fine structure constant, as well as the bound state of munium, I'm sorry, I mispronounced that, and hydrogen and deuterium. In particular, the weighted mean, and now quoted, are two values, in one of them to 11 significant figures, the other to 12 significant figures, that are in remarkable agreement, in fact, in full agreement through the first 9 significant figures until you round the 10th from the 10th significant figure. And the remark made in the CODATA report is this is a truly impressive confirmation of QED theory. So I've been studying not just the CODATA use of converged measurements of fundamental constants, but the process that's gone on starting early in the 20th century with Perreau and has just been accumulating ever since. But my real interest in it and what got me going on it initially is not there, but in the very early stages of the history of physics, namely 17th century and Newton, which those who don't know me, that's my specialty is Newton. You all know the first 2 laws of Newton, but I'm going to talk about them in a very different way. As they're used in the Principia, they serve almost purely a means to do indirect measurement. Indirect measurement of celestial forces to which we have no direct access from changes in motion to which we do have direct access. So the first law of motion is best understood as it used in the Principia contraposed. What can you do with the first law of motion? You can infer the existence of a force. Then the second law of motion is used to quantify the magnitude of that force. The specific quantification that the second law uses, Newton explained in another place. I'm just going to state it briefly. I know those slides are hard to see. It's the mass times the limiting value of a certain distance divided by the square root of time as the time goes to 0. What's that distance? It's the distance between where the particle is or the object is and where it would have been had it continued in uniform motion in a straight line. And that limiting value, then the law asserts, is the magnitude of the force. And so you end up with a licensed inference from the limiting value of that quantity at any time to the magnitude and direction of the impressed motive force compelling the change of motion. And one of the real keys to the whole of the Principia, the revolutionary aspect of it in the history of science, is here put in italics, without any regard whatever for the mechanism producing that force. It's entirely a relation between 2 quantities, and laws are going to be formed in relations among the quantities. And I give you one quick example, quite independent of the law of gravity. Newton's able to give the effect of the sun on the moon ratio to the effect of the earth on the moon to 5 significant figures purely from kinematic considerations. Now, there are philosophers, I don't think it's Pat, but there are philosophers, I should have gone back and looked at your axiomatizations, so I apologize for not doing them. But there are philosophers who take the first two laws, actually the first three laws, as being implicit definitions of what the word force meant. And therefore, there is no issue of evidence about the laws of motion because they're defining what forces are. And if they're defining what forces are, there's not an issue. That's historically totally mistaken. Newton makes absolutely clear he's talking about everyday static forces. Forces that have been around from Archimedes forward. So there's a very strong empirical claim here, a claim relating certain changes of motion to the forces of statics and static equilibrium that have been around for generations. Looking now at the statics, the standard way, these by the way are three figures cleaned up from sketches of Christian Huygens, chosen intentionally for reasons you'll see in a moment. So the standard way of measuring one particular kind of static force, namely the tension in a string, is by the weight hanging on that string vertically when vertical, or as, depending on the circumstances, that weight times the tendency to descend. And as the second figure shows you, if you put a weight on an inclined plane and balance it by a vertical weight on the other side, the vertical weight is significantly less, sine of the angle, times the weight of the one on the plane, because the tendency to descend on the plane is much less than vertically. So the whole idea, it's all over the place. Mersen's book on musical instruments does, of course, tension in musical strings. It's all done by weights. We still do it by weight very often, I think, when we do tuning. The interesting case, though, is the one at the bottom, which is a figure by Huygens in which he's doing two things. He's asking what the static situation is when you take something that's hanging vertically and lift it to an angle by pulling it sideways. And the question is, how much tension do you have to have in the string pulling it sideways for any given angle? Okay, he's also, in this, you can see, those who can see it, the pulley at the top, he's also asking what's the tension, resulting tension in the string, showing that it is the familiar vector, what we would call the vector sum of the two tensions, but that's not the one I'm interested in. What I want to stress, and all of these results that Huygens has presented are totally standard. He knew of them from the work of Stephan, his countryman, who died before Huygens was born. They're called Stephan's triangle. These are just straightforward applications of Stephan's triangle. The actual result says the following: in order to get any in static equilibrium, any string to move vertically to any fixed angle, the tension has to be the vertical tension in the string times the tangent of that angle. And that's just a nice, well-established consequence of Stephan. Okay, now there's a problem. Newton's talking about static forces and in motion. And the cases I just gave you of static equilibrium, there is no motion. So there's no relation between those as such and motion at all. And so the question of evidence can't be addressed unless there is indeed some case where static forces are in equilibrium, yet motion is involved. And that case was developed in 1659 by Christian Huygens when he developed what he called, he dubbed the word, it's his word, centrifugal force, by which he meant the centrifugal tension in a string required to keep an object in uniform circular motion. And you may not be able to see it, but his derivation is exactly using what subsequently became Newton's first two laws. That is, he's using the limit value of a displacement divided by time squared, taking that limit and discovering it comes out 4 pi squared times the radius of the string holding it divided by the period squared. So what he has done is not only to take a case of static equilibrium with the string, but he's taken that limiting value and turned it into something we can measure without having to worry about infinitesimals, namely the radius, the length of the string, and the period, both of which are comparatively easy to measure. So here was the vehicle that Newton knew totally well, the vehicle by which Newton could address the question, what's the evidence for his first two laws as assertions about relations between motion and static forces. And what Huygens proceeded to do with this particular result, first in 1659, then actually publishing fully in 1673, and now you can see these are two earlier slides that have been presented twice here before with Pat in the audience, and Pat giving me enormous encouragement to continue my work on both occasions. What Huygens did was to take this principle of centrifugal force, the tension in the string, and design a clock that happens to be a paraboloidal conical pendulum clock. The trick is to keep the center of the bob always on a paraboloid. If so, the period remains exactly the same no matter where the bob is on the period. It's a wonderful consequence of Newton's first two laws. He took that and built a clock, and with it measured the tendency to descend vertically. Specifically 15 Paris feet, 1.1 inches, that's half RG. So he's measuring surface gravity with an indirect measurement, presupposing what subsequently became Newton's two laws, and he's doing so to four significant figures, publishing it in 1673 with the details shown. And what he's done is take from Newton's, what we subsequently came to know as Newton's laws, he got a relationship between the strength of surface gravity, the lattice rectum of the paraboloid, and the period, and from those he deduced four significant figures, the value of G. He had actually done the same thing earlier in 1659, but didn't publish. By the way, where he published Horologium Oscillatorium, it's a fantastic book. It's the book Newton modeled the Principia. So it's quite significant to Newton. He had done it earlier in a rather clever way that he didn't describe very much. He gave the value. It's exactly the same value as the 15 Paris feet, 1.1 inches, Paris inches. The problem here is a conical pendulum that has to be kept at constant height. And so you need some sort of a servo mechanism to do it. Huygens has the clever mechanism of having a heavy chain hanging on the end of the string, and as the bob slows down from resistance effects, the weight pulls the string down, changing the tension and maintaining the constant height. You get the same result both ways. Both ways presuppose Newton's first two laws of motion. Newton himself tried to do the second measurement, wasn't clever enough to come up with a servo mechanism. He was less an engineer than Huygens, more of a mathematician and physicist than Huygens. But he managed to get within 1% of Huygens' known value, and then sort of abandoned it, struggling to maintain constant height. Okay, so what is this as evidence for Newton's first two laws? Well, what we end up with is two relations. One relation at the top, coming off of conical pendulum measurements of Huygens, that gives this limiting value of displacement over time squared as a constant times the tangent of the angle, where the constant is done two different ways, 2 pi squared times the height of the pendulum divided by period squared, or pi squared times the lattice rectum of the pendulum divided by period squared. On the other hand, statics has a totally parallel relation. The vertical tension is related to the tension necessary to maintain an angle, exactly by the same amount tangent of theta. So what we have here is two totally analogous formulas that correlate. Okay. Is that the only source of evidence? No. What's interesting, and this is the real evidence for Newton's first two laws of motion at the time he published them, Huygens had an independent way of measuring the strength of surface gravity, totally independent of Newton's first two laws of motion. It's using a cycloidal or small arc circular pendulum. It presupposes Galilean gravity, uniform acceleration, and it presupposes pathwise independence. But it does not presuppose either of Newton's first two laws. It had already become, by the time of Newton's Principia, the standard way of measuring gravity to such an extent that they were determining changes in the third and fourth significant figure from between Paris and the equator. So Huygens had provided an independent way of measuring the vertical tension, which then from the formula, the second formula down there, gives you the tension BK and the vertical tension. He had the numbers coming off of his conical pendulum measurements are exactly the same numbers once you multiply by mass. And therefore, you could simply say, this is a direct measure of static forces, thanks to having the two independent ways of measuring the same thing. I'm almost to Pat's question now, not quite finished. So the striking thing here is what we've come to is an example in the 17th century of the same sort of thing we saw in the QED case. Converging measurements of exactly the same quantity using entirely different theoretical principles in the indirect measurements can be played off against one another to bring very powerful evidence. And that's interesting and well worth studying, but that's not my topic for the moment. It's a topic I am working on. During a PhD oral last summer, the candidate, now Dr. Teru Mayaki, made an offhand remark, not terribly tied to his content of his dissertation, but certainly pertinent, that if all you have is an indirect measurement, a theory-mediated measurement, and the measurement is well behaved, that's automatically evidence for the theoretical principles involved, even if there's no other evidence for those theoretical principles whatsoever. Now, Pat is much too gracious to have jumped in and started challenging Dr. Mayaki in the middle of a doctoral dissertation defense. But what he did, he was sitting opposite me, and his eyes rolled to the ceiling, his eyebrows raised, and he started smiling. And I thought, is he going to challenge? But as I say, too gracious to challenge, but it was very clear he wanted to question that remark. So I'm taking that as your question that we didn't have a chance to discuss afterwards, and I'm going to answer it. I'm going to answer it for the specific case of Newton, because it's convenient for me to do so, having set it up. So what evidence, if any, would the well-behaved results from the conical pendulum measurements of gravity have provided for Newton's first two laws as of 1687 if there had been no other way to measure gravity? Then it's an open question just whether those conical pendulum measurements are measuring the hanging of an object vertically. So let me look at for two cases consecutively. Let's just drop out the simple pendulum measurement and look pure and simple at this correlation. Fine, we have the correlation, and that, I think Patrick would agree, is automatically enough to use the one to assign numbers, values to the other. But in doing so, all we have is a correlation, and that raises questions. Questions are about, could systematic errors in the measurement of one of those things be affecting the value in the other? Because they are not identically the same thing. They are two physically different quantities that are simply related by a correlation. And that's the kind of question Newton himself not only asked, he explored it at great length for the simple pendulum measurements, to concluding that Huygens' measurement required several corrections and had an upper bound on its limiting accuracy beyond the fourth significant figure. So that's a partial answer to Pat. Yes, there is evidence. Now let's take away the correlation. Say we didn't have a well-developed science of statics at all, and all we had were those conical pendulum measurements. Even that, and this was Mayaki's point at the time, even that is some sort of evidence for the laws of motion because they've just been tested. There's a consequence from them that a particular quantity in a conical pendulum properly constituted was going to be invariant. And it had proved to be invariant in two different configurations. If it had not been invariant, that would have been serious reason to question the two laws. But notice in this case, we have not even a correlation to work with. So all we're really able to say is prima facie evidence that what we're measuring here and calling force is the same as static force. And it then becomes a natural open question to ask, is what we're measuring really the same thing as a static force? Just the fact that a string is involved in the conical pendulum doesn't guarantee that's the case. To give you the analog of that, is the Richter scale using a particular spike on a particular kind of seismometer really measuring the magnitude of earthquakes? And of course now, as we've learned since 1970, the answer is no. And that was the potential right here. The answer could have turned out no. So to conclude, Newton's Principia, he says at the very beginning, is an essay in a new way of developing evidence. The very first sentence on it, in the whole book, however, mentions measurement. And the more you know the book, the more you see that his whole new way of developing evidence turns on the well-behavedness of indirect measurements, time after time, quantity after quantity, all through the book. I started looking at the Principia in 1987, 25 years ago, and had the good fortune of already being very sensitized to issues about measurement. I had read the one volume that had appeared at the time of Foundations of Measurement while a graduate student sitting in a course by Frank Fisher on econometrics, and he recommended that book to me. And the last part of it is actually on derived measurements and measurements in physics, and it had a huge influence on me when I started reading the Principia, and probably did more than anything other than Maxwell's comments on the Principia to sensitize me to what's going on in the book. By pure chance, Pat was the last of these four authors I met face-to-face, that in 2007. But of the four of them, including Dave Krantz, with whom I was an undergraduate, Pat has been the one I've had by far the most discussions with. And I value those discussions over the last 5 years enormously. It's my chance today to express gratitude for that, because no one has encouraged me more with looking at measurement as evidence than Pat has. Happy birthday, Pat.
We just about made it.
Yes.
Time for drinks.
Thank the speakers. Pat, you're
No.
You're not going to give me a rejoinder in front of everyone.
No.
Could I? I like that.
Okay. If there are no questions, we're off to refreshments.
There's a question.
Here's a question.
Question.
For the session, you opened the session by saying that physics is going to radically, severely radically maybe, change over the next 10 years. Could you just give us an idea of what's going to happen?
Well, what I was thinking about was certainly physics is going to change. Physics always changes, but there are changes taking place which are not not caused by physicists, caused by nature itself, but of changing the way physics is going to be done. Namely, the fact that it is so terribly hard to get experimental evidence. What used to be a 2-year, 3-year operation to do an experiment is now the better time of a scientific lifetime. It's getting harder and harder and harder. We're probably very much reaching or about to reach within the next generation the limits of our ability to build accelerators and do microphysics. We are almost certainly, not almost certainly, we are almost certainly reaching the limits of our ability to see large distances in the sky. These are fundamental issues. These are not practical issues. They are really going to cut down the ability to have a flow of experimental data into those areas where we've learned to ask questions. We've learned to ask questions, and the questions seem like sensible questions, but they also seem like questions which are beyond the range of experiment. And that's very disconcerting. That's, I said, it might delight you and it might appall you. I'm very interested to see what philosophers of science will make out of this and how not just philosophers of science, but how science will be done in an era where experimental input into those areas, not every area, there's going to be plenty of areas of physics which is going to have data, but those areas, cosmology, elementary particle physics, how do we do physics when it becomes so top-heavy with theory?
Can I make a quick remark about that? The situation in which Newton started was one, I can almost quote Kepler on it, as far as the physics of what's going on out there, that will forever be a matter of conjecture.
Yes, that's right. Good, well said. Well said.
Let me start with a couple of personal remarks about Pat. We met, I think, for the first time in about 1955, and it was not the greatest meeting. One of the consequences of that meeting was that the little book, Individual Choice Behavior, came out with a bright red cover because it got to be called the Red Menace. But there's a story behind it, but I won't go into the details. Then at that point, we got very interested in measurement issues, and when Bushweiler and I did the Handbook of Mathematical Psychology, we got Pat to do the first chapter on basic measurement theory, and then Pat and I later, I think it was volume 3, did a chapter on utility with respect to probability. I probably shouldn't waste any time talking more about that. I'll get down to my talk, which is there. Hölder's theorem was developed in 1901 as a formalization of extensive measurement in physical sciences. And it stemmed from work that Helmholtz and others had done, but Hölder was a mathematician and he really formalized it. And he showed that if you had certain axioms, which I won't detail, and you mapped into the additive reals, the structure had a representation that was simply additive. And that theorem is very well known and has been used fairly extensively. But he also basically had to consider multiplicative conjoint representation, which was concerned that mass was volume and times density. So you had, in addition to addition running around, you had multiplication. So you could ask the question, why did he map just into the additive reals? Why not into the full reals? And I think people presumed the answer was that there wouldn't be any difference. The truth of the matter is there is a difference. And you get this particular equation where you have the additive term, but then you have a multiplicative term with a constant that's either -1, +1, or 0. Now, in the physical case, he had distribution conditions that, let me say, we call this representation P additive, meaning P for polynomial, because it had been shown in the functional equation literature that the only polynomial that you could map into the additive representation was this particular polynomial. And the distribution laws that existed in the case of mass between extensive structure and the conjoint structure to make them come out with the same mass measurement. Those laws ruled out anything except the delta equals 0 case. So for physics, the oversight meant nothing. I will argue that for psychology, this was quite important, this oversight. And that's what I want to try to describe to you briefly. I developed a theory in the Psych Review in 2004 about basically the binary receptors, such as the eyes, the ears, the arms, independent organs that work as a team in some sense. And the theory then concerns really coding how this binary structure works. And the trick that I used was to say, okay, you put intensity X in, say, in the left ear, and intensity U in the right ear, and then you match that to a Z where you put the same intensity in both ears, and define the operation X circle plus U equals Z. And then you really then try to axiomatize the structure so you find out how circle plus works. The second kind of primitive in this work it is you get the experimenter to present a signal and a number and ask the respondent to say, well, and there's also a reference signal that I call rho, which is either experimentally given or is generated by the respondent. And you could think of this as an operator where the respondent is producing Y as the signal that has the subjective impression that the interval from rho to Y is P times the signal from subjective intensity from rho to X. This is, if you take set rho equals 0, this is SS Stephan's method of magnitude production. It's a generalization of that. Then you have to worry about linking the two operations you have running around, and I formulated some axioms about that. And there are two linking properties, in some sense, are pretty analogous to the distribution properties of physics. And this means that we have a psychophysical function for both the matching and for the production. And this led to the representation that's shown here, where you have the P additive 1 over the circle plus. You have constraint on circle plus, it's in the middle equation. And then you have the weighting function on the number P, such that the subjective differences, the ratio of the subjective differences is constrained by WP. And that was the representation I arrived at. And I thought I had shown in the 2004 paper that the delta had to be 0. And that turned out to be wrong. I made a mistake. And that was pointed out to me by CTMG, and I'll come back to that in a minute. Working with Ragnar Stein-Grimson, we did a series of experiments in loudness, supporting the various axioms of the theory, and he has been working in vision, both in brightness and perceived contrast, with very good support for these axioms. By the way, unlike most psychologists, we focus entirely on individual respondents. There are enough individual differences running around in this work that this averaging that is commonly done is nonsense. And I wish psychologists would get this through their head, that they simply are dealing with people who differ in various ways, parametrically and functionally. And the averaging over subjects is just a terrible, terrible mistake. We were able to show a behavioral invariance that I will bother to state that led to a power function, the sort of thing that Smitty-Stevens was pressing for a quarter of a century or more. Stevens felt that this power function representation applied to all so-called prophetic dimensions, the subjective intensity dimensions. I'm going to be arguing in a second that's not quite true. And one of the things that you find if you look back on that literature, one is that it was average subjects, and another is you draw a nice smooth curve through a set of data points, and you kind of convince a person that there's one form rather than another, and that sometimes can be misleading. Some familiar properties of operators we looked at. Commutativity was one, and we rejected that for all the binary domains we've looked at. We have not looked at weightlifting, so presumably that would be. Associativity we haven't looked at, and we'll see in a minute why not. And the last property is bisymmetry, which is this one here, and essentially says you can interchange the inner ones and it doesn't affect the perception. And we've sustained that in all the things we've looked at. Now, it turns out that you can prove the following, it's in the site review in press, that with delta equals 0, of course, bisymmetry is satisfied. For delta not equal to 0, bisymmetry is satisfied if and only if commutativity is satisfied. But the data are saying yes to bisymmetry and no to commutativity. So that strongly suggests that you have to conclude delta equals 0. And that corrected that claim of mine that G pointed out. And in this context, if bisymmetry holds, associativity cannot hold. So we haven't run the associativity experiment, but I kind of think it's a foregone conclusion what would happen. Now, many subjective intensity senses are not binary, they're unit. And I'm thinking of things like money, odor, taste, warmth, cold. There are just a lot of these things that are not like eyes and ears. And and let's assume that we're dealing with senses where there is a binary physical concatenation operation. And I'll call that concatenation circle dot. And again, we can have magnitude production just as before. I won't repeat that. And unlike the binary case, the circle plus operation does in fact satisfy bisymmetry, commutativity, associativity. And I know of no principal argument that forces the delta equals 0 case, which is very different than the binary kind of attributes where it was forced. Now, in the case that the delta is not equal to 0, then you can rewrite the p additivity as this product relationship. And there are two interesting and obvious things once you write it in that form. One is if you take the logarithm of it, it's an additive representation. Second, since you're working with 1 plus a delta, which is a 1 or minus 1, this has to be an absolute scale. Everything else is in ratio scales. This is an absolute scale. And we haven't had a lot of experience with these absolute scales in the behavioral sciences, so there's a great deal of work here to be done. I can show that the form of the representation phi has to be these three types, depending on what delta is. So the the not equal to 0 cases are either exponential or negative exponential. And there is a criterion that I've given to decide whether you're dealing with which value of delta. So I know how to perform experiments to verify that. Now, the literature that I mentioned of Stephen's and his various other psychophysicists in the early part of the mid part of the 20th century was that you're getting power functions, and here I'm predicting non-power functions, and one of the things that I'm predicting, and I'll get to in a second, okay, you can do all sorts of cross-modal matches between different attributes. In Stephen's world, all those cross-modal matches would be power functions with the exponents predicted from the individual power functions. Here, however, it's more complicated by a good bit. And in fact, if you look at them systematically, you get a complicated chart. Stephen's part of it is this stuff in here, all powers. But all of this kind of thing is now predicted to occur. Nobody has yet done those experiments in the detail that needs to be done and for individuals. You clearly don't want to be averaging this and this. And so there's a kind of huge experimental program to look at these dimensions that haven't ever been really very carefully studied except for money. That's the one that seems to have received the most attention from me because the economists are interested. 2 minutes, yeah. I suspect that further research is going to confirm that for dimensions like shock and pain and vibration, you're going to have the delta not equal to 0 cases. We'll see whether this is true when people start working at it systematically. The utility of money is in a way unusual because it can go both positive and negative. And it appears that in these cases, the three possibilities are people who are risk-seeking, risk-neutral, and risk-averse. And again, there's been a lot of speculation in the literature about these concepts, but they fall out pretty naturally. So, in summary, the overlooked solutions for Holder's theorem didn't matter for physics, but they do matter for the behavioral sciences, particularly for the non-binary senses, which are the ones that have been least studied, and there just needs to be a lot of experimentation carried out. And again, as I emphasized, on individual subjects. These are just, you just can't average people who have such different functions. Doesn't make any sense. Okay, I want to make one little point about the celebration that we're at. It's in celebration of Pat's 90th birthday. That doesn't happen to be this weekend. That comes next weekend, Saturday, on St. Patrick's Day. So happy birthday, Patrick.
I have a question, if I may. Duncan, you here at least, you have not been treating the additional case, and I wonder whether you have thought about it. In my 1965 measurements of binocular brightness, you get an attenuation of the other eye if you put the contour in this eye, right? Now I wonder whether that is also happening for loudness. So for instance, what if in one ear you give a slightly vibrating loudness and combine it with another, do you get attenuation of the same kind? And if you get it, how do you handle that mathematically?
Well, the theory does not encompass that, obviously. And I don't know whether you get it. We have not done the experiments to look at it.
Yeah. Okay, so forthcoming maybe, hopefully.
Well, let me, you reminded me something. I'll make a light remark, Duncan, but historically interesting. Duncan's adversions about averaging remind me of a famous conversation I had, must be now at least 50 years ago, with B.F. Skinner. Many of you know Skinner now as a famous early behaviorist. And probably his best student was somebody I worked with that I know well and that Duncan knew well, and many of you know, was Bill Estes. And in this conversation, Skinner said, I have great respect for Bill Estes, but he's really moving in the wrong direction in all of his current work. He is not concerned with studying just the individual, but averaging across individuals. And that's a dreadful mistake in terms of the research. And I thought Duncan would resonate. Not that he was, nor am I, neither one of us will be an uninhibited admirer of Skinner. Skinner had virtues, but he also had faults that are rather obvious.
He didn't like formal theory.
He didn't like formal theory, right. But I thought I couldn't resist that remark of so long ago, and that one respect in which they occurred. I do want to say one other remark about Duncan. I mean, Duncan, of course, and I have worked over many years. I want to make two remarks. The first one he remarked, he was nice to me. He had this famous red book for the individual choice behavior. And I thought that his formulation of the axioms were mistaken in relation to conditional probability. And of course, I got very vigorous in my arguments about that. And we argued long enough till I was finally persuaded Duncan was right. And I still remember that very distinctly. And the second thing is, what?
A rare event.
Well, no, I make many mistakes. The second thing is that I think of all the people working in measurement, including myself in this remark certainly, Duncan is the one who has sustained and continued this tradition, as remarking on his current work and just in the last few years, exactly in this continuing psychophysics tradition. And he's really, and one would like to say he exemplifies the virtues of S.S. Stevens, who many of you don't know, but was a famous psychologist in this direction, but he's actually much better than Stevens. And is doing beautiful work now.
The thought experiments, the meaningfulness with application to the Pythagorean theorem. Sounds like a philosophy.
He's a psychophysicist.
Some time. You know, this is my abstract and an overview, and you have read it already 3 times, so we're way ahead. So what do I mean by a thought experiment in this context? I mean an abstract constraint which is represented by a property or an equation whose validity can be assessed without experimentation. Well, that's a bit vague. So let's go to an example. Take a function g, defined on the Cartesian product of 2 intervals, and whose range is actually one of these intervals, the first one. And the interpretation is that the second variable, r, let's see, here, is affecting the first, in the sense that the y here is the current state of the system, and then r comes along, change it, and then the result is the function. Now, because the first interval, j here, is the same as the interval of the range, we can iterate the function. So we can compute a g of g, y, r, t. Why is that relevant? Because in a case in which your thought experiment tells you that the order doesn't matter, then you can compute that and you can actually formalize it. For example, imagine that the R here is adding 15 grams of a substance to a solution, and that Y is the current heat. And then the T is adding another 30 grams. You may think that in some situation, whether you add 15 grams first and then 30, or the other way around, it doesn't matter. Of course, it may matter. The thing could explode, but your thought experiment tells you that it won't. And so what that does for you is give you this equation, which in the functional equation literature is called the permutability equation. So the permutability equation, I claim, is an example of something that you can get just by thinking about the phenomena. Another equation to keep in mind is one which resembles permutability, except that you have 2 functions. And that's called quasi-permutability. The function m is called quasi-permutability if there exists a function trace such that, etc. Why is that useful? Because under fairly general condition, monotonicity, continuity, you can prove that if permutability holds, then there exist 2 functions, f and g, such that this representation is satisfied. I'll give you the precise result in a moment. And our result is a generalization of a very old result of Hosszú, 3 articles in Hungarian, which I don't claim to have read, but they are summarized in Axel's book. Now, when I say that I'm going to give you a generalization of that, well, in a sense it's true, because I have proved it. It's a generalization, but with the collection of functional equation wizard that you have, in the University of Debrecen, you never know. So maybe one of them, at some point, published the same thing. Anyway, I'll tell you what it is precisely. Now, so we get this from your thought experiment, but you can't. I mean, this is not a scientific law. This involves a 2 unknown function. Let's see. What more can you do? Well, what we're going to do at this time is introducing meaningfulness. So let me tell you what meaningfulness is in this case. Okay, so many, by the way, don't forget to read this. You know, I'm using Beamer. I'm using Beamer, and I'm told that sometimes people don't look at the top here, but you know, this is a nice title, right? So don't forget to read it. So it turns out that many scientific laws or geometric laws satisfy permutability, and I'm going to give you a collection of examples. The Lorentz-Fitzgerald contraction satisfies permutability because when you apply it, you get a product and you can commute. So the Beer's law also, monomial laws in science and geometry also satisfy permutability or quasi-permutability. Here is the volume of a cylinder. You can compute it, you get permutability. And the Pythagorean theorem. If you go to the computation, you see that you can the P of xy is the hypotenuse, and P of xyz is another hypotenuse, and you see that you can develop it and commute. Now, here we get permutability by computation, but I claim that permutability was something that you could get from a thought experiment. So the question is, do you get permutability in the case of the Pythagorean theorem just by thinking about it and some very elementary geometry? The answer is yes, right? So let's, I've been making claims, for example, the claim that permutability implies this representation, etc., etc. So let me tell you what the exact theorem is. I introduce first a definition of what's a numerical code. That's convenient. It's a function m defined on a Cartesian product with domain is an interval, Cartesian product of interval. It's strictly increasing, strictly monotonic and continuous. It's solvable. It satisfies actually two solvability conditions, one for each dimension. The first one is the strong one. If you have a point greater than a given value of the function, you can change the second variable and get an equality with p. That's the first. The second one is weaker. There exists a point in the first interval, which is such that for any p in the domain, you can change, you can find a value in the second interval, so that we bring it in the second interval, such that you have an equality. Solvability, again, these two conditions, solvability, are conditions that you have to assume. You think about the phenomena, they seem reasonable. You can actually test that. They are not empirical, right? So they're still part of what we can infer by thinking. And this is a precise definition of quasi-permutability, right? That's the same function as we had, the same equation that we had before. And here is the theorem. See, don't forget at the top, we read this theorem, right? So a solvable code is quasi-permutability if there exist three continuous functions so that you have this representation. That's the first part. That's for quasi-permutability. You see that in the case of quasi-permutability, you have three functions. If it's permutable, you have two functions. If it's symmetric, in addition, which is also a property that you can infer by thinking, then you have only one function, and you have this representation. I have a sketch of a proof, but let's see. Should I split? I skip the proof. Okay, proof, etc. All right. Here is where meaningfulness comes about. The trouble with scientific notation, as we use them, is that they are ambiguous. If you take the Lorentz-Fitzgerald contraction, for example, what L of 73, what the meaning is empirically is not clear, except if you tell in parentheses that the units are this and this. And of course that's conventional and that's practical. On the other hand, if you want to take advantage of that invariance, that's no good. You have to change your language. So what I'm proposing is to take L of LV for the Lorentz Fitzgerald translation as a shorthand notation for L11 LV, where the 11 referred to particular anchor unit that you decide to adopt arbitrarily. And then what you do is when you change unit, you indicate that by different variable. Okay, but it turns out that in the case of the Lorentz Fitzgerald contraction, L alpha beta of alpha L beta V gives you exactly the same information as L11 LV. And the proof is completely elementary. You get 1 over alpha is here, and you can show that it's equal to that. And of course, it leads you to this equation, which is an invariance equation. Now, if you generalize that, you get a definition of what a meaningful collection of code is, which is represented by this equation here. So you change the units on both sides. You multiply by the reciprocal of the first unit on both sides, and they have to be equal. Now, in the special case in which, remember, the first interval is the same as the range, we call the family self-transforming. And here is the result. Suppose that G is meaningful in the sense that I just defined. Suppose that one of these codes is solvable and permutable with respect to the initial code G. Moreover, suppose that that particular code is symmetric, strictly increasing in both variable and differentiable with continuous non-vanishing derivatives. Then you have to have this representation, which is your Pythagorean theorem up to an exponent. Now, the differentiability assumption, again, if one of the functional equation wizard was here, he would tell me, oh, I can bypass that, you don't need differentiability. I agree. It makes my proof easy. Okay, and this is the proof, I skip it. And this is for you. You see, this is one hypothesis of a right triangle. This is another hypothesis of a right triangle. A simple argument tells you that they have to be coplanar, and in fact that they have to be the diagonal of a rectangle, so they have to be equal. And in the case of quasi-permutability, what the beauty is that your quasi-permutability creates a similar figure. And that's also easy to do. Thank you very much. And by the way, the idea of applying these ideas to geometry was given to me by Pat a while ago.
Any questions?
Yes. Is there a connection of this? Is there any connection with dimension theory in physics?
Okay, I have some kind of answer to that. The trouble, as I see it, with dimensional analysis is that the invariance is hidden in the notation. So you can't get that much juice out of it. What I'm trying to do here is to make, by the way, let's start with, that was indicated in one of those things that you didn't read, right? That the first idea of meaningfulness formalized that way came in some work with Luce quite a while ago. Anyway, what we try to do is to make the invariance explicit by introducing the unit in the equation. And by the way, I'm not suggesting that we should change the notation of signs, but we may just change them, whenever we need to get some juice out of it, and we get back to the usual notation when this is done.
Any other question? Very nice. I like that very much.
Okay, slightly different title. Finding a signal with two kinds of trial and error. This is an exercise in low rationality game theory. Very low, actually. And I thought it would be appropriate for Pat's birthday. Why low rationality game theory? Okay. Appropriate because of pioneering work in 1960, Suppes and Atkinson, who applied learning models for games, right? A book that was 20 or 30 years before its time. Now, low rationality game theory is a research area that has a lot going on. But this was where it started. Okay, I'm going to talk about two kinds of trial and error learning. The first is reinforcement learning of the Herrnstein-Roth-Erev kind. And it goes like this. There's a repeated choice situation. On any trial, the probability of a specific choice is proportional to the accumulated rewards from that choice in the past. This is the second kind of trial and error learning that I call probe and adjust. Repeated choice situation. Most of the time an agent just keeps doing the same thing, but once in a while probes, that is, does something at random. If the probe gets a higher payoff than the agent got the last time, she switches to the new action. If it's a lower payoff, she switches back. If it's a tie, she flips a coin. Okay? Doesn't have to be fair, could be biased, as long as it gives positive probability to each alternative. Okay, these are rather different types of trial and error learning. Poles apart, they're not good for all of the same things. Some are better at some tasks than others. They have different mathematical properties, so they make a nice contrast. I'm going to apply them to signaling games as introduced by David Lewis in convention. Signaling games for our purposes today will have this structure. Nature chooses a situation with uniform probability from some set of situations, or sometimes are called states of nature, S1 through Sn. A sender observes the situation, chooses a signal from some set of signals T1 through Tm. The receiver observes the signals and guesses the situation from the original states. And a slight generalization of David Lewis, because he concentrated on the case where n equals m, but we'd like to look at the more general case. Of course, we could generalize this much more in interesting ways, but not today. Both players have common interest. They're paid 1 if the act matches the situation, 0 otherwise. Now we have two kinds of trial and error, and you could, if you were treating this as a game, simply apply trial and error learning to strategies in the game. So a strategy for a sender tells the sender what to do in each situation. A strategy for a receiver tells the receiver what to do for each signal received. But that really requires that the agents think of the whole business as a game and have a strategy for the game. And that's contrary to the spirit of low rationality game theory. So instead of applying trial and error to the strategies, we'll apply them to the acts. So for each situation the sender can observe, there will be a trial and error learning process. For each signal that the receiver can observe, there'll be a trial and error learning process. And these will all be interacting with one another. Okay. Let me start with reinforcement learning of the type that I talked about. In the simplest signaling game, two states or two situations, two signals. We can visualize this as an earned process. So the sender has an earned for each state. The receiver has an earned for each signal. We'll have to start it out somehow. So we can start out the earns with one ball of each kind. Right? So the A ball and the B ball are for signal A and signal B. The one ball and the two ball, of course, are for the states. And we'll then run the process with reinforcement. It's inessential that we start with one ball of each type in each of these urns, as long as we start with a positive number of balls for each type. What happens is that with this setup, we have convergence to a signaling system with probability 1. By a signaling system, I mean an equilibrium in which perfect information transfer takes place. That is, in the limit you have the sender mapping each state onto one signal with probability 1, the receiver mapping each signal to a guess with probability 1. The guesses are always right. If you start out with equal number of balls of each type in the urn, then you can get with equal probability to each signaling system. But if you start out with unequal numbers of balls, you still with probability 1 get to such a signaling system. So learn to signal with probability 1. How about probe and adjust applied to this game? Now, probe and adjust works by probing, but you have to remember what you got the last time. So the sender has to remember for each situation that he can be confronted with what he got the last time when he was confronted with that situation and what he did. And likewise for the receiver for each signal. So the whole system has to remember a map from situations to signals and a map from signals to guesses. This looks like a strategy, but this is a memory snapshot of the system of what the sender and the receiver have to remember. Okay, so if you hit situation 3 in a long string, you still have to remember what you did when last time you were confronted with situation 1 and what you got when you did that act. Okay. I'll assume that probes are relatively rare and then cheat a little bit. That is, I'll assume that neither sender or receiver probes and adjusts at the same time. This assumption can be taken away a little bit later, but for what I'm going to say here, it'll be convenient. So think of the process as nature just selects someone to probe and adjust at a given time. Well then, again, agents learn to signal in the appropriate sense with probability 1. There's an embedded Markov chain. If you look at the pre-probe and post-adjust states, right, and look at the transitions, those transitions are Markov chains. And the signaling systems are the unique absorbing states of this Markov chain. And it's easy to show that there's a positive probability path from any state to a signaling system. Actually, in this game, it only takes 2 probe adjusts to get from any place to a signaling system. So we learn to signal, in this sense, with probability 1, although we don't stick at signaling without any deviations because they're always ongoing probes, right? Rare ongoing probes. How did that happen? All right. If you're willing to talk about stochastic stability, that is, what happens as you let the probes become less and less frequent to take the limit, okay? Then we can lift the restriction that that you don't have subsequent or simultaneous probes, and you get the result that signaling systems are the only things that have positive probability in the limit as the probes become less and less frequent. Well, that's the simplest signaling game: 2 states, 2 signals. So we'd like to know how these results generalize. Reinforcement learning now for n situations and m signals has been largely analyzed by Yaeli Hu and Pierre Torres. So we can really think about limiting results in terms of a bipartite graph. We're keeping track of the probabilities that signals are sent in situations. We've got these probabilities. We'll just consider graphs where these probabilities are non-zero. So if in a situation a signal is sent with non-zero probability, the signal will have an edge that goes to that. And there's a key property that we need to state the results about these. Property P, each connected component of the graph has just one situation, or a state called state here, or just one signal, okay? And each vertex has an edge, no state or signal. Each state or signal is connected to something. So here's an example of a signaling system. Our situations are at the top, our signals are at the bottom. Each situation maps onto a unique signal. And of course, you might wonder about the receiver, but the fact that the receiver is reinforced just when the sender does allows the business to collapse so that we can talk about just this. So that's a signaling system. But here's something else that satisfies property P. This exemplifies synonyms and bottlenecks. So you see the third situation over maps onto 2 signals, right? And just onto those. So those can be thought of as synonyms for that situation. And the 4th and 5th situations map onto 1 signal. So it's ambiguous between them. So we call that a bottleneck, right? So that's an information bottleneck. You might have bottlenecks imposed artificially if you don't have enough signals, right? But here, this bottleneck is just part of this equilibrium. Okay. Theorem. If a graph has property P, then reinforcement learning converges to it with positive probability. So signaling systems, synonyms, and bottlenecks all have positive probability in the general case, right? If in fact the game allows them. Although no information transfer doesn't, right? And if you go back to the 2x2x2 game, you can see that no information transfer would violate condition P. Okay, that's the story for reinforcement learning. Probe and adjust, we have to talk about 3 different cases. One in which m equals n, one in which m is greater than n, one in which m is less than n. Okay? If m equals n, the story is just like the simplest case. There are signaling systems. They're the unique absorbing states. There's a positive probability path to every signaling system. If there are too many signals, or an excess of signals, then things are a little different. There are no absorbing states, but there are absorbing sets, right? And these absorbing sets are very nice because they're efficient. That is, the information gets across and the receiver always guesses correctly if you're in this absorbing set. So you still learn to signal with probability 1. Here's a little example of one of those absorbing sets. In a simple situation where we have 3 signals but only 2 situations, and probe and adjust can lead from A to B, and it can lead from B to A, but it can't lead out of this set. So there are multiple absorbing sets, and they're all efficient, and there's a positive probability path from any state to an absorbing set. What if there are too few signals? Now we have to have information bottlenecks. And what we have now is a big absorbing set of efficient equilibria. Probe and adjust can move you all around this absorbing set, right? But it can't move you out of it when you get into it, right? And there's a positive probability path from any state to this set. We'll talk about that. So, in conclusion, in the simplest signaling game, both these forms of trial and error learning, quite different, lead to the same result. You always learn to signal. In all signaling games, both forms sometimes learn to signal, but probe and adjust always learns to signal. So I think this is something Pat might want to say something about. Happy birthday, Pat.
Your comments?
I'll wait. Well, the natural question that's been so much studied is whether systems are probabilistic, and you don't have the same probability 1 results. You referred a little bit to that, but not much.
Okay.
What's your comment on that? I mean,
okay.
Particularly games against nature, one thinks of not having exactly that situation.
Okay. Probe and adjust look very good in this special setup. But when in the case that you're talking about, it's not so good. In particular, suppose you have a game against nature and you have a 2-armed bandit problem. 2 arms pay off with different probability. Probe and adjust will tend to probability match. And if one arm pays off with probability 1 minus the probability of the other arm, in a special case, it probability matches exactly. Whereas this form of reinforcement learning is asymptotically optimal. So of course, if you did a signaling game where you had stochastic payoffs, things would be much more complicated, and probe and adjust wouldn't look quite so good.
All right. Many thanks for the invitation. What an honor to be here. As you all know, Pat has worked a lot in the foundations of probability, and he still does. He just recently gave a talk on this in Europe. Sometimes he does so in the guise of subjective probability theory, but whenever he does so, he keeps his distinctive measure-theoretic perspective. That is, he views of the subjective probabilities as representing an underlying qualitative structure, a qualitative probability structure. And that's the kind of methodology that I want to apply in my talk when I try to come to the rescue of the field that I come from, that is logic, in all the areas in which logic is currently under pressure from subjective probability theory. So back then, that is before PET, right, in philosophy of science, you would conceive of what a scientist holds to be true, or takes to be the most plausible hypothesis about the world, to be analyzed in terms of a deductively closed set of formulas, right, a theory in the deductive sense. In epistemology, right, we would deal with rational belief, knowledge, and of course for the ideal agent, knowledge and belief would have to be closed under logical consequence, right? And the logic we would get out of that would be epistemic logic or doxastic logic, once initiated by Professor Hintiker. In cognitive psychology, right, people would be regarded rational if their reasoning would conform to the standards of deductive logic, and so on, right? So logic everywhere. But if you look again these days, then what you find is that Bayesianism is the big thing, right? So there's Bayesian philosophy of science, and there's Bayesian epistemology, and there's Bayesian cognitive psychology, and so on and so forth, right? And sometimes this is presented in a way as if subjective probability theory was replacing logic, as if logic didn't have place anymore in these fields. But of course, this is Stanford, right? We can't let it happen. So what I suggest to do instead is, this is sort of a peace project, right? Keep the probability, but also keep something like a set of belief propositions closed under logic, right? And study both of them simultaneously. So what I will do in my talk is to look at pairs like this, a subjective probability measure, degree of belief function, a belief set. We will have the probability axioms for P, logical closure conditions for Bell, and then we'll have bridge principles by which we will make P and Bell compatible with each other. And then following some of Pet's footsteps, we will prove representation theorems for such pairs. This will give us insight in what such pairs look like, actually. And also, if we do things correctly, it will allow us to move back and forth between the probabilistic point of view and the logical point of view. And, you know, everyone will be happily living ever after. That's the idea. I will do that first for absolute belief, that is unconditional belief. And then secondly, for conditional belief, believing something on the supposition of something else. The probability component will always be the same one, standard probability theory. And the bridge principles will be to do with the Lockean thesis. And what that is, I will explain in a second. And in the first part, I'll take the right to left direction of the Lockean thesis. And in the second part, the left to right direction of the Lockean thesis. So these are two different sets of postulates that I will use. But we can prove that they amount to the very same theory. So ultimately, the upshot will be, if you look at a situation like that, there is not a lot of room to play with. There is pretty much just one theory that comes out of that. So there is robustness in what I have to present. And then at the end, I will relate that to more traditional work on qualitative probability. I won't give you a lot of references. If I had to pick one, I'd pick wonderful old volume Aspects of Inductive Logic, once edited by Jaakko Hintiker and Pet in 1966, which includes pretty much, you know, pre-runners of all what I have to say. So you find there a paper by Jaakko Hintiker on acceptance. I say belief, but it's pretty much the same thing. You find Pet's paper on probabilistic inference and total evidence. I'll return to that paper. You find another paper by Pet on Bayesian confirmation theory. So that's Bayesian philosophy of science as of 1966. You find a paper by Dana Scott on assigning probabilities to logical formulas. So that's in the same peace project between logic and probability theory, I would say. You find a paper by Ernest Adams, to which I will return, and so on. All right, now if you look at my topic from the perspective of measurement theory, then actually the situation is not uncommon. So this is Carnap at the beginning of the logical foundations of probability, where he observes that in many cases, you have a quantitative concept, and it corresponds, in a sense, to a classificatory or qualitative concept. Like temperature corresponds to the property of being warm. Right? And what I'm dealing with is like that. Believing a proposition is like a physical body being warm, right? Suppressing parameters of time and so on. And assigning a degree of belief, a number, to a proposition is like assigning a temperature, a number, to a physical body. Right? Now, what would be a natural bridge principle for being warm and temperature? It would be something like this. At least that would be a good first shot, right? X is warm if and only if the temperature of X is high enough, right? With some threshold value R given contextually. I have greater than equals here. You could have greater than. Doesn't really matter for my purposes. It's something like that. And if that is a good idea for temperature, then a bridge principle like that, X is belief, if and only if the probability of X is high enough, should be a good idea for belief. Right? And principles like that have been around for a long, long time, of course. In fact, Richard Foley argued that you find something like that in Locke's essay. So they have been around for a long, long time. And that's why sometimes this principle is called the Lockean thesis. And since this conforms broadly to the empiricist tradition in which Pat is working, I thought, let's stick to the label. And in the first part, what I will use as a bridge principle for belief and degrees of belief will be the right to left direction. So if a proposition has high enough probability, then it is believed. And that is what I'm going to use as the bridge principle. So what I will do now is take this right to left direction of the Lockean thesis, take the axioms of probability for a subjective probability measure P, and let's assume Bell, a set of propositions from the same algebra over which the probability measure is explained. This set Bell is to be closed under logic, right? So if Y is believed, Y entails Z, in terms of propositions, this means subset, then Z is believed, right? If Y is believed and Z is believed, then their intersection, or if you like, their conjunction is believed, and the like. Right? I don't give you the full set here of postulates, but ultimately this will mean that this Bell is really given by one proposition, let's call it B sub W, one subset of the set of all possible worlds, or the full sample space, such that this B sub W is the logically strongest proposition that the agent believes in. Right? In possible worlds talk, it would be the set of accessible worlds. And every proposition that is believed will be a superset of that B sub W. That is what postulates on Bell like that, doxastic logic as it were, amount to. Now, what I'm interested in now is under which conditions can we have all of that at the same time? Right to left direction of the Lockean thesis, closure under logic for Bell, and the axioms of probability for P. And it turns out, if you throw all of them in, then actually this logically strongest belief proposition, B sub W, must be, probabilistically speaking, of a very particular form. And in order to spell that out, I need one concept. And that's a concept that I call P stability, P being a probability measure. There is a threshold value R here, like you have in the Lockean thesis, and it figures here too. So it's really a proposition being P stable R. That's the notion that I will need. And what this notion means is, what I have here, X is P stable if and only if, whenever you take a proposition Y that is consistent with X, that has non-empty intersection with X, then the conditional probability of our P stable set given X will be greater than the threshold value R. So this is quite a mouthful, but the idea is easy enough to get. If X is P stable and non-empty, the only interesting case, this means that, first of all, X itself has a probability greater than R. You get that by plugging in for the Y the full set of all possibilities, the top element of the algebra. So P-stable propositions, they have high probability. And what is added to that is, this is going to remain to be so when you conditionalize on a proposition that is consistent with such a P-stable set. So P-stable propositions have high probability, and it's not easy to get rid of that high probability by conditionalizations of a salient kind. That's P-stability. Okay? That's very much related to notions of resiliency that you find in Brian Skyrms' work on chance. So it's very much in the same ballpark. You can see I'm drawing together the full Stanford community here in formal philosophy. I'm not done this yet. More people are going to come. So p-stable propositions have stably high probabilities under salient suppositions. All propositions of probability 1 are trivially p-stable. But there are lots of propositions normally around which are p-stable without having probability 1. And that's what makes this whole theory so interesting, I think. Okay, so why do I need that? That's the first representation theorem. The following two statements you can prove are equivalent. The first statement just collects all the postulates, right? P is a probability measure, Bell satisfies logical closure, that's stochastic logic if you like. And you have the right to left direction of the Lockean thesis. For what threshold? The threshold is given by the probability of the logically strongest proposition the agent currently believes in, right? So that's the threshold. So notice the threshold here depends on the probability measure. If you play around with the probability measure, you might have to take a different threshold. Okay, that's important. Okay, now the other statement clarifies under what conditions you can have that. And it really says you take the probability measure and you pick a non-empty p-stable proposition, and that amounts to the same thing as picking P and Bell. So this p-stable proposition here is really this logically strongest proposition that the agent believes in, right? And it works in both directions, right? If you give me P and Bell so that all of that is satisfied, then Bell is really given by a p-stable proposition. And if you take a probability measure and you pick a p-stable proposition and you define Bell in that way, then you get back P and Bell so that all of our conditions are satisfied, right? That's how it works. And you can show additionally, either of these sides actually implies the full Lockean thesis, even the left to right direction of the Lockean thesis. So you might have thought you could just live with the right to left direction. But once you throw in logic for qualitative beliefs, you actually get the full Lockean thesis, right? There's no way around that. So here's an example. That's just a little probability measure. You can determine a very simple algorithm that will compute the p-stable set. So it's easy to program that, right? And you know Pat likes that. So in this case, the algorithm spits out actually 6 p-stable sets, one being the trivial case of a set with probability 1, but the other 5 p-stable sets all having probability less than 1. And the theorem says whenever you choose one of them to be the logically strongest proposition believed, right? And you determine belief from that, you get all of our conditions satisfied, right? You can see the threshold values that you would use for the right to left direction of the Lockean thesis in that case. So for example, W1, W2, W3, W4, that's a p-stable set. You can use it. W1, W2 is another one. You can use that too. You can't use W1, W2, W3. You can't use a threshold that lies in between these two thresholds, right? Otherwise, logical closure, in particular closure under conjunction, would not be satisfied. Here's another property that you get. So the previous representation theorem actually only needed finite additivity on the probabilistic side. But throw in sigma additivity, right? Then what you get is something very nice, even in the infinite case. If you have p-stable propositions of probability less than 1 at all, they look like this. They are well ordered with respect to the subset relation, right? So if you know the semantics of conditional logic, Lewisian sphere semantics, it looks like a sphere system, right? So that's very, very nice, actually. Since this is a well ordering, in such a situation, there will always be at least p-stable set of probability less than 1, if there is one at all. And that least one will give you the most possible beliefs, right? It's the bravest option that you can take, given the probability measure, right? The least set here will give you the most subsets, and that means the most sets that are believed. Here's another example. So this is my mind, right? I'm very simple-minded. I have 3 possible worlds. That's it, right? My probability measure then lives somewhere in this triangle, right? So the center point being the uniform probability measure giving 1/3 to each singleton sets, right? Being here means assigning probability 1 to the single set of W1 and so on, right? So each point here is a probability measure. Then I have a threshold like R1/2, and then by the theory, I can compute the p-stable sets in each of these cases. So for example here, if my probability measure lives here, close to W3, then W3 itself will be a p-stable set. W3 and W2 taken together will be a p-stable set. And taking all of them will be a p-stable set. So there are 3 p-stable sets here. the bravest option will be the one where I just take W3 as the p-stable set. Okay? So say I'm maximally brave, in fact I am. Okay. Then, if my measure is somewhere in this triangle, what I believe is, I will believe W3 to be the actual world. Okay? And if I convey that information, for example, to Helen, right? I tell her, I believe W3 is the actual world, right? Then she will know about my probability measure, that Hannes's probability measure is somewhere in here, right? So belief talk is a coarse-grained way of talking about probabilities, in a sense. Okay? That's the outcome. And almost everywhere in the triangle, you get p-stable sets of probability less than 1, sort of the interesting case. What happens in the uniform probability case, the only p-stable set is the full set of all worlds. Sort of in the lottery paradox case, right? The theory predicts that you believe some ticket will be drawn, but you can't believe of any particular ticket that it will not be drawn. So there's no exciting consequence here, but it's sort of something that seems all right. There's another approach to the same theory, but that starts from conditional belief, even on the qualitative side. And again, the starting point is something that goes back to Pat's work. So Pat was, I believe, the first to observe that if you have a valid argument in the sense of classical logic, right, then if the probabilities of the premises are bounded from below by 1 minus epsilon, and you have m premises, the probability of the conclusion is bounded from below by 1 minus m times epsilon. Right? This was taken up later by Ernest Adams, who I believe was your first PhD student, is that right?
Second.
Second one? Okay, close enough. And what Ernest Adams did is he generalized that idea to a case where you have arguments that might involve conditionals, right? And their probabilities being given by the corresponding conditional probabilities. And then he turned that into a probabilistic definition of validity, even for arguments of that sort, which goes like this. Such an argument is valid if and only for all epsilon. There is a delta, so it's like continuity, right? Such that if the probabilities of the premises are all bounded from below by 1 minus delta, the probability of the conclusion is bounded from below by 1 minus epsilon. Right? And this is pretty close to qualitative conditional belief, if you think about it, right? With a threshold like in the Lockean thesis. But it's not quite what I want, because the thresholds differ for the premises and the conclusion, right? And in a sense, there is no fixed threshold, but you play around with lots of them, right? But let's take the idea and use in the representation theorem now conditional belief, so I can say something like Z is believed on a supposition of Y, right? As the bridge principle, I will now use the other direction of the Lockean thesis, the left to right direction. So it's really, if Z is believed on a supposition of Y, then the corresponding conditional probability is high enough, given by some fixed threshold value, in that case R. Okay? And then I try to prove a representation theorem again, and again it works. So the following two statements are equivalent. P is a probability measure. Bell, right, which is now a class of pairs of propositions, right, it's conditional belief, is closed under logic. Now, what this means now has to be made precise, and this can be done in different ways, and they all amount to the same thing, right? So you can say it's closed under rules that we know from Lewis's conditional logic. Or you can say it's closed under rules that we know from non-monotonic reasoning, what people call rational consequence relations. Or it's closed under the rules of belief revision, right? What's called the AGM theory of belief revision. All gives you the same thing. You plugged it in, that's closure under logic in that case. And you throw in the left to right direction of the Lockean thesis. Right? Then an equivalent way of stating that is to say you take the probability measure and you pick now a chain of p-stable propositions. And that amounts to the same thing. Right? So if you give me P and Bell and the left to right direction of the Lockean thesis, right, then Bell can really be cooked up from a chain of p-stable propositions. And it also works the other way around. If you have a probability measure, you pick any chain of p-stable propositions, then in this way you get a Bell so that all of our postulates are satisfied. Okay. And again, if you fix the second argument on which you conditionalize, then you actually, again, get the full Lockean thesis. Okay. So you can see it's p-stability again. It amounts to the same theory. So in this case here, for example, I could convey the following information now to Helen. I could say, I believe W3 is the case. I'm maximally brave again. That's what I'm assuming here, okay? But on the supposition that it's not W3, I believe W2 is the case. But on the supposition that it's neither of them, I believe W1 is the case, right? So it's really a sphere system or a ranking of worlds that we have here. If I convey that information to Hal, what she knows is that my probability measure lives in that triangle, right? And whatever else I tell her about my qualitative beliefs, it won't help to pin down the probability measure because they all determine the same conditional belief structure, right? So you get an invariance property like you often get in measurement theory. It's not determined by the usual invariance properties, but it's something like that. Again, talking in terms of conditional belief is coarse-grained talking in terms of probabilities, and you get that from the theory. Now, how does this relate to more traditional work on qualitative probability? This is from a paper by Pat, Measurement of Belief, where he introduces what he calls weak qualitative probability structures. And that's structures that deal with notions like certainty, being more likely than not, being as likely as not, being less likely than not, and being impossible. And he deals with them simultaneously. Now, if you look at my first case, where I dealt with absolute belief, that's very close to what Pat is doing there. So what I call Bell is very much like Pat's more likely than not. The difference is I allow thresholds to vary with the probability measure, right? Where he sort of fixes it to be 1/2, right? And that allows myself to also have closure under conjunction as being part of closure under logic, which he does not have, right? He has things like if A implies B, and A is more likely than not, then B is more likely than not, right? So this is part of logical closure, but I also have closure under conjunction. That's sort of the difference. Now, the more important case in the literature is the case of what is called qualitative probability structure, which goes back to Di Finetti. It was observed that these axioms here, although they're very nice, need to be supplemented in order to get a proper representation theorem going, and that was done later by Dana Scott. Now, if you think of my second representation theorem, where I dealt with conditional belief, then underlying this conditional belief structure is really a weak ordering of worlds, which induces a weak ordering of propositions. So you can actually compare that situation with the situation here, because that's a weak ordering, a very special kind of weak ordering of propositions or events too. And then you find what the difference is. So what do you have to change here in order to get my representation theorem going? It's the following thing. You take out S4, this S4 axiom, and you replace it by these two conditions. And in my case, I would read them like this. If A is a superset of B, then A is at least as plausible as B is. Okay? So that's an axiom that they get too, just by derivation. Okay? But additionally, and that's the main difference, if A is more plausible than B and A is more plausible than C, then in my case, you also have that A is more plausible than the union of B and C. Now, if this ordering here was supposed to represent has greater probability than, then an axiom like this wouldn't make sense at all, right? Because the probabilities here, it might be that you have to add the two probabilities of B and C, right, if they are disjoint. That's why they don't want an axiom like that here. But if you have a different viewpoint, you come from a logical perspective, and you think of it in a way that this really means the most plausible A worlds, right, are more plausible than the most plausible B worlds, something like that, then an axiom like that makes perfect sense. Because the most plausible B or C worlds must either be most plausible B worlds or most plausible C worlds, right? And then you would have that going, right? So that's the reason. And that's the main difference. And if you plugged it in, you get the representation theorem going. Of course, my partial ordering means something else than here. It doesn't mean has higher probability than, but roughly something like is of at least the same probabilistic order of magnitude as, right? Which is something more abstract, but that's fine. Now, this is an area that I think might become, hopefully, because I'm working on it, very interesting to many people. I know other people are working on that too, like Kevin Kelly and Hunty Lin at Carnegie Mellon and others. And if you're successful, then logic and probability might become very good friends. And if so, the way was paved to that by Pat's work. So many thanks and happy birthday to you.
Pat, do you have a comment? No, you said so much, I have to think a while.
There's a question, I think, back there. Did you have a question? No? Hi. Yes.
I was just wondering about this union pattern. So it's reminiscent of Lewis's semantics for counterfactuals and the extension that he proposes to various other modalities. And it's also reminiscent of Joseph Halpern's logic for comparative likelihood. And sort of more recently, people have picked up on this. And it's like Angelica Kratzer's semantics for epistemic modals as well. And recently, various people have picked up on this and argued that it's a really bad prediction for epistemic modalities, at least. And so I'm coming at this more from the linguistics side, but I'm interested in, is this plausible as a logic for the word believe, or do you intend this as more as a representation of a concept of belief which is possibly divorced from the meaning of the English word or its German equivalent or whatever?
Right, I mean, of course, in these areas where we're doing things abstractly, right, it's always hard to claim that we capture, all that is sort of in the concept of belief in everyday talk, so I wouldn't claim that. That is why sometimes people prefer the term acceptance, right, because you make it clear that it's more a technical term of art, right? But actually, I would say there's so much convergence in the formal theories of conditional belief that you get the same axiomatic structure everywhere. It's just presented in different ways. That I would say, I mean, we must be up to something, right? So it's really, I mean, it's not, if you look here, it's not a coincidence that you get a ranking of worlds here, right? Or that you get a sphere system in the David Lewis sense here, right? And you mentioned some of the formal theories, right? In addition to the ones that I mentioned, where you pretty much get the same formal structure out of that, right? So sort of normatively speaking, I think we're up to something. And I would say, sort of the descriptive part shouldn't be too much away from it, because it would be very surprising if all these different theories sort of, converging to the same stuff, right? We're not up to something that's even real in a descriptive sense, right? But I would never claim that we capture everything. But yes, the idea would be that it gets close to what we mean by conditional belief, not absolute belief, right? These are structures for conditional belief. Believing Y on the supposition of X, right? And that's a matter-of-fact supposition, not subjunctive or counter-to-the-fact supposition, but a matter-of-fact supposition, right? So that's also what you find in the suppositionalist treatment of indicative conditional, right? That you get in Ernest Adams's theory. It's just quantitative there, right? And that's actually not so far away from epistemic modals, right? Because it's sort of a pragmatist theory where supposition doesn't give you truth conditions. And it's more like an act that you're making when you assume an antecedent. So I don't think it's very much away from the Kratzer theory, actually.
Any other questions? All right. No, thank you.
Thank you very much.
Okay, what I want to do today, good morning everybody, is to discuss the role of representational theory of measurement. According to Luce and Suppes, representational measurement is on the one hand an attempt to understand the nature of empirical observations that can be usefully recorded in some reasonably unique fashion in terms of familiar mathematical structure. Well, you know the stuff, so I will just skip. Suppes' beautiful example of measuring weights by means of a balance, as represented by a suitable set-theoretical structure, suggests that RTM, representational theory of measurement, involves a claim about measuring procedures, perhaps a form of instrumentalism, and that every measurement procedure consists of constructing some homomorphism. Curiously enough, other authors have got the impression that set-theoretical structures RTM makes use of, far from representing empirical measurements or empirical instrumentalist measurement, are not even about the natural world. For instance, Michel writes that RTM is based upon an inconsistent triad. First, there is the idea that mathematical structures, including numerical ones, are about abstract entities and not about the natural world. Second, there is the idea that representation requires at least a partial identity of structure between the system represented and the system representing it. And third, there is the idea that measurement is the numerical representation of natural systems. The second and third ideas imply that natural systems instantiate mathematical structures, and when the natural system involves an unbounded, continuous quantity, it provides an instance of the systems of positive real numbers. Thus, the second two refute the first idea, the principal raison d'etre for the representational theory. Now, let me start by distinguishing between metrization and measuring. By metrization of magnitude m, I understand a demonstration out of empirically meaningful conditions of the fact that m is measurable. RTM accomplishes the metrization of m by building suitable set-theoretical structures and proving the existence of a certain homomorphism, which is a mathematical representation of m. By measuring procedure, I understand a procedure for actually finding the value of m for given objects with respect to a unit of reference. It seems to me that RTM does not claim that every measuring procedure consists of explicitly constructing some homomorphism. What it does claim is that any magnitude m must satisfy certain conditions in order for it to be metrizable. The task of the theory of fundamental metrization is to probe into the conditions that m must satisfy in order to guarantee the existence of such representation when the same does not presuppose any other previous metrizations. The fundamental measuring procedures determine specific empirical procedures for qualitative comparison of the specific property involved, and chooses a standard with which the assignment begins. It is certain that RTM has never maintained the claim that mathematical structures, including numerical ones, are about abstract entities and not about the real world. Clearly, mathematical structures are abstract entities insofar as they are set-theoretical structures. And they are about the natural and the social world, let me add. But the meaning of about, in this context, needs philosophical clarification. I will try to clarify the idea that natural systems instantiate mathematical structures and criticize the idea that natural systems may involve unbounded continuous quantities. It will be seen that the existence of important metrizations in economic theory requires the adoption of rather severe restrictions. Let me start by making some distinctions. I distinguish target, concrete, real systems, let's say the US economy 2012, given in pre-theoretical experience, from model systems on one hand and set theoretical structures on the other. I take for granted that scientific theories can be identified with certain ordered classes of set theoretical structures. Moreover, I assume that theories can be formulated by means of the definition of set theoretical predicates. The relationships between target systems, model systems, and set theoretical structures is roughly the following. A model system is an idealized replica of a certain class of target systems, a replica that can be described by means of axioms defining a set theoretical predicate. Model systems are not set theoretical structures, but rather imagined physical, economic, or geometric objects that represent their corresponding target systems. Thus, model systems can be seen as imagined physical systems, that is, hypothetical entities that, as a matter of fact, do not exist spatio-temporally, but are nevertheless not purely mathematical or structural in that they would be physical things if they were real. If the Newtonian model of Sun and Earth were real, it would consist of two spherical bodies with mass and other concrete properties, such as hardness and color, properties that structures do not have. Likewise, the populations in the Lotka-Volterra model would consist of flesh and blood animals if they were real. And the agents in Edgeworth's economic model would be rational human beings. Hence, I think it's important to stress that the representation of target systems systems by means of a model system, of a target system by means of a model system cannot be identified with any kind of homomorphism, since homomorphisms are mappings from one set theoretical structure into another. My version and defense of RTM is grounded upon these distinctions. When the question arises whether the property of components of a given type of concrete system is measurable, RTM proceeds to build a typical model system to represent the class, and based upon the properties of such model, builds a class of set theoretical structures by means of the definition of a set theoretical predicate. It is in this sense that mathematical structures are about the natural world. They are true of more or less idealized model systems that purport to represent some type of concrete target system in the world. These structures, insofar as they represent target systems, may be called empirical structures. Pat's famous example of measuring weights by means of a balance is a classical instance of an empirical structure, or so I think. But it can be misleading in two ways. It may suggest both that measurement structures are always empirical, in the sense that they are not describing idealized model systems, and that RTM is a general theory of concrete empirical measuring procedures. The main criticism against RTM in the field of economic methodology begin by misconstruing it as a theory of measuring procedures, which it is not except for some cases. It is a theory about the conditions and properties of certain classes of target systems must satisfy in order to be measurable. It functions thus as a sort of ideal control for empirical measuring procedures that can also be suggestive of empirical measuring procedures. A natural or social system, that is to say a target system, instantiates a mathematical structure if and only if it is exactly described by the actions defining the structure under a certain empirical interpretation, without the mediation of a model system. In such a case, the structure may be called an empirical structure, in a strict sense. For instance, a structure of the form X with a reference relation would be an empirical structure faithfully recording the preferences of a given consumer if X is interpreted as the collection of consumption menus over which the consumer has to make a choice, and his pairwise preferences are correctly recoded by the relationship. But then nothing guarantees a priori that A will be a weak order. It doesn't have to be a weak order. In general, it is not target systems, the objects, that are exactly described as mathematical structures, but rather model systems representing the former. Hence, many mathematical structures that we find in economics are not instantiated by target systems, but only by model systems obtained out of idealized conditions. It is usual in the process of elaboration of economics theories the construction of ideal objects out of concepts that, even though they originate in experience and correspond to real properties of real beings, have suffered a sort of deformation. For example, there is no doubt that real economic agents are human beings who handle certain information, who can remember events, and that can also perform arithmetic operations. That is why the predicates 1, 2, and 3, X possesses information, X has memory, X is able to perform calculations, are true of human beings who effect economic transactions anywhere. Nevertheless, even though economic theory has to refer somehow to the properties they denote, the use of mathematical method requires the use of deformed versions of such predicates, or of the concepts they express thereby. Some specializations of economic theory require, for instance, for the economic agents to possess perfect information, perfect memory, and unlimited computational powers. Thus, for instance, predicates 1, 2, and 3 are deformed in order to obtain 4, 5, and 6. X possesses perfect information, X has perfect recall, and X has unlimited computational powers. The conjunction of predicates defines a type of ideal object, what we have called a model system, non-existent in reality, but required to channel mathematical reasoning. As Walras put it in Elements d'économie politique, the mathematical method is not an experimental method. It is a rational method. The pure science of economics should then abstract and define ideal type concepts in terms of which it carries its reasoning. The return to reality should not take place until the science is completed, and then only with a view to practical applications. Let us call idealized concepts or idealizations the concepts obtained by deformation out of concepts which are truly predicable of real beings. If in spite of this deformation, the same are meaningful, even if they are false, of these real objects, and keep an intention akin to those. We have called ideal objects those model systems built by means of conjunctions of predicates that express idealizations. The axioms of a consistent economic theory define directly as a theoretical predicate, as A is a regular preference structure, but they are also obliquely true, at least under a typical interpretation of the primitive terms of ideal objects. For instance, the just mentioned predicate can be defined canonically as follows. A is a regular preference structure if A is a weak order. It is debatable whether the preference relation exhibited by a human agent at a given moment is connected and transitive. Nevertheless, the systematic development of the theory can go on as if it were so. Utility theory has proceeded through the construction of ideal objects endowed with idealized properties. It has assumed, for instance, that the consumer, an ideal object, defines his preference relation over a space of consumption menus, which is representable as the non-negative orthon of RL. Other idealizations introduced over and above these are those of a continuous or unsatiated preference relation. All these idealizations are needed in order to prove the existence of utility functions possessing certain characteristics required by economic theory, like continuity or monotonicity. Hence, the use of RTM to obtain such functions cannot be seen as a case of empirical measurement. It is usually in economics the application of RTM methods to obtain representations of idealized magnitudes. For instance, Bieber and Dembski used such methods in trying to fundamentally measure income. They found that income can be fundamentally measured only in a world of complete and perfect markets, but not necessarily otherwise. They concluded that at a fundamental level, the central feature of financial reporting cannot be income measurement. Let me skip this section. And let me finish by talking about models of data in measuring procedures. The view of theories as systems of theoretical structures naturally leads to a particular view of theory application and testing. Typically, to conceptualize a certain phenomenon means to apply the conceptual apparatus of the theory, fleshing out the terms with a particular concrete meaning. For instance, in order to conceptualize a target system C, a real human consumer, demand theory claims that C be represented by a certain model system M, which is a consumer with unlimited memory that knows beforehand what would be his election in confronting any budget set. The information of this ideal consumer is represented in a set theoretical structure by means of a demand function, eta. If the Slotsky matrix corresponding to eta is symmetric and negative semi-definite, M knows that eta coincides with a Walrasian demand function mu derived from a utility function that represents his preferences. Moreover, since M has unlimited computational capabilities, he can determine instantaneously the preference relation from which mu, which turns out to be eta, derives. Now, if the theory represents C with M, the scientist may try to apply T to C. Whether T is applicable or not to C is an entirely empirical matter. To say that it is a claim, to say that it is a claim that has to be held on the basis of empirical data. Varian has stressed that there are two approaches to this problem. One, the approach based upon calculus, originated in the work of Antonelli and Slutsky, derives necessary and sufficient conditions on the derivatives of the demand function eta. The second, originated in the work of Samuelson, is called non-parametric because it assumes no specific form whatsoever for the demand function. The distinction between the two approaches is very important in empirical work. The calculus approach assumes that the entire demand function, that is to say our eta, is available for analysis, while the algebraic approach assumes only a finite number of observations on consumer behavior is available. Since all existing data on consumer behavior does consist of a finite number of observations, the later assumption is much more realistic. Now, we can explain the non-parametric method by means of the concept of data structure, or as Pat prefers to call it, model of data. Observing the behavior of the agent, we get the structure of data that you see here, with a eta with a hat on top, where such eta is a function defined over a finite subset of price cum wealth, precisely that of pairs of systems of price and income levels under which the behavior of the consumer has been actually observed. The empirical demand function eta hat is obviously finite and discrete, which is something that Pat loves a lot. Finite and discrete things that can be observed. And this is why structure D can be depicted by means of the table. This one here. That is the structure, completely presented. Now, the non-parametric method does not try to build directly the complete demand function eta, but rather uses an algorithm to build directly a utility function that rationalizes the data, provided that structure D satisfies the conditions of the following theorem, using Afriat. You can see the conditions. Basically is the data satisfy the general action of revealed preference, and that is equivalent to all the other conditions. In particular, the existence of a concave, monotonic, continuous, non-associated utility function that rationalizes the data. Afriat and Varian provided algorithms by means of which it is possible to build a utility function U that rationalizes the data of structure D. This is jumping, so to say, from a model of data to the theoretic function U, utility. Then it is possible to embed D in the partial structure consisting of the Walrasian demand function mu induced by the utility function. That is to say, mu restricted to F coincides with eta hat. The parametric method, on the other hand, tries first to determine the non-theoretical demand function eta without involving the utility, and afterward tries to recover the utility out of eta. The upshot, and I'm finishing now, the upshot of this example is that there are some applications of economic theories that require methods other than those of representational theory of measurement in order to flesh out the terms of the theory, to actually measure the magnitudes referred to by the terms of the theory. Suppes himself used methods more similar to this, fleshing out the magnitudes out of models of data in his classical experiments on learning theory. Hence, more than a method to flesh out the terms of a theory and empirical application or testing, I think in economics, the representational theory of measurement seems to be rather a methodology to establish the existence of metrizations, sometimes even for idealized magnitudes, and especially for this. But thank you very much for all you have given us, and have a happy birthday.
And I would like to thank Helen and Pat and anyone else responsible for bringing me here. This is a wonderful place. and I wish I spent more time.
Thank you.
And Pat and I got to know each other fairly well several years ago. Sorry, when we showed us. Okay, thank you. When we taught a course together, he proposed we teach a course on Hume, Kant, and Rawls. And I said I would be delighted so long as he handled Kant. And he was willing probably to handle any named philosopher, but he did take the Kant task very seriously. And in fact, I think I learned more about Kant in that one afternoon seminar than in all the rest of the times I struggled to figure out what he was saying. So it was a really great occasion for me at that time. And what I'm going to talk about today partly grew out of that, grew out of Hume's way of trying to understand what's going on in lots of contexts. And he called it mirroring. I mirror what you do, and therefore get some understanding on my part of what it is you're doing, and begin to understand your motives, your intentions, and lots of other things. I'm going to give you 2 quotes from Hume. He says, "No quality of human nature is more remarkable, both in itself and in its consequences, than that propensity we have to sympathize with others," and here's the rich part, "and to receive by communication their inclinations and sentiments, however different from or even contrary to our own." So he thinks that we somehow, in being close together, during one of us having emotional responses to something, we share that emotional response, not by watching the response so much as literally by, in fact, living through it with the person who's having it. The other quotation is, "We may remark that the minds of men are mirrors to one another, not only because they reflect each other's emotions, but also because those rays of passion, sentiments, and opinions may be often reverberated and may decayed away by insensible degrees." One of those quotes is from Book 2 and one from Book 3 of Hume's treatise. So here he has an idea that he carries out at great length in 2 quite different contexts, and yet nevertheless we would like to know more about that. And he, in the later edition of the Inquiry on Morals, he leaves out the passage on this phenomenon, and one suspects it's because he got hammered for saying such a silly thing. And so he leaves it out in this later edition. It's too bad, because it would have been better had he in fact gone on to make more of it rather than to make less of it. So what mirroring does, many, many things, and I'm going to try to go through fairly quickly a list of maybe 7 or 8 things that it does for us. Either it does in our lives, or it does in our efforts to explain things. So those 2 roles that it has. Hume says, and he's not often given full credit for the claim because it sounds wrong to moral theorists, Hume says that he's giving us a science of morals. That's to say he's not giving us a correct view of what's right or wrong. That's not of his interest. But he is giving us a science explaining why you and I think that X is right and Y is wrong. So that's a very important part of his contribution to us, and I think it helps explain many, many things that go on. And he also says, in a phrase that Rawls later borrows, Rawls says of some of the things that stand in the background that they are morality psychologized. And Hume is morality psychologized. So he gives us a moral theory, but it is based in the psychology of the people we are and the way in which we work. So that's a very important part of this whole enterprise, that bit of science. And it wouldn't make sense to call it a science of morality if in fact it were about telling us what's the right thing, the wrong thing to do. So that's a very important one of his contributions. Then it makes an evolutionary model of why we have this particular responsiveness to somebody else's emotions, why we sympathize, empathize with another, fairly clear. It's a fairly easy kind of evolutionary model, in fact probably easier than the much more common one we see that tries to explain how somehow people wind up being altruistic, even at cost to themselves. The idea that he has about mirroring gives us some entree to the black box of the mind, and he, in fact, makes that point, that that's an interesting part of what's going on. If I can somehow, just by being in your presence when you have some sensation, understand and grasp that, then I've actually entered your mind to some extent. He has a wonderful example that is used in many different ways, but it should be used here. It is that you or I, say, are standing on the beach and we see a boat going down out in the distance. We know that it's full of people, they're going to drown, most of them, as it goes down. And so we know intellectually that there's going to be huge loss, that there are going to be pain suffered and all sorts of things. That's not important in Hume's account. What's really important is if the boat were closer and we could actually see their faces in agony, then that would stimulate in us, unintentionally, it would stimulate in us the same kind of emotion that they're suffering. And so Hume's account of this boat going down out there is about what could be mirrored from the people if only if it were close enough and we could in fact be part of what's going on to some extent. Pat's work on various ways of understanding what somebody thinks a word means in the brain or is where it is stored in the brain and so forth might be one of the few cases in which we're approaching the kind of thing that Hume is talking about, and I would like to hear more of that. There was a huge debate in Scottish philosophy, and I'm not going to do the Scottish background of all of this. It only takes maybe 2/3 of the paper to do that, and maybe 1/3 of the paper to do the mirroring. And so I'm going to stick with the mirroring and not take up the Scottish stuff. But their literature is about sympathy in the time of Hume and a little before and a little after. Their work is on sympathy and sentiments. And sympathy, of course, is where I understand what's going on in your life and feel for it. Sentiments are perhaps not as clearly defined as essentially judgments, evaluations, and so forth. So I feel what your pain is, and now I judge it or somebody else or you, and that's the sentiment that I have from it. So when Bill Clinton was campaigning, he said, "I feel your pain." It is common to read what he said or to read other such things as saying somehow I literally perceive or feel what you're doing. So you stub your toe, I feel the pain in my toe. And Hume wants to say that that's the wrong way to read it. It is not the case that you or I suffer the literal same kind of pain that we can in fact mirror from somebody else. So I, on the campaign trail, say, I feel your pain. That doesn't mean that I somehow have a pain like the pain you have and not having enough money to pay your doctor's bills or whatever. It means that I understand that you're in pain over this issue, and that's a much more limited understanding, but also a more sensible one. So sympathy and sentiments get commonly run together. And in mirroring, that's correct. In other contexts, it would be wrong to run them together. They're separate categories. But if we do this mirroring, in fact, what happens is that I simultaneously get from you what you're feeling and react to it. I don't have to sit there and think through that. So there's no intervening action or thought or process. I just go directly from sympathy to sentiments or from understanding what your pain is, and in fact judging whoever caused it, including plausibly you. So sympathy is a form, this is a strictly Scottish definition, is a form of non-verbal direct communication. That's a very important idea, that somehow you or I can communicate with each other about things without words, and the things that we can particularly communicate to each other are these things like pains and benefits and happiness and so forth. So you and I, in one of Hume's things, he quotes Horace having said that the human countenance receives the joy and the pain of others. We shed tears on behalf of others, or we laugh or smile on behalf of others. And that's not because we are literally somehow taking their part. It's because they have such direct access to us that we feel those things. So I would like to somehow give a mirroring account of the wonderful time I had with Pat in our seminar, our joint seminar, and to say happy birthday, St. Pat.
Professor Suppes has a question. Well, I want to comment on the great congeniality between Russell and me on these topics. And in particular, we very much agree about the importance of Book 2 of Hume's treatise and the passions. And in fact, many philosophers stop reading Hume with Book 1, particularly undergraduates. That's what they usually get. Hume himself thought, and Russell and I have discussed this, that the work on the passions was what was really original in the treatise. And I think that's very much true. He left it out of the inquiry, which is a modification, as Russell stated, kept an appendix, because he was criticized for this work on the passion. It was so original and new, but wasn't properly appreciated. And the resolution of those comments, Russell and I read his paper, we've already discussed it a bit, and fortunately, in those days, we had a seminar here at Stanford because he was here half-time at NYU. And I think...
the perfect arrangement.
Perfect arrangement. So we're going to see if we can't run some kind of joint seminar next winter session between Stanford and NYU to continue this dialogue about human sympathy. I loved his paper and found many clarifying things about it.
Okay. Asked two questions. First one, you stressed the idea that the communication is nonverbal. Why is verbal? Why is that relevant? I mean, why can't I communicate my pain to you?
Oh, you can
verbally, and you
yeah.
you don't necessarily. So, but you put a big you seem to put a lot of emphasis on the nonverbal character. I didn't see why verbal communication isn't. There is obviously other communication. There's facial,
yeah,
and all that. But why shouldn't verbal be included?
It is included in our explanation of what's going on, but mirroring per se does not, in fact, require that. So mirroring.
Well, it doesn't necessarily. Isn't one way of projecting image which is mirrored what I'm saying to you?
I want to comment on that.
Yeah.
Yeah. I want to comment on that. So I think what I've come to recognize is very important. That in the study of speech, too much emphasis is put on its cognitive aspects. The young child says, "Mommy, why aren't you talking to me like this? I haven't done anything wrong." And the child has perceived that the mother's emotional quality of the language is expressing impatience, etc. Characteristically of our perception of emotion, the receiver is better at perceiving it than the one who delivers the emotion. And this perception that speech has emotional qualities that we are extraordinarily sensitive at perceiving. And in fact, a typical thing in people who are very close, the perception of emotion is almost more acute. I mean, often what's said is so repetitious it doesn't matter too much about the cognitive content, but you can know how things have gone through the day when you see that person by the quality of the speech you receive. And I think what's very important, nonverbal here means without the expression of the words, but the emotion is actually carried in the speech. I don't say I'm mad. You pick that up immediately from indirectly in this way. And I think that's extraordinarily important, much too ignored and typically in the philosophical tradition of discussing the cognitive character of language. I couldn't resist. Ken and I continually talk about many things.
Let me ask you a second.
You had a second question. You don't have to sit down, Pat. You can be ready on this one also.
You read Mirror, and I thought you were going to lead up to something, which there's a lot of, I see this read, I'm no way expert in this, but something called mirror neurons.
Yes. Yeah.
And the question is that this sympathy has got a basis for, which I believe is true of a number of animals. I mean, it's not true, not only human, as I understand it.
Yeah, in fact, you can respond to an ape or any number of other things, and they probably be your pet cat or a dog, and they respond using the same sorts of ways.
But this gives a physiological basis for these sympathetic judgments.
Yeah, a neurological basis.
Neurological basis.
Yeah. Okay, yeah, in fact.
Is anything interesting from the point of view of studying morals occur yet from these physiological studies?
Probably. It certainly goes to the kind of program that Hume had, which is to explain scientifically explain your attachment to a particular moral value and my attachment perhaps to a different one. And so it has a lot to do with the explanation in the scientific sense of your and my beliefs about morals, as opposed to somehow working through a theory that's going to show us what is the truth. For Hume, there is no truth in morals.
Rawls versus Hume.
Professor Perry.
Yeah, this question is, as I understand Hume, if I have a pain, that's a sensation, then I form an idea of it that in some strange way resembles it. And when I anticipate having a pain or remember having a pain, it's that idea that's involved. So my question is, and forgive me if you made this clear, my mind was wrong. Is the mechanism involved in sympathy and the mechanism involved in anticipating or remembering one's own pain essentially the same? I mean, is the idea that's involved when I'm sympathetic to your pain the same one I would employ when I'm remembering or anticipating?
This gets back again to Ken's point. I think there's something fundamentally important about the way in which this communication takes place that we should perhaps see more and develop more and see how it actually works in various contexts. I think it's significant and different from just ordinary reasoning about these things. When you're talking about the reasoning that I go through from a past experience that might be related to the current experience, that's a little bit like the claim on the part, that's contrary to the claim on the part of Hume that somehow these things might be completely simultaneously. It's not that I see or feel or whatever and then interpret. It's that I instantly do the whole schmear so that I see whatever's going on in your mind. I capture that in my mind, and I don't have to reason about it at all. In fact, that's a very important part of it for Hume, is that it does not require reason. That may not be satisfactory.
We have a lot of questions here, Russ. You're going to be kept at work for a while.
Is there a connection to some of the more recent work in the psychoanalytic tradition of people like Karl Jaspers or Rollo May, for example? Do you have traced that at all?
I suspect, although I'm not sufficiently articulate in their writings to in fact say that, although that raises the question just a moment ago about whether the mirror neurons and so forth are going to be a helpful thing in our trying to understand what's going on in these contexts. And I think probably yes. So far the work is at a somewhat early stage, and I would guess that it would get much richer as time passes, and then we would answer those kinds of questions better.
So I'm just wondering about if we turn the mirror slightly around, so taking an idea like in sociology of the looking glass self, that we use the other as a form of self-reflection. So for example, does Hume have any account for how we might, if I do a behavior that is morally disgusting to others, could I learn that and have some kind of gain in self-knowledge by seeing a disgust response in others?
I don't think so. I may be wrong. There might be a note here or there about such things, but that's a nice point.
So
maybe I misunderstood you, but it seems you're talking about a kind of universality of the mirroring experience. But where in that picture is the very common situation where one person is inflicting pain on another without any empathy, without any concern?
No, I don't actually think there's much of anything universal. So it's not a universality condition that's at stake here. It's in fact that's one of the modes in which we operate, or many of us do operate. And that's about as far as I think we can probably go with that. So there could be, in the midst of all of this, people for whom, in fact, inflicting pain gives more pleasure than the pain itself gives pain.
We'll have time for one more.
A small point about Hume, namely this, that his notion of sympathy is a completely naturalistic notion. It simply means that emotions are transferred from person to person. It's not a pro-sentiment in Hume's sense. He discusses the question whether there's a, what he calls a universal feeling of benevolence. And he says, oh yes, it's true that my neighbor's joy makes me joyous and his misery makes me miserable. But that has nothing to do with benevolence. It's mere sympathy.
Yeah, I think that's part of the scientific stance that he's taken toward all of this stuff. And that's, for whatever reason, lost in a long period of time, brought back by Kemp Smith and more recent writers. But there was a period in which the most original parts of Hume were essentially lost to contemporary reading, and it's good to see some of that coming back.
Thank you very much.
Thank you.
The papers were presented and the influence on my work at Pat Suppes has had tremendous influence on all of us. Incredible breadth of his interests has to be cited. Not only the depth, but the tremendous variety of papers here, right? Even this morning, and I've already studied those elsewhere on the program, all relate to Pat's work in some way, which shows what consequences it has had for all of us. Empirical relevance, theoretical relevance, understanding, all of us those. And Pat, I want to thank you for all that I've learned from you in a long period of time, maybe more than anybody else here. I have some really rather disjointed remarks to make. This is not a paper in the sense of results. It may even be, you might not be totally surprised, a paper or remarks written, not even a paper, on which has paradoxical questions raised. I don't have kind of a definite answer. I don't have a contradiction, but I want to say the nature of economic intercourse. Economics is a system. There are relationships among many people and among, of course, physical objects and impalpable objects like services of some kind. The ordinary way we present economics, the way I've done it in many of my works, is kind of a trade in goods, or goods and services to be correct, but that by itself isn't fundamental. It's a way by which people who produce grains exchange their grains for, in some way, wind up with food, with housing and food, and maybe the things they need in order to produce the grain, and so forth and so on. And that's why we always present it in a general equilibrium, work out the what's offered has to equal what's being demanded, and somehow the idea of a price as a way of regulating this thing. That we balance it by saying, well, you can sell things and get something for them, and then take that. Instead of bartering, we sell things and then take the money and buy something else. And this is a much more efficient way of getting goods around. As elaborate developments from Hume's good friend and executor, Adam Smith, as to how this transactions take place, and some arguments as to why this is a particularly efficient way of arranging these goods and services. But even from the beginning, and even at Smith's time, there was a little bit of a problem with this. And that's the big problem, but one of them is, there are a number, but one of them is there's a future, which you transact today, is only part of your life. People live, and of course may even have interests beyond their own lifetime in terms of requests. But let's say it's enough for our purposes that they live some period of time, worry about a future. We have savings and investments. Some people say, well, I'm not going to spend all I have today. I'm not going to spend goods. So I'll try to put it into something, give it to somebody else who's going to take care, who's going to use it for some purpose, and then return it to me later when I need it. Let's say we have a retirement cycle. You retire before you die, and therefore need some support during a period, or whatever your on the other hand, people can use, and that may be the more crucial thing, can use goods because they last and produce things in the future. You can buy a piece of land lasts forever. So I can buy a piece of land and use it or rent it out. Or I can put up a building which will house a factory which will house my production. I can buy machines and so forth. Things which the purpose of putting these things up is to secure some return which is going to be in the future. So we already have the problem that if I lend money to somebody, I buy common stocks or lend money in some way, I have I begin to get wrapped up into your considerations. There's been a big argument for the price system, kind of libertarian in a way, but maybe we can think of it as information-based, and I'm moving toward the topic. Namely that I know what I want, and for example, if I'm a producer, I know how to produce. So I have knowledge of how to plant or produce weave cotton or whatever activity you want to do things. And I have this private information. You don't really, if you're dealing with me, you're buying cloth from me, you don't have to know how I make the cloth at all. So in other words, we can have a distribution of information, and that's what separates us. But you see now, if I lend to somebody else, it isn't really my information that's at stake, it's somebody else's information. And we begin to see some difficulties. It's also true, of course, that a basic, something I'm not going to dwell on, but I should mention here, a basic issue about information is that even this narrow view of productive information, how to produce things, changes over time. In fact, the usual economic interpretation is that most of the vast increase in our consumption, a lot of these people flew here, technologies that didn't even exist so long ago, and so forth. These have changed over time, and that in some sense, which I'm not going to go into, most of our growth in a per capita sense, I'm not doing population numbers, it has changed over time. It's changing over time, and this is partly the result of decisions. Now you see that all of this creates the idea that you really have to know something about the others, information you would ordinarily think of as private, is not really, you're going to depend on other people's private knowledge, private information. Now, a lot of this was very sharply put forward historically in what's known in the economic literature as the socialist controversy. Socialism, of course, was a big political movement, especially before the World War I. And after World War I and all its attendant problems, there were moves in countries like Austria, Germany, leaving aside Russia, which is something else. There were a lot of intellectuals and a popular feeling for moving to the socialist parties would have 30, 40, 50% of the legislature and so forth. Ludwig von Mises, an Austrian economist, argued socialism is impossible. Without prices, you wouldn't know what to do. And this started a whole discussion. And one of the replies, Joseph Schumpeter, in fact, was one of the, although another Austrian economist, actually, and not by any means a socialist, really, nevertheless said, well, really no, the socialists could create a price system. And this led to a whole discussion, so that Friedrich von Hayek, of course, one of the great contributors to this, Oscar Lange, Van Lerner, the names of them, some of them won't be even to you. But it became it brought forward an idea which is already implicit, that prices are not really facts, things I have to pay to, but also were sources of information. They told me how difficult it was to produce something. The thing was expensive. It meant it was kind of, you have to use a lot of resources to prove it, and this means you're drawing those resources from somewhere else. So a high price, you really want a high price as a way of choking down demand for this. We didn't discuss the relevance of the price of gasoline, which is so much discussed today. So it became a big emphasis on the idea of information. By the time I was a graduate student, this was sort of already standard. And I didn't realize it. I reviewed the literature, but that really, although it's implicit, it really became very explicit with this socialist controversy in the 20s and 30s. And it made the idea that prices are not really, that the whole economic system becomes to some extent an exchange of information, of knowledge. I'm taught that things are hard for me to get. Of course, you apply a real stick. I've got to pay them. But in this view of socialism, the prices were really just bookkeeping entries. By the way, the same problem occurs within a large firm, which is using its own product from one department as an input into product from another department. So you have, so to speak, socialist entities all over the place. General Motors Corporation or General Electric are, to some extent, socialist enterprises. And they operate with this thing. Now, notice when I started. I'll try to keep it short. You have 10 minutes, okay, I get that right. Now this comes up, it probably comes up in another way. Again, they go coming back to the question of provision for the future. But there's one characteristic, the provision of the future is sometimes referred to as putting up capital, and that's where capitalism is. There were, of course, sort of capitalist enterprises back into the Middle Ages. Some of the city-states, like Florence, certainly were operating in ways that all that different from today. Out in the countryside, you have a feudal system, and things work differently. But one thing that when capitalism really became dominant, you began to have large enterprises, there was a brand new phenomenon, which really had never occurred before. Maybe really occurred, I think, really, there's some 18th century examples, but the early 19th century became systematic. The idea of the business cycle and the financial crisis. We have one, we're going through one right now, both in the United States and Europe. But this is not new. It was noted, I believe, in 1819 was the first example, where somehow there was no floods, there were no droughts, there was nothing, and yet people were unemployed, being laid off. There was a lack of demand somehow. And this has been a recurrent feature of capitalism. And to blame people might talk about government interference, the government played a tiny role in the whole 19th century, which was marked by repeated and sometimes extremely severe. The 19 wasn't so bad, but 37, 73, 93, these were major things. We were years, and banks would fail, financial crises, banks would fail all over the place. People couldn't borrow money when they wanted to because there was no bank to lend it to. Phenomena very much like this occurred repeatedly through the 19th century, and that in spite of everything that's happened, they have not ceased. This Oscar Morgenstern, another Austrian economist, the Austrians were very prolific. This had a very exciting intellectual group in this period, and not only in economics, of course, it's architecture, psychoanalysis, whatever. Was director of a business cycle research institute in Vienna. And he of course, predicting turned out to be rather difficult. I must say I was, you know, I was a graduate student in economics, and then war came, and I became a meteorologist, like Pat. And there's, well, I'm going to deal with science now, real hard stuff. Of course, the predictability wasn't a bit better in meteorology with all the scientific background. It wasn't economics. But anyway, Morgenstern was concerned, and he said, well, look, if I'm trying to predict the future, make an investment or save or something, I know the world that I'm dealing with is built up out of other people's behavior. And other people's behavior, how they invest or what they do. And other people's behavior depends on their forecasts of what I do. So I forecast, you know, you get into, now, there's always this question of two ways of when things are mutually dependent. There are two things that can happen. Things can go to hell, and we'll come back. And the other argument is you get equilibrium. That's the economists always like to find equilibrium. I think that's been our problem. That's been my problem. Morgenstern took one particular story. I don't know if many people are Sherlock Holmes fans anymore, but there's a famous episode when Sherlock Holmes is dealing with Moriarty. The whole thing is a wonderful anticipation of game theory. As the line made at one point, Moriarty says, doubtless my next question has crossed your mind, to which Holmes replies, and doubtless my answer has crossed yours. But in the course of this, Holmes is fleeing from Moriarty. If he stays, he'll be killed. Anyway, Moriarty follows him in another train, and he has a choice of getting off at an intermediate station or going on to Dover and then on to the continent. And Moriarty, of course, has to make the same choice. If they're in the same place, Holmes is dead. Well, you can see that this is a game without an equilibrium of pure strategies, but as we'd say in a very elementary way. And anyway, it was a question of each one's belief about the other. Now, Morgenstern uses as an example. It was in the book on when he worked with Falmagne, he said, "Oh no, with mixed strategies we can get rid of this." But mixed strategies really means beliefs. What do I believe about it? So for me to optimize depends on my believing something about your strategy. Now, if you think about it, it's very unstable. If I get the other person's probably just a little bit wrong, I'll go to the extreme. I'll go to a pure strategy. If you think about it. So that shows us some of the problems. Now, let me just say a few words. So information becomes, and suggests the possibility of instability. This had, by the way, it was independently of Morgenstern, and Austin said about the same time by Keynes, who cited as an example, supposing that he found that some beer, this is a prohibition that just ended, and some beer producer in the United States had a contest where you had 6 models. You voted for one of them, and if yours got the majority, if the leading candidate of the 6 was your choice, you got a prize of some kind, which of course meant that you were not really picking the prettiest girl, but you were picking the one who you thought other people thought was the prettiest. And of course, if you go back, it's the one that you thought, you go back, this is an infinite regress, and you go back, and the question is, infinite regresses, once they cost them, become impossible. If you assume that the process of calculating is relevant, then this becomes impossible. But how do you have a theory of what's optimal when you take account of the cost of calculating the optimality? This is, really tries to describe Herb Simon's idea of bounded rationality as rationality with taking account of confusion. I think, but the trouble is that problem is a harder one than when you start. Let me just say a few words. The information becomes a commodity. I really want to know what other people are doing. I want to know what technological progress is likely to be, what my competitors are likely to invent, all these sorts of things. If I'm buying security, I want to know what the probability that's going to, let's stick to rational discussion, by the way, never mind going to completely irrational, just behavioral, what we call behavioral economics. Just assume that each individual is maximizing expected utility based on a subjective probability. But there's nothing guaranteeing that the subjective probabilities are equal. Okay. Let me just say, information becomes a commodity. It's valuable to me. Its value does depend on the scale on which I'm going to use it. But it's a funny kind of commodity. It's costly to acquire. I have to do some performances. And I can transmit it without losing it. If I have a ton of steel and I sell a ton of steel, I no longer have the steel. If I tell you something, I still got the information. It can be reused. I can use it over and over again. One of the results is you get specialization. It pays to be a doctor. It doesn't pay me to acquire all the medical knowledge in the world. Because I'm going to use it only once. Or it doesn't pay me if I'm sick to learn all about my sickness. A doctor will use the same knowledge over and over again. So it pays to specialize. This means people now know that they're giving people who know more than they do. I can go on there. Finally, let me just mention one problem. Suppose we start with people having different probabilities. Now, supposing there's some event in the world which does not affect me at all, doesn't affect anybody. I mean, my satisfaction level, utility, whatever you want, doesn't depend on it. But there's an event which occurs and which we get different probabilities about. It becomes reasonable to create a market in which we bet on it. It's pretty clear that this is a net loss. I think this is one aspect that I would details. But there's a net loss to society. You're creating an unequal distribution of income. We get started with equal distribution. That gives you one example. And you can state this in several different ways. So I leave you with a lot of paradoxes about knowledge. And they have practical economic consequences. And I suspect, although I don't have a good theory, that a good deal of what's happened in the recent times is clear to us. You see, the problem with explaining some of these bets is not why a firm in the modern world bets by borrowing money and betting. I don't know what the stocks do. The person does not, the question in my mind is not why the person bet. That's the rewards are so great, maybe you take a chance of being wiped out. The question is why the lenders lend. This is, I find, these are, remember, generally people in the business. They have a lot of previous knowledge about risks. They have a lot at stake. One of the problems with you go back to the long-term capital management affair of 1998, the lenders, the amounts of sophisticated involved, that the Federal Reserve is concerned that those lenders would be affected and they would have subsequent consequences. Imagine a bank which has so much at stake in lending to one firm. Why do they lend? And the question is, how do they form their beliefs, which would lead into this? And of course, we saw this in a much bigger form in 2007, 2008. So I think this question of how you handle information as a commodity has got some rather good consequences. Thank you.
You want to look for some money to CAD and
find out. Well, let me invest it for you.
Greek bonds.
Did you answer that question at the end that you posed about what's going on?
No. I think the trouble is, I think it's one of the systems. I'm not sure if you have an authority. You kind of a closed view about it. Because at each stage you open up one thing more. Maybe some formula. I don't see how it's quite clear. There's a lot of. It's just the beginning of a lot of history. A financial crisis where people obviously did things which turned out to be very bad. And the question is why, given that, our usual point of view is, people will hedge, diversify. You don't put all your eggs in one basket, sort of thing. And that's what I've written on most of my life and things. I mean, to get worried that that's not a descriptive statement. And the question, and I say the real puzzle is why people who are highly informed, or should be highly informed, and have a lot at stake, too. question how well informed you should be does depend on how much you have at stake. But these people have a lot at stake, so there's none of those explanations. It's easy to understand. For example, if I'm putting my money in a bank, I'm not really in a position to check out what the bank is really sound. That's why I want regulation, I want deposit insurance, all these things. But these are the big players, not the small, but people who it does pay require this information. And they find if they've foregone, somebody else is making a lot of money and they're not. They infer that they made a mistake.
So there's been there's a recent book by one of your colleagues, Bob Frank at Cornell, in which the main argument is that one shouldn't think of people as, broadly speaking, utility maximizers. It's thinking of them as wanting to do better than their competitors.
Yeah, well, you see, but they're not, but interesting because that doesn't explain this, though. Let me grant that motivation. They didn't do well. If they in fact did better than their competitors, or let's say they lost money, but they lost less money than anybody else. But that's not. But that doesn't seem to be the explanation. I mean, that's a perfectly coherent theory. Unfortunately, I don't think it doesn't seem to quite explain that.
What about not all the cases, but some of the cases explained by moral hazard? That is, you can take a risk if you think there's somebody in the background that's going to bail you out.
Yeah, but
that leads to different behavior if you have that problem of moral hazard.
That's been an argument that gets discussed a lot. However, Lehman Brothers was allowed to go under. It's true that some of them were bailed out. The AIG was bailed out, or the not really so much AIG, the people who they're dealing with the credit default, but Bear Stearns survived, but the people there were kind of wiped out. A lot of them. But they did let Lehman Brothers go under. They did let Lehman Brothers go under, so they may have thought they were going to get bailed out.
But of course.
But it is true. But your point is well taken. There is a feeling that the government is going to intervene if things get too bad. In fact, that position is an old one. Walter Paget in the 1880s, the discussion of the role of the Bank of England, was it's the lender of last resort. You pump, if things are going bad, you pump money in the system, which, from the point of view of the banks, amounts to at least something of a bailout. Yeah, there's no question moral hazard. It does play a role. The idea is, if you're big enough, or it isn't so much people talk about too big to fail. It's a little misleading. It's if a bunch of banks, each one is small, but they're all going to fail, from the public policy, that's just the same thing. So it isn't sheer size. It's that there's a high correlation in the risks among different individuals. That's the real point. And then it's true that there is always a feeling that, well, the government will be better. They did interfere in LTCM, actually. Actually, that one passed. It turned out in the end they got a bunch of banks that did bail out. And the banks who did the bailing out didn't in fact lose any money. Well, by the way, especially the government's getting back the bulk of its money. But you're right. There is some sense in which the government will intervene. Now, if we go down the austerity route, which is being so much pushed, that may end. And then if we take it seriously, it would be a view that, but of course, they didn't apply to Luce.
I think it's a testament, thank you, Ken, for this presentation. It's a testament to the scope of Pat's work that we have covered in this brief session, the spectrum from the relevance of set theoretic structures to understanding economic reality to the topic on the front page of today's New York Times, the relationship discussion between the head of the IMF and Angela Merkel about the wisdom of austerity. So thank you very much.
I'm going to start by quoting the opening paragraph
of a paper that was published just a few months ago. The title of the paper is Why the Effectiveness of Mathematics in the Natural Sciences is Not Surprising. And it should not be surprising to you who the author is. That's Pat Suppes. And I'll start by reading the introductory paragraph there that sort of sets the stage for what I'm going to say here. The source of human applications of mathematics to natural phenomena is very likely to be found in the perceptual processes necessary for most animals to survive, either as prey, predator, or forager. Much of the resources of the brain are used to transform the patterns of energy that impinges on sensory nerve endings into representations more or less isomorphic to the structures and portions of the world. It is one of the intellectual triumphs of ancient Greek thought, especially by Aristotle, to have recognized for the first time systematically the centrality of such isomorphism for perception. The move from visual perception to intuitive geometry and then to systematic Euclidean geometry seems psychologically natural. The Greek application of this geometric viewpoint is to the motion of the heavens constitute the first great work in mathematical physics. The process from the Stone Age to Ptolemy is surely a very much bigger step than the move from Ptolemy to Newton and Einstein. The rest of the paper is a very careful argument to support this point of view. Pat concentrates on perception and geometry. I happened a year or so ago to listen to a talk by Bill Tate, a well-known logician. He gave the Skólem lecture on the emergence of primitive recursive arithmetic. And he wondered why Skólem was led to this notion. Now, this led me to look back to the early development of Skólem. And I would like to tell you a little bit about that and then go on to sort of give numbers equal prominence as geometry in the kind of discussion that has been carrying on. And I must also say there, I'm a mathematician. And for mathematicians, there is usually a comfort in being able to write equations and things like that. That gives you a sort of security. I'm not going to write any equations today, which means that I'm on slightly uncertain grounds. I have listened to philosophy papers being read, and I have more often than not fallen asleep. So that is a risk I'm following here. But if I see someone nodding too much, I'll raise my voice and see if I can persuade you to follow the argument further. Well, why this starting point with Skólem? You can take a short quotation in German. Es kommt doch auch bei der Begründung der Mathematik auf die Sache und nicht auf die Beziehungen an. These are words that Skólem wrote and occurs toward the end of his 1923 paper on the Begründung der elementaren Arithmetik durch die rekurrierende Denkweise. Thoralf Skólem, who wrote this paper in 1919, had at that time become acquainted with the approach to elementary arithmetic in the Principia Mathematica of Russell and Whitehead, and he was not at all convinced. Natural numbers and their fundamental properties need not and should not be justified through an exercise in abstract logic. This seems to be a strongly held belief of Skólem, firmly rooted in his early education and work experiences. By 1919, he had already been exposed to a wide range of problems and projects in both pure and applied mathematics. His master thesis in mathematics from 1913 was a profound study of the algebraic logic of Peirce and Schröder. His first employment was as a student assistant to the well-known Norwegian physicist Birkeland in the years 1909 to 1914. His special assignment was to help with the mathematics of several geophysical phenomena. In 1917, he published his first major mathematical paper, Untersuchungen über einige klassenkombinatorische Probleme. That was a 90-page long monograph. It is therefore not surprising that he was not at all convinced when he in Göttingen in the winter 1915-16 first learned about the Russell-Whitehead approach to elementary arithmetic in the Principia Mathematica. We get the impression that Skolen, through his work in algebra, combinatorics, and geophysics, knew what numbers are, and that his 1923 paper can be seen as a protest against the approach of Russell and Whitehead. In this paper, he takes the first step toward a more correct approach by developing what has later become known as primitive recursive arithmetic. And he would argue that to choose the rekurrierende Denkweise as a foundation for real mathematics was almost to be expected from an expert in combinatorial analysis. He develops his theory within a free variable logic formalism, but he is not entirely satisfied. But despite this and many references to further to foundation, he never wrote a continuation of that paper. Skolen does not tell us what numbers exactly are. But an answer to this problem is, however, only part of the challenge. The world of mathematics contains, as we have noticed, in addition to the discrete object of arithmetic, also the continuous object of geometry. Is Russell's logic and Zermelo's axioms for Cantorian set theory an answer to the question of existence? Skolen would not agree. Mathematics is more than an axiomatic exercise in logic and abstract theory. In a popular lecture given at the Michelsen Institute, that was a private research institute in Norway in the 1930s, when money was very scarce at the universities and rich merchants from the city of Bergen had money to spend on academic pursuits, even foundational mathematics. So in a popular lecture in 1932, he says, if one works within a completely formalized mathematics based on a finite number of precisely stated axioms, there is nothing to discuss but questions of consistency and ease of manipulation. But in ordinary mathematical practice, for example, in the usual study on continua, which are never given by a set of specified formal constructive principle, the axiom of choice is, in my opinion, definitely undesirable. A kind of scientific fraud. Leaving the question of scientific fraud aside, a challenge to ordinary mathematical practice remains to explain what kind of objects numbers and geometric objects are. There is a long story to tell here. I want in this paper to try to defend or to analyze a bit further a kind of cultural view on the origin of numbers. And I was led to this many, many years ago when I read a paper by an American anthropologist, Leslie White, The Locus of Mathematical Reality, an Anthropological Footnote. White opens his essay by asking, do mathematical truths reside in the external world, there to be discovered by man, or are they man-made inventions? Does mathematical reality have an existence and validity independent of the human species, or is it merely a function of the human nervous system? So there is a long story again here to be told, but the anthropologist ends up by arguing that there is no mystery about mathematical reality. Mathematics is a kind of primate behavior as language, musical systems, and the penal code are. That and that mathematical concepts are man-made, just as ethical values, traffic rules, and bird cages are man-made. These are quotations from the anthropologist. I wouldn't think about bird cages when discussing on numbers, but I'm faithful to my sources. And he says, mathematics in its entirety is its truth and its realities is part of human culture, nothing more. Mathematical truth exists in the cultural tradition into which the individual is born and so enters his mind from the outside. But apart from cultural tradition, mathematical concepts have neither existence nor meaning, and of course cultural traditions have no existence apart from the species. Mathematical realities thus have an existence independent of the individual mind, but are wholly dependent upon the mind of the species. So, expressed on this very general level, it sounds great, but it needs a more careful argument. A variant of the cultural view, more as a kind of a social construction, is has no significant support in the mathematical community. A classical reference is the book The Mathematical Experience by Davis and Hurst. There is also a more recent book by Hurst arguing this point of view. A recent voice in support of this view is David Mumford in a lecture from 2000. But again, these are more expressions of opinion. For a more carefully argued account of mathematics as a social construct, I make a reference to work by a young mathematician, Cole, from 2008, and also some forthcoming work. And I should have liked to, but I cannot, make a reference to the thoughts of Saul Pfefferman on the same issues. These are views that he has had for the last 20 years, more or less. And it is about time that it is now presented more carefully and fully to his fellow mathematicians. Well, all of this, I mean, there has been a great deal of criticism against this social constructivism from philosophers of mathematics. They have not always been convinced by this approach. And I have references to several critical accounts by philosophers to that point of view. In a sense, one feels that philosophers of mathematics has become a bit too protective of their domain and do not look very favorably upon people trying to inject into this domain bits of science from other domains. I think Pat will agree with me on that point. I presented this work in a seminar in Oslo under the leadership of Fenstad, and then of course I was immediately, they immediately drew upon me all of Husserl and his view on the foundation of mathematics. And it is quite clear that he, among philosophers, seems to have a very coherent and I would say in many respects a very attractive philosophy of mathematics. But nevertheless, I'm not prepared to give up on this cultural approach. The main problem with the cultural approach was, as expressed by Husserl, is that mathematical objects cannot be assimilated to social or cultural objects because social and cultural objects are bound to times and places. That is a main point. And at this point, I would like to make reference to the work of Richard Kitson and and he has his own work, but he has also written an excellent survey of Husserl's philosophy of mathematics in the Cambridge companion volume on Husserl. I very much recommend that article. So, let me go back to, let me still somewhat stubbornly insist on the cultural view. How could the cultural view be strengthened to meet the criticism of Husserl? This is a question I'm saying a few words about. We agree that numbers are abstract objects, but how are they related to brain and mind? I shall, in this paper, I first approach this question by discussing the evolution of language and how syntactic categories such as noun phrases and verb phrases became object of the collective mind. I mean, the anthropologists, 5 minutes, distinguish between 3 kinds of objects: the matter and mind, the individual mind, and then you have the abstract objects, and in the colorful language, the collective mind of the species, and that is where numbers are. I cannot hear, since Sol already signaled to me that there are only a few minutes left, 5 minutes left, go into this example of syntactic category. But it's very interesting, because the argument there is not a neural argument in itself, from that you have it, but it's an evolutionary argument. You can formulate, and it was done by Martin Novak and collaborators in a paper some years ago in Nature, a theory that explains the evolutionary advantage of splitting up messages in an NP-VP form. And since there is a kind of a common view of the world in objects and acts and properties of objects, this seems to give syntactic categories a kind of universality and invariance over various cultural differences. This is very much different from word order, which we know, again, recent work, is very much dependent on cultural context. If we come to numbers, there has been a much current interest among neuroscientists on how mathematics is related to brain structure. In the paper, I review much of this work, but I'm not entirely convinced by that kind of work, that there exists a certain mathematics gene there from eternity to eternity. It seems also that for numbers, we would try to seek a similar explanations as we had for syntactic categories. And then we don't start with the mathematics of the Greeks, but we do, as Pat did in his paper, go all the way back to bones and strings and stones and these early examples of being able to handle quantities 1, 2, and more, and then try to trace a history of how this developed. I mean, there is a lot of knowledge, of the development of, obviously, the non-European roots of mathematics, and that is highly relevant for this story, in the same way as the references Pat makes to the development of geometry. So I think that, but what is also interesting is the question, which also maybe is that the relationship between the environment and the individual, the genetic makeup. I mean, today one is much more willing, and I can refer you to 2 excellent survey papers, one in Nature and one in Science, quite recently, just the last one just a few months ago, on causalities in more complicated biological systems. And you have a two-way trade between inheritance and outside influence. And it's quite clear that with the invariance, say, of syntactic categories and of numbers, and they have a survival value, then those who survive would have a genetical basis for having these things. This, in a way, is a counter-argument to Chomsky's views on the origin of grammar. In my view, the semantics is primary, and the syntax is secondary. But when the syntax becomes fixed in the surviving individuals, you might be led to think that they are the primary thing. But it is a co-evolutionary fact. 1 minute? Yes. I should now enter into a long discussion of how this kind of view leads to Pat's view of why the applicability is not unreasonable, or in my words, that the obvious applicability of mathematics. But and that I cannot do in 1 minute. I must say that I wrote this without knowing of Pat's last paper, but I sent a copy to him and got a very, very extensive reply. And we are now entering into a dialogue on the nature of mathematics, and we hope to continue that. In fact, we are looking forward to receiving, beyond this 90th birthday and all these celebrations. He will come to Oslo later this year, and we will sit down and discuss this further, concentrating on structure and algorithms. The main point of disagreement between us is whether the things we observe are really objects or just patterns of reasoning. This reminds us of the famous Abram Robinson Gödel's discussions about infinitesimals, which was mentioned in the title, but not here. Okay, thank you.
Well, I'll say something short. I'm trying not to say too much here, because we're going to continue this discussion. The disagreement between us and some of the views held, for example, by Saul, which I respect, one wants to be careful, I think, and give something rather more subtle and complex in answer than I might first tend to do. And I think one of the things that I want to start with, the brain does not process abstract objects. So there has to be something that is not abstract to give an account of any mathematical thinking. So one of the things I want to distinguish is between the claims about the nature of number and the claims about mathematical thinking. But I think we could probably agree on that. And the only remark I'll make here, I want to continue in the discussions with Jens-Erik to say that the primacy goes to the thinking and secondarily to the nature, whereas much mathematical discussion goes the other way. What's primary is the nature of the abstract objects, not the thinking about them. That, I think, is a mistake.
Further questions? Let's see, Jaakko.
Only one comment. I think we should distinguish the problem, the question of the so to speak, the origin of mathematical concept, mathematical objects, whether the human creations or not, from the question of the objectivity, or from their objectivity. There are lots of objects that are human constructions, and yet we have lots of very hard facts, objective facts about them. Bridges are human constructions. They are cultural objects in a sense. But we'd better be aware that there are very hard facts about them, objective facts. As Turing said to Wittgenstein, if you have wrong ideas about mathematics when you build them, the bridge will collapse. So I think we have to distinguish these two questions from each other very, very, very clearly.
course, we have to distinguish these things clearly, but my argument here is that certain abstract objects, like syntactic categories, like numbers, has a certain cultural invariance. I mean, if we did not insist on that, the field will be open for Husserl and his kind of mathematical philosophy. But this is a long point. I mean, I argue a little bit about the point you are making in the paper, but could not really enter into it here.
Okay. I find your notion of collective mind extremely problematic. It actually contradicts methodological individualism.
Well,
according to which there is no such a thing as a universal mind as Averroes, for instance, would have us.
I mean, this is, I use this as a cultural object. I use the collective mind as a colloquial phrase. It was used by the anthropologists, so I thought it was amusing to adopt this phrase. But behind this idea of a collective mind, there is this world of abstract objects, different from matter and different from individual mind. So it's more a choice of words.
Last question.
Last question. I think there's something I observed that I think is relevant to what kind of point of view Pat was giving. Tell me if I'm wrong, Pat. I noticed that I showed that if you take very basic principles about finite sets, there's a unique process of extrapolation to general sets based on simplicity. You take all simple statements of a certain form and in the finite, and you can extrapolate them to the infinite. Take all statements, you get nonsense. But you take the simple ones, and you can prove a theorem that generates CF directly from finite considerations. You see the connection I'm thinking of with what you said?
Well, yeah, but the point here is that I was telling the story about the origin and tried to answer the criticism from Husserl. Pure mathematics, in a sense, arose out of this practice when the old syntax became the new structure. And the new structures, then you start to investigate that new structure and discover all kinds of interesting and deep properties. But that is a toolmaker's trade, not the natural scientist's trade.
I think my comment was more related to what Pat was saying.
Okay, that's good.
I'll wait. I'll wait, Harvey, until you talk. Time's up.
Obviously, yes, our time is up. We don't want to run into the next section. So thank you, that was very stimulating.
It'll work. Okay, then I'll start. I'm deeply honored to be speaking at Pat's 90th. And Pat was chairman of the philosophy department when I was hired as assistant professor of philosophy right after my PhD in mathematics from MIT, way back, I think I could say way back in September 1967. Wow. Pat Suppes is arguably the greatest polymath on the planet today. And I'm going to talk a bit about recent advances in a long-standing project of mine in the foundations of mathematics. Now, foundations of mathematics is just one of countless areas in which Pat has made substantial contributions. After writing two well-received textbooks in '57 and '60, still after I was born, but not much after, Pat's main interest in foundations of mathematics went into the direction of the foundations of mathematics as used in the sciences. And there's a focus on the foundations of finitism, geometry, and infinitesimal reasoning. Here is some of the papers of Pat in the Foundations of Mathematics, the two textbooks which are reprinted by Dover now, and geometry here, and philosophical implications of Tarski's work, Shakai, I don't know the pronunciation,
Chakwe, okay. I will continue. Summer, who is here, I can pronounce that. Now, of course, there are many more contributions to other aspects of logic by Pat. This is just what I would call foundations of mathematics being somewhat restricted. But Pat has many more papers in all kinds of aspects of the logic, some of them arguably foundations of math, but I decided to cut it down there. All right, so, but Pat, I talked to Pat wants me to talk about my stuff, not his stuff. Okay, so, is that all right? Yeah. Okay. So, the usual axioms for mathematics. Now, I doubt if many of you can recite the commonly accepted axioms of mathematics, and this won't be a problem for what I want to say. The usual setup is ZFC, or Zumelo-Franco set theory with the axiom of choice. And the variables of the system range over sets with a single primitive relation of membership written epsilon. And equality is also taken as primitive. This is the standard setup, the gold standard. ZFC consists of intelligible axioms about sets, together with the usual axioms and rules of first-order predicate calculus with equality. ZFC is gigantic overkill for the support of mathematical proofs. It is so successful as a general foundation for mathematics, it is so successful that mathematicians today generally have no idea what it is, but are at least aware of its existence. In other words, the mathematicians are not pushing the boundaries. If they were pushing the boundaries, they'd have to go pull off the dust off the shelf and see if something's legal or not. It is so successful that it is virtually unknown in detail, except, logician experts. All right, so with that background, the classical limitations of ZFC. Yet ZFC does have certain limitations. An obvious issue concerning ZFC, or for that matter, any proposed system for supporting mathematical proofs, is whether it supports a contradiction. Prima facie, any system that supports a contradiction is worthless as a foundation for mathematics. I could go on with a tiny footnote, but that's the standard point of view. So we want to be certain that ZFC is consistent, i.e. free of contradiction. But from work of Kurt Gödel, we have the following classical limitation of ZFC. Either ZFC does not prove that ZFC is consistent, or ZFC is not consistent. The generally accepted view is that the former holds, namely that ZFC is consistent, the usual view, and ZFC does not prove that ZFC is consistent. So it's limited in that way. Furthermore, Gödel's work shows that this situation cannot be repaired by modifying ZFC. So this is an irreparable situation. All right. Now we've learned to accept this first limitation of ZFC. ZFC does not prove that ZFC is free of contradiction. However, this does not reveal any limitation of ZFC for any what might be called, quote, normal mathematical purpose. There is a crucial problem in abstract set theoretic mathematics called the continuum hypothesis, which asserts that every infinite set of real numbers is in 1-1 correspondence with the integers or the real numbers. Every infinite set of real numbers is in 1-1 correspondence with the integers or the real numbers. And Gödel and Cohen in the 30s and 60s established the following limitation of ZFC, that ZFC can neither prove nor refute the continuum hypothesis. So this is a limitation of ZFC for some normal mathematical purpose. The Gödel-Cohen development sparked a substantial development whereby further limitations of ZFC for abstract set theoretic mathematics was established. Now, what do we mean by abstract set theoretic mathematics? So the key feature of abstract set theoretic mathematics is that extremely general, uncountable sets are involved. In the continuum hypothesis, arbitrary infinite sets of real numbers are involved. Examination of mathematics reveals that the reasonable uncountable sets, the mathematically reasonable uncountable sets, are Borel measurable subsets of complete separable metric spaces. Even this is far more than what is encountered for ordinary garden variety purposes. What happens if we're to give a more reasonably concrete formulation of the continuum hypothesis? Borel continuum hypothesis asserts the following. Every infinite Borel set of real numbers is in Borel 1-1 correspondence with the integers or the real numbers. That is the obvious Borel continuum hypothesis, being sensitive to the fact that in mathematics, sets of uncountable sets coming up are Borel measurable subspaces of a complete separable metric space. Okay, Borel continuum hypothesis is a well-known theorem, however, of ZFC from the Polish school, Hausdorff, Alexandrov. So the independence from ZFC is removed in this way by taming the pathological. Now, the new limitations of ZFC I want to talk about are much more concrete than Borel measurable sets and functions even. And the new limitations involve only rather concrete, discrete, and even finite mathematics. Caution. It is doubtful if any discrete or finite mathematical problem already arising in the mathematical literature by people other than me trying to do this are neither provable nor refutable from ZFC. But I argue and believe strongly that this would be inevitable, but we're in the wrong, I'm born too early for this, and so I wish to construct what I see from the future. So we claim that the new examples are simple and natural and strategic enough to, one, conform to existing standards for normal mathematical investigations of a concrete nature, and two, provide interesting and valued concrete mathematical information. And I work with leading core mathematicians concerning strategy for integrating the examples further into current concrete mathematical culture, and I can prove it by correspondence. Okay? Now I'm going to present a recent example of a simple concrete statement, neither provable nor refutable in ZFC. In fact, the statement is provable using certain far-reaching and well-studied extensions of the ZFC axioms, but not in ZFC alone. Let Q be the set of rationals. We begin with the following well-known statement. I use the rationals later. Every set of ordered pairs contains a maximal square. Okay, by a maximal square, I mean a subset of the form A cross A. So, and by maximal, I mean it's a subset of the form A cross A which is not properly contained in any subset B cross B. Now, I even think this may have an interesting physical interpretation. You know, non-deterministic, this is non-deterministic, this maximal square. So, you know, you pour some liquid into some container of hay or something, you know, and it's spreading around, you know, maximally or whatever. You know, I mean, you can make some image of this, you know, maximal things, maximal objects containing, you know, contained in things is something that probably has an interesting psychological or physical interpretation, which I don't begin to exploit, but I think it may be exploitable. Now, in the countable case, this is proved by a straightforward greedy construction. You enumerate the field of the set of ordered pairs, and you start throwing in points according to whether you're staying in according to whether the square, the Cartesian product of with itself of the stuff you've thrown in is contained in the original set of ordered pairs, and you throw it in if you can. If you can't, keep it out, and then this way you get a maximal. Now this is not deterministic because you could have. It's deterministic relative to the enumeration of the field of the relation, but the field of the relation can be enumerated in any way you want. Okay, so that's. All right, now we're moving towards the following statement. Every invariant set of ordered pairs contains an invariant maximal square where the two notions of invariant might be different. This is what we're moving towards. We're going to inject invariance conditions into this simple-minded statement that is well known, follows from Zorn's lemma, and the countable case has a beautiful greedy construction. We're going to simply throw invariance conditions in. Okay, let's see what happens. Now we need some structure to have an invariance condition. So let Q be the set of all rationals, and let Z plus be the set of all positive integers. So the situation I'm interested in the rationals and the integers sitting in there, positive integers sitting there. Every invariant subset of Q to the 2k contains an invariant prime maximal square, is what we're heading. Now because I'm in the space Q to the k, and that's a binary relation on Q to the k, because I'm in the space Q to the 2k, I can define a lot of invariance conditions that are very natural. So let's define order equivalence. Two vectors are said to be order equivalent if they're in the same order. This has a well-known definition. So 3, 5, 2, and 4, 7, 6 are in the same order. Okay. The other notion I want is a lifting function. So given a vector of rationals, I can lift it as follows. I can add 1 to all of the coordinates that are bigger than all of the coordinates that are not positive integers. So just as an example, 1, 3 has 3, 5. Doesn't have to be in order, but the example is similar. 1, 3 has 3, 5 goes to 1, 3 has 4, 6. Because 1 doesn't go up, because it's not bigger than all the things that are not positive, because 2, 3 has is not a positive. Okay, it's a very simple lifting operation. And I say that a set is order invariant if and only if, for any two order equivalent vectors, one is in the set, if and only if the other is. If and only it would follow from if then in this case. I call a set completely Z plus up invariant if and only if for every x, for every vector x in Q to the k, x is in S if and only if its lifting is in S. So this is an example of complete invariance. Complete invariance is a standard piece of terminology. Okay. And we have proved the following. Every order invariant subset of Q to the 2k contains a completely Z plus up invariant maximal square. Every order invariant subset of Q to the 2k contains, and Q to the 2k is viewed as ordered pairs for Q to the k. Every order invariant subset of Q to the 2k contains a completely Z plus up invariant maximal square. And I prove this only using much more than ZFC. I don't have a proof in ZFC, and I don't know that you can do it in ZFC. However, if you work instead with the rationals in the interval 0, 16 inclusive to the 32, so 16 tuples from the interval from 0 to 16 closed, where we restrict, where Z plus up obviously applies only to right open 16, because otherwise we'd go to 17, which is outside the space. If you do that, then we have every order invariant subset of Q 0, 16, 32 contains a completely Z plus up invariant maximal square. And this I prove the same way as I proved the other one, but this time I know that ZFC is not sufficient. I know that ZFC is not sufficient. Submitted for publication. Okay. Referee report not obtained yet. All right. Now, I'm repeating the statement. This statement is very concrete in the following senses. First of all, it is an easy exercise to construct a finite set of sentences in first-order predicate characters of equality such that the statement is outright equivalent to the satisfiability of those sentences. So by Gödel's completeness theorem, we know by general theory, Gödel's completeness theorem, that this statement is equivalent to the formal consistency of a finite set of sentences in predicate calculus, which means that it's what's called pi 0, 1. The same logical complexity as statements like Fermat's theorem. Goldbach. Okay, secondly, there's a non-deterministic algorithm straightforwardly associated with the statement, such that the statement holds if and only if this algorithm can be run for infinitely many steps without reaching an obstruction. It can also be shown that the statement holds if and only if this algorithm can be run, this obvious algorithm, by the way, it can be run for any given finite number of steps without reaching obstruction. So saying that you can, for every finite number of steps, you can make this construction without running into obstruction is equivalent to this statement. So that's also clearly very concrete, even though the actual statement is going to involve infinite things. And there are some further examples of statements, which I don't have time to talk to, which are neither provable nor irrefutable in ZFC, which are a little more involved, and they live entirely in initial segments of the natural numbers, so that one does not have to talk about an associated algorithm. One is talking about them directly, and these are explicitly finite. Probably have what, no minutes or one?
No, you have 2 minutes.
2 minutes, oh my God, all right. I can tell you everything. No, I can't. All right, so what's being used beyond ZFC? Just beyond ZFC, by the way, is a strongly inaccessible cardinal. To give you a flavor for this, and this is what's been used by Grothendieck in his most elaborate form of topoi. Kappa is a strong limit cardinal if and only if, for all smaller cardinals, 2 to the smaller cardinal is less than that cardinal. Kappa is a strongly inaccessible cardinal if it's a strong limit cardinal, and not the supreme of the set of cardinals that are smaller, of less cardinality, and is uncountable. These are classical definitions of the strongly inaccessible cardinals due to Cantor. And what I use for this stuff necessarily, demonstrably necessarily, are much, much, much bigger than that. The ones used, by the way, mathematicians, the vast bulk of mathematicians won't even see Aleph 1 for really, except in school. So Aleph 1 is the first uncountable cardinal. All right, the ones used and needed are a lot bigger, and they involve colorings, partitions. So for those of you who know the subject a little bit, I can finish this probably in 30 seconds. If you partition the unordered k-tuples from the cardinal, this is what I could need a cardinal with the following property. You partition the unordered k-tuples into 2 pieces. Then there's a stationary set, a stationary subset of the cardinal, all of whose k-tuples lie in the same piece. And stationary means meets every closed unbounded subset. So stationary is a kind of a large set. So this is a kind of a standard kind of large cardinal principle that goes far, far, far beyond the Cantor inaccessible cardinal used by Grothendieck. So with that, I'll close, and with reference to the economics talks, I'm going to say, Pat, you've now become much too big to fail.
Time for a couple of questions. Comments?
I'll ask a question, a philosophical one. You said it is doubtful if any discrete finite mathematical problems that have already arisen are neither provable nor refutable from ZFC. Can you say a little bit why you believe that's the case?
I think that I think there's a threshold. There needs to be a certain kind of combinatorial complexity that won't arise early. Now it's going to arise more early if people buy into what I'm doing. But it's just not something that is, it's just not something on the surface of the standard development of mathematics, except for much longer periods of time. And I think that, for example, I do think that some of the things I did, including earlier things involving Boolean relation theory, but this is a newer thing. This idea of studying invariance properties when they're not usually placed is something which I believe is a kind of an inevitable idea. And you need some sort of twist like that is going to take would take a long time to be done without me pushing at it, trying to speed it up. It's just that when you talk about abstract set theory, it's right away that ZFC is not good enough. Right away. But abstract set theory is extremely different than concrete mathematics. And I don't know, first of all, I'm not going to take it. I should not be taking any more time right now. But I don't know anything better to say to you.
Let's see.
For
ordinary mathematics, would second order arithmetic with choice suffice? Do they need all the rest of ZFC for practical mathematics?
Well, there's something called reverse mathematics, which writes down some much weaker systems than than what you described, much weaker, which map out. Now, this has precursors with work of Theorem. I mean, they also were considering this for many years. You know, what do you actually need to do things? And you need very little for a lot of stuff, and then at some point you need more and so forth. But there is a subject called reverse mathematics, which works out a lot of
Invented by Harvey.
which works out a lot of information about what exactly you need for what and so forth.
Bob, quick question.
Any thoughts about P versus NP?
Oh yes, I have this proof using large cardinals, and I'm keeping it secret. I'm gonna have to wait for. No, I don't know. I believe that P not equal to NP. Of course, I have this dream that maybe what's needed is some high-powered set theoretic method. That would be really spectacular. I don't spend a lot of time doing it, and if I did, I wouldn't admit to it.
That's an example of a problem posed beforehand.
Ah, yes.
Thank you very much. Next speaker is Dana Scott, who's going to speak about Turing Church and the Entscheidungsproblem.
Here to celebrate Pat's birthday. I hope you realize this is the Turing centenary. Now 90 is pretty close to 100. Of course, Turing tragically died at a very early age, and it's so wonderful to have such a big turnout here to celebrate Pat. And just think, in 2022, what a big turnout it's going to be. Pat was much too kind in his remarks the first day. I do want to tell him how much I've appreciated his support, mentoring, inspiration over the years. It's meant such a tremendous thing to me, Pat. And I'm glad that I'm the second oldest colleague. Kenneth gets the prize of the oldest one from 1950.
No, that's not true.
Sorry?
It's not true.
What's the other one?
Myself, Ted Anderson,
Ted Anderson, when are you from?
1993. I'm sorry, I'm 93. I'm a professor emeritus at Stanford University.
Oh, great. Okay, well, I'm the third then. I was thinking back on some personal history. When I entered the University of California as a freshman in 1950, what seems like an awfully long time ago to me, I looked up on the internet and found that the population of California was 10.5 million people. Today, the population of California is 37.5 million people, bigger than all of Canada. And I realized if I were magically made a high school student again, I would never have been able to get into the University of California under present circumstances. It's amazing how things have changed. I wouldn't be able to afford the University of California either.
Right.
But it changed my life. Meeting Pat changed my life. Going to Princeton totally changed my life. And I certainly appreciate all those opportunities. Just a couple of days ago, maybe a little bit longer, I came upon a letter. You won't be able to read this thing here in the notices of the American Mathematical Society. Let me quickly respond to it. Someone was answering an article written by Frank Quinn, A Revolution in Mathematics. And he says, my mathematics colleagues almost never think about mathematical logic. See the paper by Davis and Hirsch for a funny and profound description of mathematicians. Oh dear, Ruben Hirsch's book, What is Mathematics Really, is one of the most irritating books on my shelves. Mathematical logic is almost never taught in mathematics departments, this chap says. He's David Edwards. He's an emeritus professor at the University of Georgia. I looked him up. That's a very interesting CV there. Logic is almost never taught in mathematics department. It's taught in computer science departments and philosophy departments, and when it is taught in a purely technical way with no concern for history or philosophy, except at Stanford, except at Berkeley, except at Harvard. I mean, who is this guy? Now, in reference to what Harvey was saying, mathematicians still live in Cantor's paradise, or even Eilenberg's paradise. I think he should have said McLean's paradise there. In spite of Russell's paradox, they simply learn not to make certain moves that lead to trouble as long as the referee doesn't complain. What? Me worried? The various formalizations for avoiding Russell's paradox also prevent one from making certain moves which are usually safe and powerful. So mathematicians work informally and have always done so. There is almost no trace of mathematical logic in most of the history of modern mathematics. So, who's going to answer this letter in the Notices of the American Mathematics? I offer that as a challenge. I'm not saying that mathematicians are aware of what I said. Most are totally unaware of these issues and are simply working in a successful research tradition. Pat, if your books are going to be reprinted again soon, maybe you should add something to the preface there about the importance of logic and what it can do for you. What I want to turn here now is a bit of history about Turing, because of this centenary of this taking place. Things happened very quickly. As Jens-Erik was saying, Schoolem had a lot of very original results. In fact, Schoolem could have proved the completeness of first-order logic. But it wasn't so much in the air. What happened was that Hilbert and Ackermann's book came out and it formulated the questions about completeness and the Entscheidungs problem or decision problem that I want to allude to today. And then Gödel moved so fast and got his proof of the completeness theorem and then the incompleteness theorem. And so Schoolem's things weren't as noticed as they should have been. But things also moved very quickly with Church and Turing. So Church got his degree in 1927, and then he went for 2 years to Europe, first to Göttingen and then to England, I think. And he was formulating a new approach to foundations of mathematics, which then was published in 19, what does it say? I read it here. 19, oh no, I didn't put those things out. His new approach to foundations was published in 32, I think, the year I was born. And one of the things that he did was to take over Frege's ideas of making functions the prominent abstract object in his theory. But in the meantime, influenced by Max Newman, I was very glad to have met Newman in England, very lively professor who was one of the only people lecturing on logic at Cambridge. This was long past the time of Russell and Whitehead. And so he introduced Turing to the decision problem in first-order logic, and then Turing set about solving it in his way by defining what it means to give a computation that would work on such problems. And so then it turned out that Church's paper was published and received in England, and then Turing realized that he had been anticipated a bit, but things worked out very amicably between Church and Turing, even though they had competing ways of approaching the problems, and Turing came for 2 years to Princeton there. The sad thing is, both Rosser and Kleene had finished their PhDs and gone off to their first jobs, and Gödel, who had been earlier in Princeton at the invitation of von Neumann, went back to Austria and then had to escape with the train across Siberia. And so he wasn't in Princeton, and so Turing never met Kleene, Rosser, and Gödel, which is too bad because they could have had lots of interactions. But both Church with his theory of functions and Turing with his theory of machines then proved each other's versions, gave the same class of computable functions, as you know. And of course, what happened with Church's lambda calculus that he used for his definition of computability, Kleene found that people didn't really want to hear about it very much, and so he transferred everything over to his way of approaching recursive function theory just on numbers, number theoretic functions, which of course became the prime way of doing it. Church's solution to the decision problem for first-order logic, that is to say, given some axioms in first-order logic, can you decide whether some formula is a theorem or not? Church said, let's just write down, since we using things from Gödel and Kleene that worked out the details there, we only need a finite number of definitions in order to get to a non-recursive set in terms of number theoretic functions. So we just have to axiomatize that part of arithmetic using symbols for those functions to get something in first-order logic, which then would give the undecidability because of the non-recursiveness of the set being defined. Much later, influenced by Tarski and Mostovsky, Raphael Robinson came up with a very small fragment of arithmetic. I mean, you can't get smaller than this. A property of successor, a property of zero, the recursion equations for plus, the recursion equations for times, and it shows that in terms of fairly complicated logical formulae, you could get to that non-recursive set. Of course, much later, we know from Hilbert's 10th problem that you can just do it in terms of polynomial equations to get there. But there's a theory. Those students who've been suffering under logic, I mean, I think I could keep them sitting still long enough to explain this theory to them. It's not so complicated to do, thanks to Robinson's insights there. So that was Church's solution. Now, Turing's solution was to say, wait a minute, I defined the universal Turing machine, which then leads to a way of notating things for any computation, and therefore the non-recursive set. So let's just axiomatize the universal Turing machine, the action of the universal Turing machine. But if you ever suffered through Turing's paper or tried to make up your own universal machine, it isn't a lot of fun, because what he did, though it has philosophical significance, was to analyze the action of the machine into very atomic acts. And you have to sweat an awful lot on a single tape to get everything to come out. Now, later on, people, starting with Shannon, had lots of competition to get the smallest universal machine, and that's quite fun. I tried to find a snappy example on the internet. You can find so much on the internet these days. But I couldn't really find one that was really attractive. And of course, the trouble with the small machines is you have to encode everything very much in order to get to the universal property of it. So it doesn't lead to such snappy axioms for doing it. But of course, in principle, we understand that Turing solved the problem in that way. Now, Post had already thought of the idea that was pretty much equivalent to Turing's machine earlier than Turing,
but wasn't able to publish his results. And he and independently Markov in Russia came up with the idea that you can do everything in terms of very simple kinds of formal systems, which are just rules for specifying how you change one string of symbols, your hypothesis or antecedent, into another string of symbols and the consequence. And so Post then worked out, he actually used the Turing machines, that we can make this symbol manipulation into equations in a associative system there, and that the unsolvable problem would be just on the basis of the associative law there, and take some constant generators there. Does a set of equations in an associative system lead to another equation there? Of course, you use the rules of equality that Euclid gave us. If equals are multiplied into equals, the results are equal, to give those deductions there. And so it's really nice that that's an example of a problem. But still, if you take the universal Turing machine, it's a very long thing to write down what would be the unsolvable. I mean, when you think of the class of problems, you see it's unsolvable. But if you wanted a more specific example, it's the universal Turing machine again. In the meantime, and Church must have met Curry and Göttingen in about 1929 when Curry was working on his thesis there. Earlier, Schoenfinkel was a fairly crazy Russian and apparently disappeared into Russia after he left Germany, and no one heard about him. Schoenfinkel had formulated an idea of using functions that take arguments as functions and produce functions in a completely type-free way. And Curry took that up when he discovered Schoenfinkel's idea. He had independent ideas, and he incorporated Schoenfinkel. And then, of course, Church, with his theory of functions in the lambda calculus, they realized that it was the same thing to do things in terms of combinators and lambda calculus. I'm not going to try to explain lambda calculus there. The combinators are very easy. What Curry only needs is the constancy combinator k, which when given a constant value there gives you the function that always takes on that constant value. And then Schoenfinkel's combinator, and that's the key thing that makes things undecidable here, is that given two functions x and y, if you think of another argument there, you give that argument to x, you have a function, and then you compose that with y there at the same z there. See, what makes this undecidable is that the z gets doubled there. And so expressions are going to expand and may take you a long time to get them small again there, and that's the combinatorial difficulty. So this is an example of an undecidable theory in first-order logic, and an undecidable question is, does a term in K and S reduce to some fixed term in K and S? Excuse me. That's Church's numeral 0. I'm not going to really explain it, but just say, does a term reduce to some fixed given term? That's an unsolvable problem on the basis of those very, very simple axioms. I'm now going to give a different version of this. I'm going to try to combine Curry and Church and Kleene and Rosser and Turing together in one system here. The problem with Curry's theory here is proving it's consistent, by the way, but also the thing is it's non-deterministic. When you just give equations and you can say you replace equals by equals, you can replace the equals by equals in any place. And so it's non-deterministic where you do your next replacement. So what I'm going to do is to give you a very quick system here in the next few minutes where I replace things only at the left-hand end of the string. Now to make that left-hand end of the string stick out like a sore thumb, I'm going to write things in reverse Polish notation. So instead of writing f of x the way we usually do, I'm going to erase the first parenthesis and reduce the second parenthesis to a period, okay? But it's reverse Polish notation. It's a binary operation of application of a function to an argument. But I'm going to use another application of a function to an argument, reading from left to right, and said, wait a minute, calculate the value of x first, and then apply the function to it. You see, the first one says calculate f first. That may be a compound expression or function. Do the function first, and then pay attention to the argument. So I'm going to do it both ways there to have a deterministic system. So here's the syntax. Maybe we don't want to read it. I can just say it. We have variables, if you like, but we won't actually use variables. But constants, for the combinators, I have to add a Q combinator for a technical reason, never mind. Terms are made up out of the constants and the two application operations. A combination can no longer be reduced by the rules of the combinators if it doesn't have enough junk on it, because the rules of the combinators from Curry's axioms require a certain amount of stuff before you can make the reduction. And then just technically there, when you have one of these reduced things, you might have a chain of additional arguments there, which could start up other reductions there. And so that's just a syntactical name for things there. So here is Curry's reduction rules in my deterministic left-right way. If you have a reduced term followed by some other term there with a double dot there that says, oh, okay, you finished that first one, so now turn things around and start reducing the term and give it the argument there. So that's that way of being able to sequence which steps are done in which order. Now for K, S, and Q, K says do a cancellation, S says do a duplication and set things up one on top of the other. For Q, I have to have one there that says, oh, okay, we can do that reverse trick there. So I'm just making the double dots into a combinator here in order to have a simple relation between expressions and combinations. So the whole point, which Curry knew very well, is that no matter what gigantic formula you think of, you can always program into a single constant combinator so that if you give it the arguments x, y, and z, it will then reproduce by those reduction rules any formula in this notation. And of course, what Gödel and Kleene did was to see that the recursive functions in terms of certain numerals, certain expressions there, could always be obtained by reduction rules there. If you give it the expression that corresponds to one numeral and start reducing, it will eventually get to the value there. And so now, you don't need to read those. I hope I wasn't too fast there to say that there are certain syntax and reduction rules here. And now we just have to axiomatize that. Turing said axiomatize the universal Turing machine. I'm saying axiomatize the reduction rules. And so this is completely mechanical to write down word for word what I said informally about defining induction there as first order axioms. And so again there, if you formulate the problem of taking a constant term and asking will it eventually reduce until it comes to an end halt, that's the typical example of the undecidable problem. So this is the universal Turing machine. What I've done here is I've not made a stored program computer, right? I've made a stored computer program. Everything is expressed in terms of the syntax, and the syntax has both the programs and the tape, the amount of space that you want to use to do it. And so, therefore, it takes less axioms to do it. I thought of that 50 years ago. I wouldn't have revolutionized logic if I proved it. But I thought, thinking back historically here, that you ask yourself, how did people think of things and how did they come upon it? And so just like Schoolem missed the chance to prove the completeness theorem, Gödel didn't say it fast enough to give the Entscheidungs problem, but finally the penny dropped and the things can be expressed in a very direct way. Thank you for your attention today.
Saying is that not only do I appreciate this chance of congratulating Pat on his 90th birthday, but to thank him for a friendship that lasted half a century. I think I can illustrate how much give an example of how much I appreciate his friendship. Is one example is that he was my best man when I was got married to my late wife Merida. So that's an example of it. So congratulations and thanks. Now that's work. If you ask Dr. Name, I think Suppes to philosophy of science, I think the most likely response is, oh yes, set theoretical structures in science. And Pat has pioneered an approach to philosophy of science and perhaps philosophy more generally in terms of structural terms and the framework of discussing all those structures has been set theory. And I think this is the right approach. Pat has pioneered it, and he deserves tremendous credit for that. So, in some sense, I would say page with him, but saying that raises a further question, namely, if set theory is such a wonderful tool as it is, in Pat's view and mine, what can we say about this tool itself? From the fact that set theoretical structures are important, and that set theoretical methods are extremely important and useful, it doesn't follow that we must have a theory about this tool as on a par with ordinary theories of philosophy of science or logic. And this is what my title is all about. The title is borrowed from biology from Wittgenstein. I think Wittgenstein's philosophy is largely can be thought as being phenomenological. He said himself that you can say his philosophy is phenomenology, but he also said there is no phenomenology, but there are phenomenological problems. And in the same spirit, I would like to say there are set theoretical structures, and there are set theoretical problems, there are applications of set theory, but there is no set theory, at the very least, in the form of a first-order theory, in the usual sense. This is of course very radical claim, because in the last 100 years, set theory has been, by and large, with some exceptions, mainly cultivated as a form of a first-order theory. Cerebral Frankel is the best example of that, but the differences between different first-order theories don't really matter. And it's my thesis that this is not the right way of looking at set theory and its applications. And I have lots of arguments. I will run through them very quickly. You can see they are summarized in the handout. I have to skip much of the argument just to give you the outline of my thinking. But here are some of them. I have three main arguments. The first is from the nature of the axiomatic method, which is a very tricky subject, and it requires critical analysis, which I propose to do elsewhere. But the conclusion I reached here, both historically and systematically, that what happens in axiomatic theory is that you is not just deductive systematization, not just your application of logic, but something that is connected precisely with the idea of structures. Namely, we capture a class of structures, mathematical, physical, or whatever. We capture a class of structures as models of an axiom system. And what's the point? The point is that then we can study these structures that can be physical systems by studying logically the axiom system. And by studying it, I don't mean only deriving theorems from the axioms, because that's the least important part of the study, because by deriving deductive conclusions from the axioms, you can only establish those properties that all these structures that you are interested in have in common. Much more important, or at least as important, in fact more important, is for instance the question as to what structures are possible with it, given the axiom, given the truth of the axioms. For instance, if you have a physical system, it's not just, say, Maxwell's equations. It's not just interesting. It's not so much, or at least not only what kind of electromagnetic systems there can be, but what electromagnetic systems, structures are possible. And that's also a question that you can answer by studying the axiom and the equations. In principle, of course, you have to bring boundary conditions, but that doesn't change the logical structure, logical nature, conceptual and logical nature of the study. So this is what I take to be the essence of the axiomatic method. But if so, the idea of first-order axiomatization of set theory becomes extremely problematic, because what are the structures that are supposed to be studied in set theory? They are structures of sets, of course. But what are the models of first-order theory? They are structures of particular objects, structures of individuals. And those are different animals altogether. So the assumption that we can gain knowledge about structures of sets by studying structures of individuals, particular objects, is right from the beginning problematic. And I don't think it works. It's like building, if I may use only comparison, it's like trying to build a theory of dogs by building a theory of cats, and then call cats dogs. You can gain a great deal of knowledge about the physiology of dogs by studying other animals, but you don't get the full theory in this way. And I think this shows up in the actual set theory, because if you try to interpret strictly take say some of the theorems of all the theorems of first-order axiom system set theory, for instance, I think you can demonstrate some wrong, some false theorems. I could give some illustrations, but that doesn't, I will not go into them unless pressed on them. Now you can say, but we do have actually axioms or set theory. Don't they tell something about structures of sets? Well, if you look at them, I would claim that from this point of view, the point of view of the nature of the models, you can see that most of them, with some exceptions, they are not really statements about structures or sets. They are first-order assumptions that are trying to make the first-order models, structures or particulars that are models of axiomatic set theory, to behave like structures or sets. But I think you can show very easily that this will not succeed completely. The two exceptions are, of course, the axiom choice and the power set axiom. Now I have independently argument that you have to consider the axiom of choice as a logical principle. I have argument for that, and I think that has to be done, that can be done. The power set axiom, you don't need it if you don't think of set theory as a theory or subset theory of the universe. If you don't think that it has a domain of its own, if you think of it as a method and not as a theory. So that's the first kind of argument that they propose. The second one is more technical and subtle, and that concerns the current formulation, the formulations of set theory not only on a first-order level, but in the traditional, the accepted use of first-order logic. Because if you do that, then you can't do everything you want to do in set theory. And this is illustrated by what I've shown here. The point is simple but very deep. It turns on the nature of the logic of continuums. If you, in axiomatic set theory, you introduce new sets by comprehension principle. What limitations it has to have is a different matter, but this is how new individuals, how new sets are introduced, how their existence is asserted by the comprehension scheme. So, what's wrong with that? There's something deeply wrong with it. And it has to be pointed out. Because if you look at the one-star formula there, what do you see there? You are essentially, you can say, perhaps this can be turned into a literal matter. You can say that you are essentially defining the set X by means of this formula, by giving a condition on the membership. Well, if you look at it, that definition, if you think it in terms as a definition, then this definition must not be certain. You must not be referring back to the set to be defined in the membership condition. But now, what is the membership condition, the D of Y like? It's a complex predicate of Y, usually, typically containing quantifiers. Now, quantifiers don't only express, their semantics is not exhausted by the ranging over class values. By by the dependence, formal dependence of quantifiers on each other and on constants. You express, you can express it, you have to use this to express on the first level, dependencies of variables on each other. So quantifier dependencies are means of expressing the actual, the formal dependence of quantifiers on each other is a way of expressing the actual dependence of variables on each other, namely those that are more quantifiers. And therefore, the quantifiers in D must not depend on the quantifiers EX and AY. But in the usual notation, they those quantifiers are within the scope of this EX and AY. This is circular. This is what Poincaré originally meant by the vicious circle principle. This is something that shouldn't be done. And unfortunately, I'm here making historical claims, this observation on Poincaré's was not understood, and it was seen that it was some kind of dependence, but it was misunderstood by Russell and others. So, and moreover, with its scope conventions, this kind of independence cannot be expressed on the ordinary first order logic. So you cannot express the comprehension principle in well, this is a little more complicated because the AY just must depend on the EX and so on and so forth. There are some other similar things. Well, anyway, this is the second kind of argument. The third one is perhaps more, is perhaps less novel, but yet important.
Yeah, just a few minutes.
Yeah, okay. This is the last one. The third one is perhaps the most relevant to Pat's use of set theory, and that is that set theory, first order set theory, with the usual logic, usual first order logic, cannot serve as its own or model theory, because for model theory you need a truth definition, and by tasking this out, you cannot give a truth definition for a first order theory in the same theory. So not only is it too much to think of set theory as a universal kind of woman's model theory, it's not a universal model theory, it's not even viable model theory for itself. And this is again actually due to the same logical fact that logical things that I mentioned in terms of the comprehension principle, truth definition of this truth condition would in a self-applied set theory would look like this, the double star formula, and there are also the quantifiers in B must be independent of the quantifier AX, and that cannot be expressed in the usual first order level, which by the way expressed by the tasks T scheme works, because there you don't have quantifiers, you have just substitution instance of the expression like this. So perhaps that's enough, radical enough. So my conclusion is to exaggerate it, of course, is to modify Wittgenstein's dictum and to say there is no set theory, at least at the first order level, with the usual first order logic. There's no set theory in that sense, but of course there are set theory constructions that they are enormously important, and they've been successfully studied by that. So, thank you.
I'm going to talk to you today about work done over the past several years with Pat on semantics in the brain. And no, I didn't upload the wrong image. It is a map of Europe. It's meant to be there because I'm talking about the analysis of electroencephalographic data collected while participants were processing statements about the geography of Europe. The overall aim of the work is to see if we can detect evidence of semantic processing. So I'm going to jump right into the data, which should make Pat happy. But let me first just briefly say what made me very happy a few years ago was when I was having lunch with Pat, and he told me about his brain research. I was a student of Pat's in the 1980s, and he did some work on language and learning for robots. And when he offered me the chance to work with him on language in the brain, I didn't hesitate. There is no one who does science with such philosophical verve, and no philosopher who so enjoys performing theoretically grounded computations on somewhat messy data, getting the results and looking at them and trying to interpret them. It's an absolute joy to work on that with him. So, right on to the data. This is the experimental setup, and these experiments were conducted before I came on board. Briefly, a computer presented 48 spoken sentences to each participant, 10 randomized blocks of all 48 sentences, so the 480 trials. That's the data we got to work with. The sentences are all about the geography of Europe, very straightforward. The forms of the sentences on the bottom there, sentences such as the capital of Italy is Paris, which is false, and Spain is west of Russia, which is true. What were the participants doing during this experiment? They were asked to determine the truth or falsity of each statement while the EEG recordings were made and their responses were collected. That was a set of city names, country names, and the sentences were simply about capital, largest city, north, south, east, west. In approaching this work, the two fundamental claims established by Pat in his 2009 paper, which are important to get clear. And that's a paper on partial orders of similarity differences invariant between EEG recorded brain and perceptual representations of language. The two claims establish that when brainwave recordings are time-locked to the presentation of words in a sentential context, as they were in the experiment, as each word is presented to the participant, the time is noted. So when brainwave recordings are time-locked to the presentation of words in a sentential context, segments of those brainwaves, after appropriate transformations, can be identified as representations of those words. And these representations have approximate invariance across language speakers and across a variety of sentential contexts. As Pat points out, that being the case, it'd be very surprising how we communicate with each other. Secondly, significant structural similarities can be found between language constituents, and Pat was working a lot with phonemes, and the brainwaves identified as their representations. What I show today is that structural similarities can be found between the brain data and the language data at the semantic level, and new methods to measure the strength of these structural similarities. And what this allows us to do is to assess the relatively better fit with the brain data of one semantic model over another. The three semantic models we're going to look at, and each one of them could be discussed for 20 minutes on its own. I trust a brief description will give you a sense of what they are. Many of you perhaps know WordNet, George Miller's work at Princeton with colleagues. It's a database of English organized around what we call sets of cognitive synonyms. And each word has several senses, and so you can choose the senses you're interested in, and you can so strongly restrict the context of the words that you're interested in. Latent semantic analysis is a statistical method to extract measures of word similarity from selected sets of documents, such as novels, newspapers, articles, psychology textbooks. So the context, again, is restricted, somewhat less so, not to what it's about, but to documents that are about certain things. And I say that because in contrast to the third model, which is a probability-based method that extracts word relations from the internet, with no restrictions on context, not even how that language is used. You don't always get sentences on the internet, you get word farms produced. So, just to make sure it's clear, WordNet will have different senses, such as for Paris, the capital of France, the plant, the character and mythology, and lest we forget the town in northeastern Texas. Multiple word senses, the words are all connected to each other by links, usual, more specific, less specific, hyperlink, and is an instance of, has member. Those are the kinds of semantic relations that are connected. We're really just look at the is more specialized or is less specialized, such as a vehicle and a car, a vehicle and a truck. I point that out because what we're going to be looking for is measures that show us how similar one word is to the other. And given the structure of a word, there are various similarity measures that have been devised. I use 5 of them and take the average. One, for instance, measures the path length between 2 words. So 2 words like car and truck, up in, think of it as a hierarchy, would go immediately up to vehicle. You can have a pony, which is also be a mode of transport, but it's animate. These are inanimate things. You have to go right further up the hierarchy and travel back again. So it's a longer path, more distance. That's just one of the 5 measures. Latent semantic analysis is the interesting thing about that is that claims have been made about its connection to human language. This is interesting. The similarity judgments produced by latent semantic analysis, it's shown to correspond to, in some ways, to human similarity judgments. For example, after training on about 2,000 pages of English text, it scored as well as the average test taker on the synonym paths of part of a test, as is the English as a foreign language test. Even more interesting, after training on an introductory psychology textbook, it achieved a passing score on a multiple choice exam. But of course, it's not without its detractors. It's merely a statistical technique to measure how similar the context of use are for 2 words, and just in terms of the words that are around it. But it does give some surprisingly interesting results. The Google-based similarity score is derived from the Google distance, and it can be, this is extracting data from the internet using any search engine. Intuitively, the Google distance, normalized Google distance, is an estimate of the symmetric conditional probability of co-occurrence of the words X and Y, and it's transformed into a similarity measure in a straightforward way. So, what can we do with these? Now, LSA and the Google-based NSS provide straightforward measures of similarity. That's what they do. But for WordNet, as I explained, there's several and we use a combination of those. Here we have, for this set of words, London, Moscow, Paris, North, South, East, West, Germany, Poland, Russia. This is the semantic similarity matrix derived from WordNet. What we did here is we used only the senses relative to the geography of Europe. So one of those Paris words, and then North, South, East, West had several senses that were left out. So we restricted the senses that we took and took these similarity measures between them. So that's the kind of thing we can do with the language data. I showed you the WordNet one, show you one for LSA and for Google-based NSS, completely similar. So what are we interested in doing? We want to find structural models for the brain and language data. What we do, first step is to analyze the brain data using a statistical model that predicts to which class of brain data sample belongs. I used a discriminant model, courtesy of Marcus over there, who you're going to hear from more later. So taking these 10 words, they gave us 640 data samples classified into 10 classes. So more generally, T brain data samples, S1 to S10, are classified into the N classes, W1 to Wn, and roughly speaking, those classes represent prototypes that we compare the actual data samples to. If a test sample Si is classified as W1 and and WJ have a minimal similarity difference compared to the other possible classifications. So here we have 640 brain data samples classified, and we look at the confusion matrix, standard confusion matrix from the classification, and from that we get the estimates of the conditional probability densities. So now we have for the brain data a similarity matrix akin to the ones we have for the language data. It's useful to see what's going on in that similarity matrix. Here's a hierarchical cluster tree computed from that matrix we've just seen. So that was a classification, and this is how the classification grouped the words, really quite pleasantly with the east-west, north-south together, the cities together, the countries with Germany just a little confused. Now, every single trial classification produces its own conditional probability density estimates, and so it gives rise to its own similarity tree. Here we have one that's not quite so well behaved in terms of cities and countries. Back to the semantics for a moment. We had the word net similarity matrix. Here's to get a sense of what's going on there. Here's a similarity tree, a hierarchical cluster tree, which is very neat. The word net does a great job. It's very well organized. It was manually crafted. This is for the latent semantic analysis. Here's a cluster tree from its similarity matrix. It just has Moscow grouping itself with those three countries. And here is the Google-based normalized similarity scores, which is very much less well behaved. So some of those similarity trees, and on some classification runs, you get some fairly intriguing congruence, it seems, between the brain and semantic data. But where exactly does that congruence lie? And can we devise a quantitative measure of the nature and strength of that congruence? Well, yes, we can, thanks to the work Pat has done. So, having computed the conditional probability density estimates, we can, for each word, define a returning relation R prime, such that it holds if and only if it's between W and W1 and W2, and this is for the word W. This relation holds only if W's one's similarity with W is smaller than W2's similarity with W. So R prime is actually an ordinal relation of similarity differences. It's a partial order that is irreflexive, asymmetric, and transitive. And we do exactly the same for the semantic models. We give partial orders. And what we're doing here is actually have two structures. That's the article I kept on finding myself going back to with that. That we have a relational structure, R prime, for the brain data, with all its partial orders, and a similar one for the language data. In fact, we have three of these, one for each of the models. And what we're going to do to compare the brain data and the language data is compare the partial orders of each structure. First of all, we just use Spearman's rank correlation coefficient, which we interpret in the usual way to determine if we have a statistically significant correlation or not. And for those instances in which the brain and language partial orders are significantly correlated, we find the partial order that is invariant with respect to the brain and language data. And here are two examples, both with respect to Paris. So these organize in fairly nice ways, the directions at the top there, then the countries, then the cities. The one on the right, south, its similarity differences, its semantic similarities there was not an invariance between the brain and the language data, so that lies outside of this invariant partial order. So these are just two. As pointed out, every single classification run will produce its own partial order, its own probability density estimates. So what we did is performed a series of computations, let's just say 30, that's what I'm going to show you. Computed 30 single trial classifications of the data, in this case 640 data samples, using random resampling with replacement. For each classification, we find the partial orders that are significantly correlated, brain and language, and then for each of those, as I explained, we find the partial order invariant with respect to both. We do that for WordNet, latent semantic analysis, and rule-based NSS. And these are the results we get for 4 subjects. So S18, S24, S10, and S25. The one on the left, S18, out of the 300 invariant partial orders, significant invariant partial orders that could have been found, when WordNet was used as the language model, we found about 260. For LSA, about 160, and for NSS, just over 100. And for the other test participants, we found a similar staggered result. WordNet gave the largest number of significant invariant partial orders, except for the subject number 25, which I've shown here, which had this little bump up with the NSS. Interesting, that subject only got 60% of the geography questions correct. The one on the far left got 91%. So, I don't know if it's got anything to do with it. So, the original conclusion I drew from these results is that the brain data reveal evidence of context-sensitive processing, because the number of statistically significant structural similarities found between the brain and language data is greatest when the language model is strongly restricted to be contextually relevant, that is to the geography of Europe. For a language model that is less subject to contextual restrictions, such as LSA, the brain and language data exhibit fewer statistical significant structural similarities. And for a language model that is subject to no contextual restrictions, there are even fewer statistically significant structural similarities. Lately, I've been asking, though, do these results instead tell us something about these semantic models? Is it perhaps that WordNet is a better model of some aspect of language processing than LSA? Is it a better model of how the lexicon is organized in the mind, a better model of semantic knowledge? So it's not altogether clear what to conclude, but it's certainly interesting. Those are the results I wanted to present today. Now, most people have been ending their talk by saying thank you to Pat and happy birthday, but I'm going to take another tack, because as we know, Pat likes nothing better than a good argument. So I'm going to end on another question, which is picking up a conversation Pat and I have been having for a few years, and we have not yet resolved it, as to which are the best experiments to follow up with here to tease out what's happening. And I hope we pick that conversation up again and come up with a good answer.
Would you like to respond?
Well, I'll just make one comment. Colleen had to persuade me to do this, all this analysis. I was skeptical that the semantics would show much. Thinking, of course, you've got to have these results for the sounds of the words and to get the phonemes right, to recognize what they are. And so quite surprising, the actual similarity data we got on the purely semantic considerations. And she was very persistent in denying that I could possibly be right and thinking that wouldn't be so.
But I still haven't persuaded you to do the experiment.
And we'll take one quick question there.
How can you, excuse me, how can you exclude that there's another factor involved, which is not semantic, namely word length? So the direction terms are all one syllabic, the geographical terms are 2 or 3 syllabic. You would say, no surprise, that the brain computes more similarity between the one-syllabic ones than between the one and the 2 or 3-syllabic ones. That is not semantic, it's phonological.
Yes. A very good question. How do we exclude other confounding variables? And there's this number of syllable ones. There's also the grammatical category, because north, south, east, west are very different grammatical categories. In fact, I looked at both of those. I looked at both of those questions, confounding syllable and confounding grammatical category. You can do the grammatical category question by simply restricting yourselves to questions or to all the statements that, not the ones about capital of and largest city of, because then the cities and country names are all in the same syntactic position. And then I did a lot of tests of the same syllable lengths, because some of the city names and country names are one syllable. So I did a lot of tests only using that data. But there still could be other confounding effects, and that's why we need to have well-designed follow-up experiments to try to tease those out. So find some words that can easily be used in 2 contexts and run experiments on that. But these are surprisingly robust results.
And on that note, let's think of
So it's a pleasure for me to be here and Pat and have a chance to participate in your 90th birthday celebration. I came to Stanford in 1966, so I haven't known Pat as long as some other people. I mean, maybe I'm 10th on the list or whatever it is. In any event, I spent a lot of time in Ventura Hall, and this is a kind of a well-known photograph that was taken of people who were part of mathematical psychology. Pat should have been there in the photo, but for some reason he was missing that day, and his name appears in the list of people who are missing. But you do see a number of other people who were very close to Pat. So there's Bill Estes, who was mentioned earlier by Pat in this symposium, the student of Skinner's, and there's Dick Atkinson, and there's Gordon Bauer, who was a young professor at Stanford, and here he is in the audience still. Again, today honoring Pat. So I joined a group that I didn't quite fit in very well with, but let's see, how do I advance this? The down arrow. All right, I'm hitting the down arrow.
Space.
Space. Oh, there, okay. So, but whatever, there I am. And you can see times were very different at that point. I came to Stanford and started working with Dick Atkinson and finished my master's thesis, but then began working with Pat on computer-assisted instruction and mathematics education. And I mean, I was very intimidated by him because this is his academic lineage. And in fact, at that point, I don't think I was allowed to call him Pat until after I had gotten my PhD. So it was always Dr. Suppes or Professor Suppes to me during that time. Now, we did write a couple of papers together. And so here's one of them, published in 1969. Here's another paper that we published together in the Journal of Educational Psychology. I do have to say I just accessed Google Scholar to find out that this paper has been cited 50 times. Nowhere near Foundations of Measurement, which was published around the same time, which has been cited at least 2,500 times. So I have not done very much for Pat's citation count. However, it was enough to get my PhD and to be added to this illustrious lineage. And for the other Pat Suppes students, if you'd like to have a copy of this and pluck out me at the bottom and put yourself in, just send me an email. I then, oh, by the way, I was started my career in New York City, and the paper, the Journal of Ed Psych paper that's been cited 50 times, was something that we worked on after I'd already moved to New York, and one of my, fondest memories of Pat is he was so busy doing other kinds of things that he had to do in New York that the only time we had to work on the paper was while he was taking the taxi from Manhattan to Idlewild, now known as Kennedy Airport, at which time we would work in the back of the taxi, and then he would hand me the money to give the taxi driver to take me back into the city. But we did get that paper done. At this point, I departed from, I guess, my intellectual roots, although I continued to use many things that I learned from Pat, like multiple regression and stepwise regression, and to apply them to other problems. But I got very interested in legal cases. And so throughout the last 40 years, I have devoted a lot of attention to legal cases and considered the application of my scientific work to legal cases. I'm particularly interested in two classes of cases. The cases where a crime really happened, a murder, a rape, whatever it is, somebody's been identified as the person who committed the crime, and we now know that there are a growing number of cases of wrongful conviction, people who spent 5, 10, 15, or more years in prison for crimes that we know now they didn't do because DNA testing has shown they are actually innocent. And when these cases have been analyzed, the major cause responsible in 75 to 80% of the cases is faulty human memory, faulty eyewitness testimony, and so I've been studying that issue. Then in the last 20 years or so, I got very interested in these repressed memory accusations. And I want to be very clear what I'm talking about here when I talk about the repressed memory accusations. I'm not talking about a person who's known her whole life that she was molested, or he, and maybe 20, 30 years later got the courage to tell a friend or a trusted therapist about it. I'm talking about one specific kind of situation, and I think this family exemplifies that situation. The dad, Gary Ramona, was an executive with the Mondavi winery. When his world came crashing down, his daughter went into therapy, and there she learned something she never knew before, namely that her father allegedly raped her between the ages of 5 and 16, forced her into many rapes, sex with the family dog, all allegedly repressed into her unconscious until this therapy made her aware of it. From my analysis of a vast attempt to document this or find support for the idea of repression, there is no credible scientific support. And yet these kinds of accusations were being brought in criminal and civil cases by the hundreds and hundreds over the last couple of decades. And as I would be involved as an expert witness in some of these cases and listen to some of the bizarre memory stories that were being offered as evidence in these cases, I was prompted to rewrite that solemn oath that witnesses take when they get on the stand. I think this is a much more apt oath that witnesses should be swearing to tell the truth, the whole truth, or whatever they think they remember. But so far, I haven't, much as I've been pushing this, it hasn't caught on yet. So I've developed a couple of paradigms that I think map into these two kinds of court cases. First, there's the misinformation paradigm, as it's now known in the literature. And here, experimental subjects come in, they see an event, might be a simulated crime or an accident, they get some post-event information about what they saw, and then they're tested. And that post-event information is typically misleading in some way. And I think that taps into the first kind of case where there are memory errors. But there really is an event that happened. There really was a rape. There really was a murder. But to map into this other kind of case, where a person is coming up with like 10 years of brutalization and forced bestiality, we needed to go a little further and try to plant rich false memories, as they're now called. And to do this, we don't start with an event, but we ply people with suggestions about their past And then we test them to see what they remember about their childhood or about their more recent past. And so for that first type of paradigm, one of my earliest studies that you can often read about in introductory psychology textbooks today, we showed people a simulated accident where a car goes through an intersection with a stop sign, and by asking a single leading question that insinuates that it was a yield sign and not a stop sign, we get lots and lots of people to believe and remember they saw this scene. Even when the truth is staring them in the face, they choose the scene that corresponds to the misinformation. And so now I've given you a brief summary of 35 years of research on the misinformation effect. If people see an event and get misinformation about it, it impairs their memory performance. But to now turn to that second type of case, the many cases that have been tried in court where people have developed these very, very rich and detailed false memories. Rich, detailed memories of being forced into satanic rituals, or sometimes rich and detailed memories of things they don't get into court cases, but things like being abducted by aliens and taken up on spaceships. There are actually a lot of people who have such memories. We needed to find a way to plant richer false memories, not just tinker with the detail here and there. So how are you going to do that? You're not going to be able to get it through the Human Subjects Review Committee to plant false memories of 10 years of rapes and bestiality. So we needed an analog, something we could plant that would have been, if it had happened, at least mildly traumatic for the subjects. And so at some point we came up, I and my graduate students came up with the idea, why don't we try to make people believe and remember when they were 5 or 6 years old, they were lost in a shopping mall, that they were frightened, they were crying, they were ultimately rescued by an elderly person and reunited with the family. And after 3 suggestive interviews where we told our subjects that we talked to their family members, that we learned things that had happened to them, we convinced about a quarter of our ordinary adult subjects to have a complete or partial false memory of being lost in the mall. So the critics came back and they said, well, wait a minute. Getting lost is so common. At least show us that you can plant a false memory for something that would be a little bit more bizarre or unusual. And other investigators came along and they used our lost in the mall methodology, and they planted, for example, you went to a family wedding, you were 5 or 6 years old, you knocked into the punch bowl, and you accidentally spilled punch all over the parents of the bride, succeeding with about a quarter of their subjects in getting them to develop this false memory. In another study, you were a victim of an indoor accident, a serious one. You were attacked by a vicious animal. You nearly drowned and had to be rescued by a lifeguard. Well, the critics said, you know, these are pretty strong forms of suggestion. We talked to your mother said these things happen. And we who do therapy, the fraction of people who are doing certain kinds of therapy, we don't do anything that's that strongly suggestive. Well, they may not have been doing anything quite that strongly suggestive, but they were doing other kinds of things that were perhaps more subtly suggestive, but were also capable of leading people to false memories. So guided imagination. You don't remember who abused you, but you've got all the symptoms of someone who was. Why don't you just close your eyes and try to imagine who might have done this? Dream interpretation. Taking the material that the patient or client dreamed about and interpreting that as evidence of sexual abuse. I mean, I've had court cases where she dreamt about a snake, the therapist said that was a penis. She dreamt about a serpent, the therapist said that was a penis. But when I had my case in which I testified where the patient dreamt about a cinnamon roll, and the therapist said that was a penis. I thought, I don't get it. But this is one of the good things about cross-examination, because it was there that we were able to find out what was going on in the mind of that therapist. It was the goo on the cinnamon roll. The goo. So I know you never think about cinnamon rolls in quite the same way. Exposing people to other people's information. Supplying them with false information about themselves or exposing them to doctored photographs. All of these techniques can lead people to develop false memories. In terms of those doctored photographs, I'll just mention one of my favorite studies was actually done by a former postdoc of mine, Marianne Gary, and her collaborators. And they used the kind of lost in the mall technique, but they did it with photographs. So they took a photograph from the family photographs of the subject when the subject was a kid. And there's the subject with the subject's father. And they photoshopped it into a hot air balloon ride and then handed the doctored photograph to subjects along with real ones. And by the time they were done with this, half of their subjects fell for the suggestion in the doctored photograph and started to remember this experience. We did something similar with public events, and inspired by this doctored photograph work, about a year ago, Slate.com published a long article called The Memory Doctor, which is about a lot of this work on memory distortion. And to first gather a little data from their readers, they showed their readers some photographs. And so they showed a photograph of President Obama shaking the hands of the president of Iran. And a number of people said, oh yeah, I remember that one. How about you remember when Roger Clemens was visiting President Bush on the ranch during Hurricane Katrina? A number of people said, oh yeah, I remember that one. Well, they couldn't have because they were created through Photoshop. So it was really someone else who was visiting President Bush, but Roger Clemens' photo was photoshopped in. And our president never shook the hands of the president of Iran. It was also created through Photoshop. And here are the data. This is really to die for. 5,000 subjects gathered in 1 week from Slate.com. And you can see from the light blue bar, about 15% said, yes, I remember seeing Clemens at the ranch. And the pink bar on the right, over 25% remembered the Obama handshake. And they don't just say, yeah, I remember it. Many of them go on to provide additional details. Big Astros fan, live in Texas, very much remember this, said one of the subjects who fell for the Roger Clemens photo. We recently got the data, the 5,000 subjects from Slate.com, and I and my graduate student have done a little bit of analysis here. It turns out there is political ideology correlates with how commonly you make the mistake. So it's the liberals who are more likely to fall for the Roger Clemens Bush photo, and it's the conservatives who are more likely to fall for the Obama handshake. Let me just say, I have been attacked. Another common thing you hear is maybe these things really happen. Not with the doctored photos so much, but maybe the subject really was lost in the mall. Maybe they really were attacked by an animal, the parent didn't know it, or the parent forgot, and you have revived a true memory rather than planting a false one. And to respond to this, I and my students have said, well, we got to plant some things that would be implausible or even impossible. And so in the implausible area, we planted a false memory that on a childhood trip to Disney, you had your ear distressingly, disturbingly, and persistently licked by the Pluto character, succeeding with a significant minority of subjects. And the critics said, you know, maybe it really happened. Pedophiles like to go where they work where there are lots of kids. Maybe, you know, somebody did run into an ear licker. And so that was the genesis of our work, in which we said, we're going to plant something impossible. Like you met and shook hands with Bugs Bunny at Disney. Impossible because Bugs is a Warner Brothers character, and when the LA Times wrote about this study after I presented it at the AAAS meeting, the editorialist wrote the Wascally Wabbit would be arrested on sight if he tried to go to Disney. Well, we have continued to learn as much as we can about the creation of false memories. We've been studying the consequences of having a false memory, and I can tell you they do affect, they have repercussions for people, they affect future thoughts and intentions and behavior. That when we try to see if we can find means of discriminating true from false memories, we find it's very difficult. The false memories look very much like true ones. I even collaborated recently in an fMRI study that showed that even though there's a little bit more activation in the visual cortex when people are recounting a true memory, and a little more activation in the auditory cortex when people are recounting a false memory, the overwhelming impression here is the neural signatures are very similar. We've done recent work on who is susceptible and who is resistant with a large collaboration with Chinese colleagues. We've found that to some extent, if people score higher on standard tests of intelligence, they are somewhat more resistant to these kinds of manipulations. Here's the one message that I've learned in now 35 or more years of working on these issues, doing these experiments. Just because it's vivid, detail, expressed with confidence and emotion, doesn't mean it's true. I have discovered that I really intellectually have a lot in common with Patrick's great-grandfather, Hugo Munsterberg. He was a psychologist at Harvard who wrote a book called On the Witness Stand, published in 1908. And he was very interested in seeing science, the science of psychology, be applied to the legal system. He received, a lot of, he was controversial at the time, but I was very proud, I'm very proud to say that I did, there was just a reissue of that 1908 book, and I got invited to write the preface for that reissue, so I was quite honored by that. So thank you, everyone, and Pat. And Hillary's only in there because I was going to tell you a story about her, but I should have taken her out. And happy birthday, Pat.
When a medical student decides to specialize in psychiatry, he usually does it on the basis of courses he's had or of some research he's heard of, and he got excited about the research. So he has a theoretical view of what psychiatry is or should be. My first dilemma is the theoretical dilemma. We have a common joke among psychiatrists. We say that being attracted to a theory is like being attracted to a woman. You fall in love, you ignore the rest, you become a believer, you are not aware of being a believer, you think your belief is science. What do you believe in? Either the brain or the mind. The believer of the brain, in the brain, or in the physicalist approach, if you wish, claims to be a materialist. He does molecular psychiatry. Psychiatric disorders have, he knows that, causes in the brain. He will have a domain of research like the genetics of autism, and if he publishes in his publications, you will find statistical analysis, eventually evidencing links between specific genetic polymorphisms and behavioral phenotypes, such as cognitive deficiencies. That's for the first believer. The other believer claims to be a humanist. He believes in psychologically oriented psychiatry. He is interested in the historical antecedent of his patients' troubles. Language is his means of communication with patients. He will listen. He will try to empathize with the patient's mental and emotional experience. And if he publishes, he will publish case reports. Those kind of psychiatrists are so different from each other that you would want both parties to merge and work together and do something creative together. But that appears to be extremely difficult. Eclecticism is extremely rare. I give a little quotation here. There is a document. I give a quotation from a book written by Salomon and Mexico. The book teaches, or is supposed to teach, the psychiatric diagnosis according to ICD-10, that is according to the International Classification of Diseases, Chapter 5, which is very close to DSM. But as you read what they say, you read that in order to prevent future psychiatry from dissolving in a number of methodically defined subunits, and to further strengthen person-centered diagnostic approaches, we strongly need the historical perspective. Those are humanist psychiatrists, and they want to reunite psychiatry under their version of humanism. So they consider that the other party is dissolving psychiatry. The other party is the molecular psychiatrist. That's the first dilemma, unresolved so far. My second dilemma, I call the relational dilemma. The medical student who has chosen psychiatry will wonder, he's filled with theory. He's learned a lot about psychiatry, but one day or another, he will have to relate to real psychiatric patients. For example, in the emergency room of a general hospital. I've done that for 25 years, one day a week. There is two ways of relating to a psychiatric patient who was, for example, brought in by the police and lies in the emergency room. Either you treat the patient as another you, or you treat the patient as an irresponsible he. First way of communicating to the patient. You address the patient as a person who is suffering of an ailment that she is unable to deal with by herself. The fact that the patient was brought to the hospital means that she's asking for help. And your kind of help is an appropriate possible solution to the patient, and you let the patient choose. Or if the patient resists, you will tell her that you will force her to be hospitalized, for example. That was my personal option when I did the work. But there is another way of relating to the patient. These other ways, this patient is out of her mind. she's intrinsically sick. Discussing with her is wasting one's time. You have to make decisions for her. In that line, you don't talk to the patient. You talk about the patient to nurses, for example. You prescribe an injection. And you make the decision that the patient will be locked in a psychiatric ward, or that this patient will be put in bed until she's sobered up because she's maybe full of alcohol. That's your decision. This second dilemma, the relational dilemma, is the same as the first dilemma. Because there is a fraction of psychoanalysts who assume that the psychiatric patient has chosen an existential posture that is mistaken. The patient is locked in that posture, and the patient is wrong. For example, that patient is locked in a paranoid, existential paranoid posture. When you believe that, the objective of psychoanalysis will be to evidence his mistakes to the patient and bring him to correct his mistake or his mistaken choice. But while he is locked in his position, you treat him as an irresponsible he. He does this or that. You can't communicate the same way if you believe that. There is a long tradition in psychiatry of considering that patients are not free and that psychiatric disease is a pathology of liberty. That's why in some countries, systematically, psychiatric patients are judged irresponsible. If they were violent or something, irresponsible. That was the second dilemma. My third dilemma is the therapeutic dilemma. This dilemma illustrates the detour. My left hand ignores what my right hand is doing. What treatment will I prescribe? Either drugs or psychotherapy. In most cases, both. But my left hand ignores what my right hand is doing. My right hand prescribing drugs. And at the same time, my right brain is telling the patient that she is in need of psychotherapy. That's quite paradoxical. I think it's the product of a history. Until 1949, psychiatrists had practically no treatments of mental illness, except radical treatments like lobotomy that had been tried. And suddenly, within one decade, from 1949 to 1959, all psychotropic agents were discovered. Neuroleptic drugs, antidepressants, anxiolytics. From then on, there is virtually no consultation in psychiatry that does not end with a prescription of some chemical. Even though chemical theories of mental illness have failed on the whole. But psychiatrists who received those miraculous drugs had no knowledge of chemistry, absolutely no knowledge of chemistry. They prescribed miraculous like miracles. There have been fashions in the prescription of psychiatrists. Around 1970, that fashion was psychoanalysis. And I quote here Garcia saying, in the past 40 years, largely under the impact of psychoanalysis, dynamic psychotherapy has become the principal and essential curative skill of the American psychiatrist, not only the American, by the way. Then, around 1990, psychiatry turned molecular. Very fast. Molecular, biological, and bye-bye psychoanalysis. Young psychiatrists now who are taught biological psychiatry and molecular psychiatry, I recently observed that as a result of that, of being told that they are rediscovering Binswanger. They read Binswanger. They are fascinated by Binswanger. That is by the, I was going to say the worst kind of psychoanalysis. I was talking about the one that thinks that people are locked in an existential position. And so young people in psychiatry now get tired of biological psychiatry and go back to the other end of the other branch of the dilemma. We can only hope that the dilemmas will come closer and work with one another, but so far we haven't seen that. Thank you for that.
I'm going to, after it's a bit intimidating to talk after such people before me. First, I apologize for my accent. I hope everybody can understand. I will not present a specific paper, but do a little tour of Pat's lab on the brain, the Suppes brain lab, and talk about work we have been doing since I'm here in 2001, but the lab actually started about 15 years ago. And I will go rather superficially, because other members of the lab are going to talk in more detail. So, quick tour of the lab. So, what is the Suppes brain lab? The Suppes brain lab is mainly studying recordings of the brain. Most of our recordings of the brain are electroencephalogram, EEG, and you can see a setup. That's a new setup with a lot of electrodes, but we used to work with more older setups before with only 31 sensors. Just a view picture. And I'm going to show data. So this experiment was a subject seeing on the screen either a sign stop, a big sign stop, or hearing the word go. With no, I put the word go because to show you, but it was purely auditory. And it was actually part for us. And you can see the recording of the brain waves. This is EEG. And you can see visually that actually the presentation of the stimulus does have some impact on the EEG. What's not surprising, because the brain has to deal with those stimuli. And this is a very simple experiment that is not that interesting in terms of language, but it's an experiment we use mostly for methodology, to improve the methods. But it's the one where you can actually see the impact of the stimulus directly on the EEG. In most cases, and in language, it's not that easy. So I just wanted to mention people that work at the lab before I arrived. So when the lab started in 1997, and back correct me if I'm wrong, you have Zhongling Gu and Bing Han and Julie Pelboim. They were before I arrived to the lab, so I meet them once, but I don't really know them. But the lab was well alive before I arrived in 2001. So I have only one slide on the method, and I'm going to skip all the math. How do we analyze the data, the EEG data? It's in general in two steps, two main steps. First, we do some inverse processing where we identify sources that can be inside the brain or outside the brain by statistical meaning. So most of the methods are maximizing some function of such as joint entropy. And it doesn't do a perfect work, but in most cases, it actually helps the analysis. And then we use a variety of methods for classification, from the very basic ones to more advanced regression methods or nonlinear methods. I'm not going to talk too much about that because I know two of the speakers are going to give me. So here just an example of classification. So here you have the stimulus. Here you have one of those independent sources that we pick. I just pick one of them, one that actually helps you classify, and we are pretty confident it actually comes from the brain. This is just a map of the probabilities for the stop. So the more red, the higher probability that is the stop. And here you have actually the likelihoods with the actual classification from the brain. So you see that in this experiment, we are able to classify at a high rate. In some subjects, we actually get 100% classification rate on unseen data. So we set the model, the parameter of the model in a set of data, and we test it on an unseen set of data. So the result you have here are on unseen data. And this one is not 100%, but is more than 90%. And you can see that when you have a visual stimulus, we have something consistent with the visual cortex that is at the back of the head. And when you have an auditory stimulus, it's less clear. The auditory cortex is on the temporal side of the head. So this is just an illustration of the method we are using. So I'm going to talk about some results. So actually, the first paper I worked at the lab was not EEG, but MEG. So it's a magnetic version of EEG. We did not do a lot of it because it's a lot harder and a lot more expensive to run this experiment. And we have had an experiment with 9 words. First, second, third, yes, no, right, left, here, there. And we got a fairly good rate for 9 class classification. And for some of the pair, we were close to 100%. Over, if my memory is correct, close to 1,000 tries. Here you can see average tries and a single tries of the best independent source.
And this is the classification of all the pairs. I have to say, when I arrived to the lab in 2001, or when I met Pat in Paris in 2000, and the brain classification, and I remember he showed me a couple of the papers of the lab. I was excited about the adventure, but not fully convinced it was possible to classify brain waves. But after that paper, I was convinced. So then we moved into a more theoretical work. How can we go beyond classification? There is a limit of what we can actually say about the classification rate itself. So when we interact with people or with objects, with anything in the external world, for example, language has some structure, grammatical rules, syntactic rules. Colin talked about semantics. How can we, obviously the brain manage both in reception and in production, at least for speech. How can we see if we can find in the EEG? And for that, we use previous work of Pat on isomorphism and the theory of measurements and partial orders to set up a theory on how to find or to show isomorphism between the world of the stimulus and what we see in the EEG. We don't have access direct to the brain, but we see the EEG. Can we find some isomorphism between some of the stimulus, for example, language, and what we see on the EEG, and how to provide evidence? So I'm going to skip. Colin was talking about it, so we come up with partial orders and with the trees. So here it's a big confusion matrix on the same experiments that Colin talked about, where on a little different twist, we arrived to the result here, where we were looking for it. We find out this grouping of directions very consistently. And it was robust from visual stimulus because the sentence either were presented visually, but for some other subjects, they were presented auditorily. And this, the separation between cities and countries wasn't robust. It was working well in some subjects and not in others, but the directions were consistent with the remark we had before, and we thought a lot about that. What is it? Just the length of the balls. As best as we could test with the data we had, we tried with some combination and measuring the length. It looks there is an effect beyond the length of the ball. But the remark was right. I mean, there is those direction balls are particular in length and in number of syllables. But the effect was pretty robust. And we don't have that on the cities and the countries, or not so much. And we leave at that. We need more data. But at the end, I will show some more data. Just one thing, we did on Germany and Russia. So here's some trees. We compare differently than Colin. Work from 1955 on perception. So this is speech. So you present to subjects phonetics, and you put noise and distortions, and you see at which threshold the probability they confuse. A phoneme experiment. We found a lot of similarities. In the intersection, it's harder to see. How long to write? 5 years, 6 years?
No, yes.
So we were thinking what to do next, and well, you know Pat, most of you a lot longer than I do, and we didn't go one small step. So the funny thing is, about a couple of years ago, I was excited about, and I proposed to Pat to do an experiment where we record the brainwaves of a subject listening to an extract of the American Constitution, that most Americans at least know the first paragraph. And Pat was skeptical that it would work. And then he proposed something far beyond. At least my experiment was controlled. I could know which time the words were presented. And we jumped to something totally uncontrolled, where we record the brain activity of couples in therapy. And Michel and Margot, that I don't see. And so we record everything, the sound, the video, and the EEG. It has been an engineering challenge these last 2 years to make that work. I don't go into details, but it was challenging, and it's not, the challenge is not finished. Now we have about 50 hours of recording with 6 couples, and we're even starting to do some Vietnamese. I don't know how we're going to transcribe it. So, just before we can even start to analyze this data, we had a lot to do. The first thing, we need the transcription, because it's not controlled. So we need to know the words that have been said by the 3 speakers. So you have the therapist, and the couple. And we need to know the onset of the word at rather great accuracy to do any work on the EEG. So we had to start developing the tools. And we wrote a program to do it manually. But it turns out it takes 100 hours to transcribe 1 hour of experiment, what ends up being costly. So now we are turned into writing speech recognition software to try to make it a little easier. And this is still going on. Then the therapists themselves code the emotion, watching the video and listening to the video. The number of emotions change quite a bit. So we started with 19, and it proved to be a challenge. And now we're back down to 4. The therapist can code for several things, the level of intensity of the emotion, the confidence they have themselves on the coding, the direction of the emotion, is the subject expressing an emotion to himself, like sadness, or towards the other, like anger. And Pat wants to do a lot of work on insight. And logistically, this takes about 30 hours to code 1 hour of work. And this, there is no way to do it automatically. So quickly, some results. We are very preliminary. We started analyzing the speech and the EEG a few months ago, the EEG a few weeks ago. So on the speech, we actually able to classify emotion quite well, better than this curve. This is just an example, just on frequency arguments. And you can see here, this is the onset of the word you, or all the U's you have in several sessions. And you can see, for example, for the second format, we have a significant rate, less than 50 milliseconds after the onset of the word. So we have some hope for the speech. And then we hope to use the speech as a crutch to have some handle on how to analyze the EEG. So just to finish, so that's the first analysis I did of the EEG. So the EEG is a big problem here because of the size of the data. It's 2 times 128 channels. But we have one finding that's quite interesting, even if it's preliminary, and it links with what we've heard earlier about mirroring. We found that it's actually easier to classify, for example, in this case, the EEG of the male, or the emotions in the EEG of the males, when we are looking at the emotion expressed by the female subject, more than his own emotions. And this is the case, so this is the EEG of the male subject, but the triggers here are the emotion coded as they were expressed by the woman subject. It goes fast, I'm sorry. So you see the classification going, at the end it would be easier. Other thing you can see, this set of data is incredibly noisy because the experiment is totally uncontrolled. The subjects, they can move, they talk, they frown, they don't fight, so far. But treating the work of just cleaning this data is an open problem. We probably will have a couple of papers just on techniques on how to clean this data. So you see the classification is going to last another 10 seconds. So most of the noise you see are from the muscle activity of the face, the scalp, and the jaw. So, and it's not just, you have two sources. When the subject is talking, obviously the jaw is moving. But for example, like Ryckman showed, when people express emotion, they use the muscle of the face. They frown, they tense their jaw, they blink, and all that contaminates the data. We're not going to treat it as pure noise. We may analyze it. Actually, it's interesting to analyze. But we are going to work with, I started, to how to separate, how to know that the classification I just showed you is something coming from the brain, or is it coming from the muscle, or is it coming from something else? And it probably will take us a few years to get there. Thank you very much.
So a lot of it, hear the truth about it. Analysis and the proper treatment of quantity presented and invited to. It was a real eye-opener for me to hear all the presentations at that meeting. So Montagu's work, of course, has been very influential since then, but it had some features that Pat thought were undesirable, and one of them was that he really felt that the semantic analysis Montagu gave fit the syntax of natural languages very awkwardly. And that was further reflected in the fact that it seemed to require the use of individual variables in sentences where they don't actually occur. And so Pat felt needs a full Zermelo-like hierarchy of sets for the model structure of ordinary sentences of English. So those do seem to be really complications of a kind you might prefer to avoid in giving a semantics for natural language. Pat's papers argued that instead there was we should be pursuing a sort of algebraic semantics, which would have obvious advantages in efficiency and computing meanings, and would avoid artificially escalating the semantic types of expressions. He found, however, though, he frankly confessed that it was, as he presented it, at odds with established thinking about the syntax of natural languages. So he ended up assigning tree structures
like the top one here, to sentences of the form, say, all freshmen date some juniors, where there is no noun phrase comprising all freshmen or some juniors, as syntacticians would generally argue there should be, based on considerations like the fact that if a sequence such as all freshmen can replace another sequence, like some juniors, at any occurrence without disturbing the grammaticality of the sentence in which the substitution was made, then these two expressions are of the same syntactic type, and we ought to recognize that they constitute a phrase in the sentences for the grammatical description of these things. But Pat argued that, in fact, there was a conflict between trying to give an algebraic semantics and recognizing that sort of phrase structure, and felt, I think, for very good reasons, that there were many advantages of trying to give such a semantics. So in particular, he aimed at presenting the semantics to interpret English in an extended relation algebra. Basically an algebra of sets, unary and binary relations over a domain that constitute a Boolean algebra and are closed under certain other operations, like the inverse and composition of relations and a certain kind of image operation, combining relations with sets. And he argued that such an algebra doesn't actually provide adequate denotations for interpreting all the quantified noun phrases in language. In fact, they really don't, they're not even adequate denotations for all the, what you might call syllogistic noun phrases, the ones whose determinants are things like every, some, no. So I think his argument to that effect is actually a very important thing for semanticists generally to appreciate. There have been many arguments over the course of history of trying to understand quantification in various natural languages as to what phrases like all freshmen or some juniors might denote, if anything. Pat's paper contains the gem of an interesting fact that interesting facts that allow one to prove that they cannot denote sets or individuals. You can actually construct a rigorous proof of this, starting just from the truth conditions that the sentences must have, and then making the assumption that we want to interpret the meanings of the sentences compositionally, so that whatever denotation all A's or some A's may have, they would contribute in the same way to the semantic composition of the truth conditions of the sentences. And from there, actually, quite a simple combinatorial argument allows you to prove that these conditions require a sufficiently large number of denotations to be available for the phrases that there aren't enough sets and individuals around in any finite domain to provide those denotations. In infinite domains, you need more than the simple cardinality argument, because you can play coding tricks that would actually encode the denotations in the available sets, and so you'd need additional properties beyond these things like isomorphism, invariance, or conservativity. But I find this result really a remarkably interesting one, because it really depends only on two very simple quantifiers, the universal and existential one, and two simple assumptions. One is that the meanings are to be interpreted compositionally, and the other is that in principle, these predicates that are expressed by nouns or verbs can denote any subset of the domain over which the language is being interpreted. So that's an interestingly general result, and I hope it gives you some feel for why, in the sort of extended relation algebra that Pat was employing, it's impossible to provide denotations for these noun phrases. So how should we respond? Should we jettison the syntactic result, or should we perhaps look for a slightly further extended relation algebra in which such interpretation might be possible? Well, I think it's interesting to explore the latter idea. So along with in-ary relations of the first order, we might allow ourselves to consider second order in-ary relations. In this particular case, they all have their relations over the same, over first order relations of the same arity. That's not necessary. Of course, you could go to higher orders, but there's no need to, I'll suggest. In fact, for the first order relations, we really just need arity 0, 1, 2, and 3 to get an awful lot of natural language interpretation. And for the second order relations, we just need unary and binary relations over unary first order relations. So there isn't actually a large explosion here. What is useful, though, is to supplement the combinatorial operations that we had before with a couple of additional ones. So one is simply the preimage of an individual in the domain, in the codomain of a relation, application of the relation, as it were, of its inverse, to give us the set of first arguments that are related to a given second argument. And the second is a more complex operation, but an interesting one, which takes a unary second order relation over unary first order relations, a quantifier in point of fact, a set of sets of members of the domain. That's what it takes as its first argument. As its second argument, it takes an in-ary first order relation. And what it does when it combines them is to produce an n-1-ary first order relation, as follows. It simply says that relation holds of a given n-1 individuals, just in case the quantifier is true of the set of nth individuals which are related to those n-1. So that's again another just an operation on these this limited set of operations. So if you take the full power sets of the arities that I described, they are Boolean algebra. They're closed under the operations that we're interested in. Of course, you might not want the full power set. You could take subsets, which were again Boolean operations. Boolean algebras, and we're closed under these relations. So let's call these doubly extended relational algebras. They provide all we need, really, not just for interpreting determiners of the syllogistic sort, all, some, no, but also non-syllogistic determiners, like most, as binary relations between sets. So all is essentially the inclusion relation. The first argument is included in the second. Some is the non-disjointness. No, the disjointness relation between these sets. Most is a slightly more complicated relation that compares the cardinality of the intersection with the relative difference of the sets. Nouns, like freshmen, juniors, are interpreted, as you might expect, as simply sets of entities. What about verbs of various kinds? Well, intransitive verbs, like stood, would be interpreted as unary relations. Transitive verbs, like, say, date, as binary relations. And ditransitive verbs, like let's say gave, as ternary relations. So we have adequate denotations for the various lexical items. How about the semantic rules? Well, here's where those new combinatorial rules that I described enter the picture. So a noun phrase, a generalized quantifier, if you like, a second-order concept, as Frege called it, a set of subsets of the domain, simply takes the binary relation between subsets that the determiner meant, inverts it because we usually think of its first argument as being the one that the noun fills, and then uses the noun's denotation as its second argument, fixes that, giving us the set of sets that are related to the noun denotation. And then all of these operations, like the one that combines a subject with a predicate verb phrase, or the one that combines a transitive verb with its object noun phrase to yield a verb phrase, similarly for ditransitive verbs with a first and second object, all of those use that other operation I described, which takes a full quantifier, a noun phrase interpretation, and an in-array relation, and produces an n-1 array relation in this uniform way that I described. Always simply quantifies the way the last argument plays of that relation. So when you combine two noun phrases with a ditransitive verb, you get a unary relation. One noun phrase with a transitive verb, you get a unary relation. And no noun phrases at all with an intransitive verb. And you have a unary relation. When you then combine that verb phrase, a unary relation, with a noun phrase as the subject, as the sentence, you get sentence's interpretation, you get a zero-array relation. It either holds, is true, or doesn't hold. It's not true, of no arguments at all. So that's the basic idea, and what you get then for these sort of familiar syntactic trees that for which there's good syntactic evidence, semantic interpretation trees whose pieces are put together algebraically in the fashion that these rules describe. So I think you can see there's a fairly simple uniform structure to composing those interpretations. Summing up, since John Perry is kicking me in the shins, if you extend these relational algebras slightly further, you can actually have an algebraic semantics of natural languages, which is a good thing. It preserves Frege's insight that quantifiers like everything, but also including not just the syllogistic noun phrases, if you will, like all freshmen, but others such as most juniors. These are all second-order concepts. Unary second-order relations on unary relations on the domain. And you can also, at the same time, formally capture Aristotle's implicit insight that all these determiners, all, some, no, and even most, are relations between sets. They're binary second-order relations between unary relations on the domain. Because so you can capture that and get the right truth conditions for sentences where you couldn't interpret most in the other schema, in the other way, because you cannot define the requisite relation of cardinalities within the relational algebra, the first-order relational algebra. We're no longer trying to define the meaning of most this way. We're simply using the algebra to compose the meanings of things. So I'd like to suggest that, in fact, you can combine Pat's vision with Montague's vision of how the semantic interpretation could go. These postulated semantic values are efficient to compute. They respect the linguistically motivated syntactic structure. They neither escalate semantic types nor necessitate artificially inserting variables, as you saw, and they also interpret these sentences with these non-syllogistic determinants. So, to quote some of Pat's words, in algebraic semantics, with the properties that he desired, As that, this snugly fits the syntax of natural languages as subtly as could be desired. So thank you very much.
Well, that's really a beautiful talk. I mean, I think he has the right combination of what I was trying to do and didn't complete, and didn't have the insight that Stanley had to finish it, because it seems to me it's a very nice analog in some sense of second-order arithmetic and the many things you can do. And what's important about second-order arithmetic, you don't really need third-order arithmetic. And that was what I was objecting to, was the computational problem. You got to be able to compute very fast to do natural language. So I think this is very, very nice indeed, Stan.
Well, thank you. I'm glad you're pleased.
Yeah,
I'm pleased you're.
Very impressed with what you've added to finish it. I know you were always a little unsatisfied. In fact, we had this discussion years ago.
We did.
And we agreed about it, that it needed something more. You've certainly done a great job.
Stanley, you want to take your own question?
Oh, okay. Is there time for questions? Sure. Okay, so I think Jaakko has his hand up first.
How do you deal with quantifier dependence relations or quantifier dependence of each other?
This is a very simple fragment, and within this, we're not attempting to deal with quantifier dependence. That would be another topic, which we could talk about, but not here.
Then if the answer varies for you that to deal with them, you have to give up things like compositionality, and that will affect your own approach. So my suggestion, if I may say so, is go back to Frege and see that he really he didn't do justice to the dependence relations. Even the dependence relations with mathematicians were handling at the time in the arguments. So Frege's treatment of quantifiers was already defective. So that's
okay, I'll grant you that whatever defects were there are carried forward here. Jens-Erik. Yeah.
Since we are in the barwise lecture hall, it's naturally to ask about the relationship between this and the generalized quantifiers of barwise-Cooper.
So that was exactly the crucial step. So Montague treated the determiners syncatagrammatically, as Pat did, without interpreting them. And Barwise and Cooper actually were the ones who showed how you could systematically interpret determiners as first-order relations between sets, second-order relations between sets. And so that is really one of the crucial insights here, absolutely. Yes, I think.
Freeman Ross and Nancy Smith and I took a somewhat different approach on this problem working with Pat at the time. The surface structure syntax, we were dealing with programs as parsed by context-free grammar. We would transform it to a deep structure using a program that would find the noun phrases and so on, and the existential and universal quantifiers, and actually came up with the canonical set theoretical notation on the other end of it. So it was a fairly simple model structure. Of course, the problem is that we had to deal with some fairly kludgy transformation rules written in the code to do this, and there was certainly a lot of ambiguity about how exactly the quantifier should be set up. So it had many problems, but kind of corresponds really to the way a lot of programming languages handle these kind of problems. But I wondered if you have any.
I mean, I guess I share Pat's feeling that that it's desirable to interpret the natural language expressions directly to the maximum extent that it's feasible.
I want to make a comment. Well, I want to support Stanley in that. I mean, Jaakko's comments very much in order. On the other hand, it's very important in thinking about the ordinary use of language not to try to cover everything and why it works so wonderfully efficiently. I mean, in many other areas of science, it's like first-order logic about something more complicated.
So you need both kinds of theories, but you need computationally very efficient things.
I hear the hook grabbing me by the neck, so I'll be happy to talk to anybody.
So, Michael has a question. You want to ask your question?
Oh, no, I just wanted to quickly ask about most, because, I mean, that's vague, right? I mean, could you just fix some arbitrary cardinality relation? Or?
Yes, so when, in any given context, it presumably has some definite relation. But it's a little like, you know, the mathematician's concept
In a
of much
context,
greater.
it has a definite meaning in a context?
In many contexts, it does. And it's very much like, in many ways, the mathematician's concept of this number being much bigger than that, which is rigorous enough for a lot of mathematics and can be used in interpreting things like that.
I proved some theorems that there's no interpretation of most satisfying certain conditions.
I'd like to see them.
So, moving along, I just do want to say on
What's to be said about most?
on a somewhat personal note, Stanley came here, I believe, 30 years ago next year, I guess. This was made possible by a typically bold move by Pat, who founded CSLI as a part of IMSSS when the university had taken a position that it didn't want any new research institutes. So screw them.
Right attitude.
So we were able to hire Stanley, John Barwise, John Etchemendy all in one swoop with a grant from the Systems Development Foundation. Barwise went back to Indiana after a few years. Etchemendy drifted off somewhere, kind of lost track of him. But Stanley has stayed the course and provided intellectual leadership and leadership of CSLI at very crucial times. And, so I think it was a great event in the history of language and linguistics at Stanford when Stanley came. Of course, it seemed greater at the time because we didn't know Pat was going to be around for another 30, 40 years, keeping charge of things, but anyway.
We still don't know how long.
Yeah, who knows, right, so, but, and this is one of many talks I've heard from Stanley that have just seemed to make whole areas of research that were opaque to me, if not exactly transparent, considerably less opaque.
An astonishing array of activities, influence that Pat has had across the humanities and sciences over the last couple of days. I want to remind you about his constant daily influence on legions of earnest students around the planet, kids, young people, who are working on the courses in mathematics and in language arts, in writing skills, that he launched many number of years ago and continues to use. There are tens of thousands of students, even at, well, not today on Sunday, but as we sit most of the week, typing away, practicing, using the computer to improve their skills in these areas. There is a team working here, several people in this room, with Pat on expanding the language arts sort of part of that coursework. And I want to talk to you today about one class of assessing in the attempt to improve the accuracy, the utility of. This is part of this education prize here at Stanford of their academic as they get feedback. In a writing course, you want people to be able to write, and you want to be able to give responses to their particular individual attempts in a detailed way. That is a challenging test, at least as challenging as doing mathematics. The mechanism we're using is to present the students with a little context, ask them a question, all in text form, and have them construct a response, construct an answer for us, written as a complete sentence. And if they fail, we diagnose the errors to the extent we can and ask them to make another attempt. So they get 2 tries with each sentence. Let me give you just an example before I pose the problem we're trying to solve. A student in the 5th grade is faced with the following question. Abigail didn't want to go hiking with her parents because she felt too tired and wanted to rest instead. Why didn't Abigail want to go hiking? This is not rocket science. We're not asking the kid to reflect deeply. We're trying to put something in their head so that they have a reason to write a sentence for us. This is just a quick, rather dim view of the screen that the student sees. The point here is that we give them the puzzle,
And then we give them a very short list of words they get to use, broken up by parts of speech. There are 15 distinct words on this list. They have to construct a response using those words, and our job is to evaluate everything they can do with that inventory of words and give them effective feedback. Approve their answer if it's correct, and advise them about how to repair it if it's slightly incorrect. Well, let me show you some good examples that the students might write in response to this question using those 15 words. She was tired, too tired to go hiking. She didn't want to go hike because she was too tired. There's a variety of ways in which you can use the structure of language to have main clauses, embedded clauses, modifiers, verb phrase ellipsis. All of these are perfectly fine answers to that question. They are not exactly paraphrases. We're going to use the term paraphrase today to describe this kind of variation. Each of these is an effective response to the same question in a given context. And so the task for us is to find out how to evaluate this set of answers and contrast them with a bunch of other answers that I didn't put up here, which would be wrong, false answers to that question. The problem is there's lots of ways kids can write this sentence. These are still the same 15 words. Here's a few more variants where what I did was vary the didn't, want to go hiking in each of the main clause and the embedded clause. So I just folded these two sources of variation in the verb phrase ellipsis across and taken the trouble to write those down. Well, that's not all the answers they could have given, because notice here I used she. I could have put Abigail in place of all of that. So string-wise, I've got twice the number of sentences. This is now starting to get a bit tedious for our authors who were attempting to write all possible answers down for each of these short questions, one after the other. That's not scalable. This isn't the whole list. Here's another list. Imagine I take the because clause and put it at the front instead of at the end. Perfectly fine answer to this question. Because she was tired, she didn't want to go hiking. Because Abigail was tired. So here, these are the same except she is on the left and Abigail's on the right. Well, that's not the whole list. Because I have two occurrences. Here's another set where I've just made sure that Abigail shows up at least once, and in some cases twice in both of the sentences. So only one pronoun rather than two. There are more variants. You're getting tired of this like I was.
Linguistic combinatorics.
Linguistic combinatorics. Nasty problem. It's the nature of language that there is this free variation, relatively free, often independent sources of variation. And if you're going to try and enumerate all possible answers, rather than doing it programmatically, doing it algorithmically, it's going to be a tedious job. Not the right way to build a course. The scale of the problem we're dealing with here, we've had 4 million sentences coming in from students in these kinds of exercises over the last year and a half. We're doing pretty well here with these kids. They were teaching them something. Their first attempt is about correct. Where it's incorrect, we have stored correct and incorrect answers for the most frequent ones. We don't want to waste computer power if we don't have to. So as we accumulate correct and incorrect answers, we put them into our list. But there is still a pretty good residue. About 1/3 of the sentences coming in, or sentences, attempts, they're not all sentences, fall outside of what we have seen before. There is a steady, novel, creative element in these young students. They find ways to say things differently than we would have expected before. Okay, so how are we going to evaluate that problem? We have our cached lists. We have syntactic machinery that can diagnose syntactic errors. I'm not going to talk about that part. That's been the main thrust of our work over the past year and a half, to get that syntactic set of variants. So if a student says, she didn't want to go hiking, they leave out the to, the infinitival to, that's an easy thing for us to diagnose, given the current machinery we have. That answer being ungrammatical but analyzable, detectable, that's the piece we've worked on well. The grammatical part we can do quite well. I can tell that it's a well-formed sentence of English. What I cannot tell with this machinery is whether it's correct or not, whether it's a good answer. The strategy we're using is to address the class of errors where the answer survives our grammatical analysis. It's well-formed, to see whether it's actually correct. And the focus of the next couple of things I want to tell you is how we're going about that attempt at detecting the semantics. Let me show you a couple of ways in which that variation of these correct answers can happen. kids are pretty happy about these modifiers we throw in, and we will find a student who wants to fill up the box of 4 or 5 lines of text we allow them with the word very. So they'll say, she's very, 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 very good. They just hold down that key until the box fills up. That's an okay sentence. It's not wrong. It's not very cooperative. That repetition of modifiers is sometimes useful and sometimes redundant, sometimes irritating. We don't want that to get in the way of their understanding of the course. There's also a course freedom, relative freedom of order for some constituents in this phrase. So his friends will throw a party tomorrow or throw a party for him tomorrow. The for phrase and the tomorrow can be in either order. That's true of most temporal and beneficiary modifiers and verb phrases. That ordering of modifiers or even of some arguments is something the grammar can attend to, but I want to find out, I want to be able to tell in which cases that order variation is indifferent or not very significant to the paraphrasing. And the problem of grammatical but incorrect answers, I can't just let everything go through. If the student says they're going to the zoo this weekend, to the circus, well, that's a kind of way we talk, but that's not what I want the student to write. They got to make up their mind. Was it to the zoo or to the circus? One answer's right, one answer's wrong. If they say, where does Josh go when he has the flu? Well, the student doesn't see the word goes in the word list because we didn't give them that word. So they make do with, well, Josh has at the hospital. That's not the right answer to that question. It is an English sentence. In the right context, you could say that. Has John ever seen a doctor? Well, he has at the hospital. It's English. It's just not the answer we want to this question. And likewise, what happened to Rebecca after movie? Well, she got home late is what we want them to write. She got her home late is a different sentence. Same use of vocabulary, just not the right answer to the question. We're doing this, it's not yet in the system, but we're developing this mechanism of comparing the semantic representations. We're parsing these sentences for their syntax to tell about grammaticality. We're also computing a semantic representation, which we are beginning to exploit rather effectively. So the main piece of work here is we are handwriting these rules of congruence. And here we're building on work that was begun some number of years ago by Michael Botner and Pat. Like always, one is building on something Pat and colleagues have done before. There's no reason to start from scratch. And the goal here is to define these rules of congruence so that we can apply them to the student's semantic representation, compare that to answers that the teachers or previous students have written, which we have recorded, and use that as the mechanism to discover whether the paraphrase is a near equivalent of something that we have seen before. The kind of semantic representation we're producing is yet another notational variant of familiar representations. This is minimal recursion semantics, and it's essentially a set of elementary predications, relations with arguments. We label these argument positions instead of using order encoding because that makes it easier for us to write rules that manipulate those. So here is friends will throw me in a party tomorrow. Not very surprisingly, there's a throw relation which has a friend in a party and Ian as the 3 arguments. There's a possession relation for his friends, and there's a located at for the temporal location of the tomorrow, the location of the party. The friends will throw a party tomorrow for Ian is almost the same, but not exactly the same. This for phrase, this benefactive, we take out as a separate 2-place relation. You wouldn't have to. One could define these as being exactly semantic equivalent, but that's a slippery slope. At some point, the modifiers begin to add their own semantic content. So these are 2 variants. What we'd like to do is define congruence rules which can effectively and productively alter or establish relations between this kind of representation and this representation. 2 near equivalent but not exactly equivalent sentences, let's say. So the rule that we're writing is something that's got another notation of its own. I won't trouble you much with that, but there is an input, that is the semantics that I've been handed, and an output, the semantics I want to transform it into. So we're transforming the semantics of what the student wrote to something else, which we hope is more normalized and therefore matchable to something that the teacher has written or that we have in the course. And in this case, I'm saying, give me a set of predications that are these 3-place arguments, like throw, make, give, and find a for phrase, which is there as well, and relate that to a 3-place relation where you've dropped the for. So you've taken 2 2-place relations and turned it into a 3-place relation. That's not hard to do. It's an independent, a step that's independent of many other changes. Let me quickly show you 2 more. The modifier relation with these very varies. Well, I want to see if I can drop that modifier and still end up with something equivalent. Of course, I can't do that with every modifier. So the rule as I've written it here, which says take anything which has the shape of a modifier, that's this entity where the labels, the hooks of the two predications are the same, and there's a correct relation between the noun and the adjective, or the adjective and the adverb. And in the case where that condition is met, just drop the relation. Throw that piece out of the semantics and see what you can come up with. And the third one, there are more curious ones here where there are co-occurrence relations. You can say in English, they made breakfast, they cooked breakfast. Make and cook are roughly equivalent. You can't do that with everything. They made mistakes, they cooked mistakes. That would have something more to do with irresponsible financial accountants, let's say, than cooking the books. But in general, this substitution is highly constrained. We have the mechanisms in this same rule system to be able to do very specific, even word-level collocation constraints. So we can establish those at varying levels of granularity, from all three-place verbs to very specific verbs with specific arguments. So in conclusion, let me just walk you through one example here of how we discover an alternation between his friends will make Ian a very good breakfast tomorrow, and one variant, his friends will cook a good breakfast tomorrow for Ian. Slightly different, not much different, but there are hundreds of variants I can do with this. As I hope I explained to you in that earlier example, it looks local and cozy and simple, but there's an awful lot of tedium in doing it mechanically. So here I'm going to transform this guy into this guy. Well, I do that even just using the three rules that you saw. I can take make plus this third argument and use the converse of that one rule I showed you that relates the three-place one to two-place relations. I take make and this argument 3 and say, that fits my conditions. I will substitute instead make as a two-place relation plus this four-phrase establishing the relation of that third argument. That's one step. I can, did I jump over that? Yeah, I went too fast. In this case, there was that very good breakfast. Very is something we are always happy to get rid of when we're trying to establish relations. So here we just made it disappear. It vanishes from the scene. And then finally, there is this rare condition of make and breakfast, which happen to co-occur. And we know that's a nice collocation we can replace. So I can turn make here into cook. And then the extra bonus we get from the syntax is that, in fact, this relation of these two modifiers, tomorrow and for Ian, that's in free variation. That has no effect on the semantics, and so our semantic generator can produce the variants with the very same input. Last slide. This data-driven approach is driven by looking at those 4 million sentences somehow. We're still finding our navigational skills in going through that data, looking for places where the students have written something which does establish a paraphrase, an equivalence that we hadn't seen before. And we are manually adding these very general, generic congruence rules to establish relations of those, and then seeing what falls through after we've applied that set of rules, what remains, what more work has to happen. This is a relatively slow process, but a quite interesting one. We have found so far about 10 or 15 of these congruence rules. Michael Butner had done a lot of that work with Pat several years ago. There's still more to do. This is a kind of long-term strategy. And our current mechanism in terms of engineering, as Pat and Stanley have been talking about, some efficiency issues in language processing as you try to do it carefully, we're still experimenting with this offline. So you saw that long list of variants for a particular example. We're generating those long lists and storing. The machines are good at storing and indexing and looking up. So we're not yet doing this on the fly. We're expecting to do this by taking for each of the 1,000 exercises, writing several hundred example variants, run through these paraphrase rules, and then use good lookup mechanisms to find those and match them with the student. In principle, of course, we can run this mechanism on the fly, and we're going to need to do that as we expand our ambitions from sentence paraphrase to paragraph level paraphrase, which is the step we're just now starting to take. As of about 10 days ago, students in Memphis, Tennessee, some of those 29,000 students, are now writing little paragraphs for us, 4 and 5 sentence paragraphs. We don't get to have much of an idea about how to evaluate them. We're just gathering the data. It's a kind of controlled experiment on a massive scale. And over the summer, we're going to look at strategies for extending this notion of a paraphrase at the sentence level to see what we can find across sentences at the paragraph step. That's all I have to say.
Interrupted that's a contradiction. My train of thought about that. What I just want to stress that, what I want to say is that in the psychological and philosophical analysis of language, this enormously central role of paraphrase is often not paid enough attention to. And that is really a critical thing, to have in any analysis of language capability an understanding of paraphrase. And so what is wonderful is to get down to cases here with what Dan's now doing with it, to get a much more detailed feeling. And what is amusing about it, this is my final remark, we're running this elementary language arts course for like 3rd grade students, 5th grade students, right alongside the mathematics course. Of course, from a computational standpoint, evaluating the mathematical exercises is utterly trivial. What is really hard is evaluating the writing of 3rd graders. Already at the level of 3rd grade writing, where the vocabulary is restricted, we face, as Hardin would agree, I'll force him to agree with this, computational explosion. And so it turns out to be the real task is to understand 3rd grade writing. The final point is, in this country, for a variety of reasons that I'm not trying to go into, but as a fact of life, teachers have signed off on evaluating what they used to do in the past, of marking each sentence that students write. A few good teachers still do it, but you can see why. If you have 30 students and they're each writing 10 sentences a day, that's a lot of homework. It's really a difficult task. It's exactly the right task for smart computers, but those computers must be smart. And Dan is showing it. We're making progress on making them ever smarter. Paul, on your own.
Yeah. Okay. Yes.
Yeah. Well, I think that your experimental approach is exemplary, right? And this rewriting rules is pragmatic, okay? But it's a little bit ad hoc, and it doesn't scale very well. And it would be nice to have something more principled. And I think that the rewriting approach for the paragraphs is going to lead you into something of a quagmire.
Might be right. I disagree about the scalability. We are using the same machinery here that we have used for machine translation systems, most recently between Norwegian and English. And we scaled up to about 60 to 70% of the translation of real-world texts using, admittedly, hundreds of such equivalence rules. Of course, across languages, you have to do a lot more substitution. There's a lot more work to do. But the amount of human labor required is in the right shape. That is, you can, with a modest amount of labor, capture the vast majority of what you see, and then there's a very long tail. But in this business, we benefit from doing 90% of the work. We achieve a great amount of educational benefit with a modest amount of labor, even though in the limit, you're right that it's an extremely long, difficult problem. But I think you're right that it's going to become more challenging once we move to the paragraph level.
But you wandered off into semantics. The translation problem between English and Norwegian is largely a syntactic problem.
No, it is largely a semantic problem.
No, well, okay.
We'll take that offline.
Okay, but you can't tell whether something in Norwegian, a Norwegian sentence says the same thing as an English sentence. That you can't do.
I'm defining congruence rules that declare what equivalences exist. That's the point. But it's hard work. Yeah. One more question, Michael. No, sorry. Yes.
This is your attention is on paraphrasing or hard or soft equivalences here. One of the things that a person has to become sensitive to as he learns to write is the distinctions that can be generated by placing parts of, altering the order of words. For example, take the word only and consider the differences in meaning you get from placing it in different parts of a sentence. I pointed this out to one of my classes in logic years ago, and the next day I came into the room to find written on the blackboard, problem for Professor Luce. Take the sentence. She told me that she loved me. And
Put the word only in every possible position.
The word only is one of those words that we very carefully control against when we're giving them candidate words to supply. We have enormous control over the way in which we shape the difficulty of the problem for ourselves.
Yes.
And so that one we will defer probably to some later state of the course. It's a nice point. Yeah.
Okay, Jean-Jacques Rousseau was born this year exactly 3 centuries ago. Here he is. And we also celebrate the 250th anniversary of his book Émile ou de l'éducation of 1762. Although Rousseau was an almost exact contemporary of David Hume, the Émile was not really an Enlightenment treatise, but an early Romantic one. Not rationality, but nature guides us, should guide us in creating the Enlightenment virtues of equality, freedom, and goodness. With the Émile, Rousseau wanted to revolutionize educational practice. It is nature, not human drill, by which the child should be educated. And the first requirement to make this work is for teachers to carefully observe their children. So here are a few citations. Hence, begin by better studying your pupils, because surely you don't know them at all. Observe, and this is necessary for this natural education of the child, and it's a hard education. Observe nature. Follow the route that it traces for you. Nature exercises children continually. It hardens their temperament by all kinds of difficulties. It teaches them early the meaning of pain and sorrow, and goes on. Accustom them, therefore, to the hardships they will have to face. Train them to endure extremes of temperature, climate, and condition, hunger, thirst, and weariness. Well, all children he fathered himself were immediately dropped in children's homes to be completely deserted by Jean-Jacques, but that's another thing. Although Rousseau had a few observations on children in the Émile, it was not too much, it was limited. Many pedagogues nevertheless took his advice and started observing their children. In fact, Rousseau's theories became especially influential in German pedagogical circles. Johann-Heinrich Campe, an enlightened theologian and pedagogue in Hamburg, organized a society of practical pedagogues that who would jointly publish over the years 1785 to 93 a general revision of the educational practice in 16 volumes. And in his preface, Campe pleaded for well-off philanthropists to make available 1,000 thaler for a competition in diary writing. Such a diary on the bodily and mental changes of the child from birth on would indescribably enrich our knowledge of the developing child. There's no evidence that this competition materialized, but a few attempts in diary writing followed this plea. And the first one was Tiedemann. He was a philosopher, and he had kept a diary from 1781 to 84 and published it in 87. It contains well-counted 15 observations on son Friedrich's early speech development over the first 13 months of his life. So, for instance, at 7 months, the child was going to imitate sounds such as ma. And at 8 months, he would point to X when asked, where is X? That's very early. Okay, fine. At 21 months, another example, the first sentences appeared, consisting of an infinitive verb and a nominal, without inflections, without articles. Only 1 year later, the mathematician Moritz von Winterfeld published another diary, very much inspired by Rousseau, and it announced, very interestingly, to relate the gradual formation of the quite peculiar language, the very simple children's grammar. It's the first time that that term is used in the literature. However, it is mostly concerned about the bodily development of daughter Amalia Louise, far less with mental development. It makes some linguistic observations as interesting as the child can say the H, in spite of the fact that that is the easiest letter of the alphabet. That sort of observations. But enlightened Winterfeld certainly was. He inoculated his child with his own hands with a pus of a cow's smallpox. And the child got extremely ill over several weeks, but then survived and also survived the next smallpox epidemic, all thanks to Rousseau. The second small wave of diary writing occurred in the midst of the 19th century. 4 diaries survive, and the most important of them is Bertolt Sigismund's. Sigismund was a doctor and a teacher in Rudolstadt, and he wrote a really very nice monograph on children's development, containing 50 pages on language development, with a richness of observations of language development in the 2nd year of life. Very little on the 1st year. I will not go over those details, but just mention 2 theoretical claims that Sigismund was making and that would be influential. The first one is about the function of first words. That the little speaker uses the first uttered words at once, mainly or maybe exclusively, as expressions of will. The proto-language is nothing but the will made audible. Now, the Bund student, Neumann, would 40 years later make the same remark about first words, and that became simply canonical in the literature. The other theoretical remark or claim concerned the child's early phonology. The notion of least effort. Easy speech sounds appear before hard speech sounds. B, D before, say, L, sh, or. Now, that issue of a least effort principle became very important in evolutionary explanations of language development. All in all, however, in the mid-19th century, the diary making had lost its intellectual appeal. These people were not related to universities anywhere. That changed drastically 30 years later in the years 86, 87. Then what had been really marginal, scattered business was suddenly drawn into an explosive scientific development. The French man of letters, Hippolyte Taine, provided the fuse, and Charles Darwin set fire to it. In 76, Taine had published a report on the diary he had maintained on his infant daughter's language development. A report making ample reference to evolution theory. So here's one of his remarks. Speaking generally, the child presents in a passing state the mental characteristics that are found in a fixed state in primitive civilizations, very much as the human embryo presents in a passing state the physical characteristics that are found in a fixed state in the classes of inferior animals, Haeckel's law, that was. Now the next year, the new journal Mind published an English translation of that French text. This triggered Darwin to publish in the same year, 77, and in the same journal, a 10-page biographical sketch, as he called it, of his son William's early development as an infant. The sketch was based on copious notes Darwin had made between 1839, when William was born, and 1841. Clearly, after reading Taine's paper, Darwin did not want to repeat the Wallace affair. He had been the first to keep a diary over 30 years before Tanner, and the world should know. Celebrity Darwin's paper appeared the same year, also in French, German, and Russian. Not failing to promote the diary business on a grand scale. From now on, keeping diaries on child development was real science, and a tsunami of diary keeping emerged, which reverberates till the present day. Darwin's sketch includes some observations on the Williams language skills developing, but hardly more than the 15 observations that Tiedemann had published almost a century before. Darwin stressed in particular the invention of new words by Williams, such as mum, to express the wish for food. Also, he noticed the instinctive use of intonation patterns, voice modulation, to express modes such as interrogation and exclamation. Here he concluded, repeating what he had expressed in The Descent of Man, that before man used articulate language, he uttered notes in a musical scale. The singing origins of language, that is, and also this kept echoing in the literature till the present day. The importance of Darwin's paper was not so much in its content, but in one swoop, it made the study of child development a respectable branch of human biology. Diaries now appeared at an accelerated rate and in various languages. I just wrote a book on the history of psycholinguistics, and it also tells the story of this diary explosion. Here are some of the 19th century diaries which you will find discussed in that book. There's a whole list in a short period of time. It is from these early diaries that the first language statistics were derived. Doran in 1907 was the first to publish an overall statistics on the development of vocabulary size in children, based on more than 100 children. In the 20th century, this diary business went on full force. Here's a list of 20th century diaries. Here, Clara and William Stern, 1907 diary study, set the new standards for the decades to come. Clara and William Stern reported in much detail on the language development of their three kids, Hilde, Günther, and Eva. Vocabulary development is one aspect of it, but a major part of the book is dedicated to syntactic and semantic development. In the following decades, a rich statistics development was gathered on syntactic complexity. Not only utterance length, but also varieties of syntactic types, such as coordination and subordination, and so on. When famous but Jewish William Stern was in 1933 dismissed from his Hamburg professorship, Clara and William went to Duke University, where William died in 1938. Clara went to New York, where she died in 1945. Their former student, Gordon Alport, took care that the diaries, the largest ever created, were deposited in Widener Library. However, nobody showed any interest in them, and their daughter Eva then moved them to Hebrew University. With Eva's help, we transcribed the full diaries in our Max Planck Institute and made them digitally available to the world. Then really the largest corpus of German language acquisition data. The intellectual break with the rich German tradition was complete after the war. Roger Brown doesn't even mention the Stern's work at all in his famous book, a first language of 1973. I will return to that in a second. But first I should commemorate another occasion really very dear to me. 4 decades ago, in 1972, a few months after his 80th birthday, 50th birthday, 50th birthday, Pat Suppes lectured in a Nuffic summer course, which my former supervisor, John van der Geer, had organized in The Hague. Duncan also taught in an earlier course there. I was on the organizing committee, and Pat lectured on formal grammars and automata. I had just returned from the Institute for Advanced Study in Princeton. I will be eternally grateful to Duncan, who had invited me there. During that year, I wrote my 3-volume book on formal grammars. And one thing I did there was discuss the work, is writing on probabilistic grammars. So I was all tuned to Pat's course, and one thing he did indeed was discussing his work on probabilistic grammars. And that is the issue I want to address to finish my talk. So in my book, I had included a chapter on probabilistic grammars, and then further chapters on their applications in linguistics and psycholinguistics. In the dominant Chomskyan linguistic community of the time, that was simply not done. This is what Chomsky had to say about that. It must be recognized that the notion probability of a sentence is an entirely useless one under any known interpretation of this term. On empirical grounds, the probability of my producing some given sentence of English, say this sentence or the sentence birds fly or Tuesday follows Monday or whatever, is indistinguishable from the probability of my producing a given sentence of Japanese. It was Pat who not only pertinently and repeatedly argued against that curious position, but who also set the example. In the early 1970s, he was the first to do serious work on probabilistic grammars for children's speech.
Chomsky's politics is even worse.
That's my next talk. It was the only empirical work Pat's on probabilistic grammars available when I wrote my book. Pat's first applications were to Adams' corpus of utterances collected by Roger Brown and his co-workers for his book First Language. Brown had unknowingly continued the work of the Sterns, in particular their work in syntactic and semantic development. Pat's classic contribution to the study of language acquisition was two-pronged. He was the first to construct probabilistic grammars for a range of child language corpora. Not only Adams, but also corpora collected by his co-workers, the Nina corpus, so Léveillé, French, and Smith, Nina's corpus, Philippus, French corpus, Eric's corpus, and the small Chinese corpus. Here is Pat's very first probabilistic grammar for Adams' corpus. It was only the beginning. When you read all subsequent papers, you get impressed not only by the sheer amount of detailed work, but by the enormous constraints imposed by the probabilistic paradigm on feasible syntactic rules. Rules that seem obvious to the ordinary linguist just don't work, and other rules that are considered trivial do a lot of work. Pat's second important innovation was to supply these grammars with a compositional model theoretic semantics of the type discussed a moment ago by Stan Peters. That was the other thing not done in the Chomskyan linguistics of the day. Syntax was the thing, formal semantics was etude, it was just not done. Pat supplied each of these syntactic production rules with a semantic function, such as, say, identity, intersection, and so on. And these functions then combined following the syntax of the sentence to compose the meaning of the sentence as a whole. And again, the experience was that these semantic functions put further constraints on what could be a possible grammar for such a corpus. Let me close by saying that Pat was far ahead of his time with these important contributions to psycholinguistics. It took decades before the application of probabilistic grammars to large-scale corpora really took off. It is an established booming field now, both for developmental and adult corpora and in many languages. Its combination with model theoretic semantics, however, is still a rare commodity. Well, thank you, Pat.
It's a pleasure, and I must say I'm really, really glad that Michael started out and reviewed Pat's work so that I didn't have to undertake this really monumental task, and I can focus instead on just some lessons in one minor area that I've learned and want to talk about. You want me to wear this? They want you to wear it. They want me to wear it. Okay. Not me. So, I've had two mentors, Pat and Ruth Marcus, both of whom I admired long before I ever met them, both of whom I have come over the years that I've known them to love, and both of whom my entire philosophical career I've been absolutely terrified of. And in both cases, for the same reason, which is, as we know about Pat, the intellectual power, and also in both cases the intellectual focus. So you mustn't think that, say, if you stay over with either of them, that you might have a casual conversation about the buckwheat pancakes over breakfast. That's not on the pappy. Now, with Ruth at least, I once had some relief. When I was still a graduate student at Chicago Circle, she invited me and a couple of the young Circle faculty to a breakfast with Elizabeth Anscombe. And I wondered why we were invited, and I asked Ruth, and she said that she needed us for moral and intellectual support because she was terrified of Elizabeth. Now, I've never been invited to such an occasion with Pat, and I doubt that any of the rest of you have either. So there's been no relief from these being terrified. But I want to talk today along these lines about intellectual power I don't have, but about the kind of intellectual rigor. I want to talk about two lessons I've learned from Pat. And the first is that rigor matters, but the second is don't bring to a subject more rigor than it can bear. Now, my topic today is a place where I think rigor is badly needed, and I'm in trouble for trying to bring it there. Okay? And that's the movement that insists that randomized controlled trials are the gold standard in evidence for predicting medical and social policy effectiveness. So a lot of the ideas I have here, very simple ideas, are based on Pat's work on probabilistic causality. But I am in trouble for trying to bring some rigor to the discussion. And here are two people I'm in trouble with. One is Ian Chalmers, who is at the, he's one of the founders of the evidence-based policy group in Oxford, which is evidence-based medicine group in Oxford, which is one of the core places that really pushed off the evidence-based medicine movement. He's an influential and avid spokesman for the group, and about 3 years ago, there was a conference at LSE sponsored by the philosophy department, the philosophy center, and the Center for biology and society there. It was run by a sociologist of the biomedical sciences, and she published a volume of papers afterwards. And Ian Chalmers wrote to her. He wasn't in it, but he read the volume, and he wrote to her, and he said, "This is a marvelous volume, but I really, really must protest that you've got this paper by Cartwright in it." And, you know, Cartwright thinks that she can talk about these issues by writing down some equations. So I'm in trouble with Chalmers for thinking that equations matter. You'll see the equation I wrote down. It's not all that complicated. It's a simple linear equation with 4 variables in it. Right? Now the other is Michael Rowlands. Michael Rowlands is the current head of Britain's National Institute for Clinical Excellence. NICE is the body that recommends what's best practice for British medical practice, including psychological therapies. And I was at a, even though Michael Rowlands himself has been less strict, argued about not being so strict, about randomized controlled trials being the gold standard for evaluating medical and psychological interventions. Still, I was at invited to a conference by talking therapists. You can imagine talking therapists are a little worried about the idea that you need randomized controlled trials to attest that therapy works. So I was invited to this conference, and I gave the a 10-minute version of what I'm going to talk to you for about 15 minutes about today. And Michael Rowlands didn't, and it was in favor of just a little more rigor, and Michael Rowlands didn't reply to me. He spoke first, I spoke second, a couple of other people. There were 1,000, maybe 700 to 1,002, say 702 people in the room. 700 talking therapists, right? And Michael Rowlands, who's a chemist, and me. So that's who was in the room. And though Rowlands didn't reply to anything specifically I said, the very first question, somebody sitting in the second row asked some question that was slightly critical of randomized controlled trials, and Rowlands didn't really address his question. But about halfway through, he just was getting angrier and angrier, and he started shaking his finger at this man, and he said, "And you know that in 900 years, philosophers have never contributed a single thing to science." So I took it that, being the only philosopher in the room, it was me that Michael Rowlands was mad at. So here's why they're mad at me. Because of this obvious question, what makes the effect of the outcome of a successful randomized controlled trial, what makes the outcome, for instance, putting it very briefly, T has a positive effect size for the outcome in an ideal randomized controlled trial. I call that here in the trial, or there in the trial. What makes that claim evidence that the treatment will play a positive causal role for that same outcome? So that's the obvious question that I think one wants to answer. And I've spent about 5 years fiddling around with the kind of complicated on and off, complicated things to say about it. And I kind of honed it down to there's just very, very simple thing I want to say in reply. So the question is, what connects E with H? And this is where I was interested in bringing a little rigor to the issue. And, well, it's actually mistaken to say a little rigor because I really wanted to bring a lot of rigor, but not very complex. So, essentially, what I lay out are some simple syllogisms, but apparently Ian Chalmers doesn't like syllogisms. So what connects E with H? Okay. And what I think connects E with H is, I want an argument that starts with E and ends with H. And I propose really a concatenation of two very simple arguments. The first is what I call the RCT argument, and this is fairly standard argument in the literature that looks seriously at what you can immediately conclude from a successful randomized control. The argument uses the premise the effect size of T for O is positive to conclude that T principles governing O in the study. Already sloughing over issues of statistical inference here, and also how we know whether the trial is ideal. We never know that a trial is ideal, and I'm not going to really go through the details of how to define an ideal trial. You'll see some requirements that we rely on for the RCT argument. They're fairly standard requirements. But when I said sloughing over issues of statistical inference, effect size, I'm going to describe to you, is defined in terms of averages. And what it's really defined in terms of are the true averages, which of course have to be inferred from the finite frequencies one sees in the experiment. So there's already a previous argument that gets you from what you see, the actual numbers you see in the experiment, some kind of a statistical inference that gets you to an estimate of the true averages. But so I've already missed, that argument I'm not even going to discuss. So we start with the RCT argument that takes it that we actually have learned what an effect size is in a study, and then derives from that the treatment plays a positive causal role under the premises, under the principles governing the outcome in the study. And then couple that with another simple argument that uses the conclusion of the first, right, to argue that, well, if T plays a positive causal role under the principles governing O in the study, it will play a positive causal role here. That's what we need, right? If you want to get from E to H, right, you need an argument that will take you all the way. And there are two simple arguments you can concatenate to get there. And the second one is particularly interesting because it's not just an argument that will get you there, but if the premises in this argument fail, it's just an accident that the randomized control results are relevant to your case. So it's not that gets you, in a sense, the premises they're not just sufficient for the bottom line, they're in some sense necessary. So here is what, in a randomized control trial, you start with a study population. We're not going to discuss how the study population is chosen. That's already often a problem. But we start with a study population and randomly assign subjects in the study to either the treatment or the control group. This is the very simplest outline. And then you look to see, you introduce the treatment, there's random assignment, there's quadruple blinding. The whole point of all of this is to ensure that all the other causally relevant factors for the principles that operate there are evenly distributed in the treatment group and in the control group. And you look to see what the average value for the outcome is in the treatment group and what the average value for the outcome is in the control group. And the effect size, one definition of the effect size is it's the difference between the average and the two groups. So we do the experiment, we do it as well as we can, and we come out with a positive effect size. Okay, so what? What can you conclude from that? Well, if you suppose, for simplicity, that the causal principles are linear, you don't have to do this, you can get much the same, make the same philosophical points if they're, let's just assume for simplicity that they are linear, so that the outcome, CP stands for causal principle, the outcome is that C equal there. Sorry, folks. It's at the bottom of the page. I don't know how to get it up higher. Let's see if... it's still at the bottom of the page, isn't it? Well, look, all this says, what we have here is that the outcome depends on, in a unit in the study, depends on, for that unit, plus some contribution due to the treatment, plus some other stuff. so it's some simple linear expression of what kinds of things are causing the outcome. The C equals is a way of signifying that we not only have an equality between the right-hand sides and the left-hand sides, but the right-hand side factors are the causes of the left-hand side factor. So this is the causal principle that governs the production of the outcome in the study. So let's assume that it's a simple linear form like that for simplicity, and then you just do some simple calculations. These are done regularly when people explain what you can learn from an RCT. You see these are often done by Holland and Rubin or by some of the economists who work in the area. So the effect size is just the difference in the average, and just run through the simple algebra. And then one of the assumptions we want to make about the ideal RCT, part of the definition of an ideal RCT, is that the random assignment of units to either the treatment, which is here getting the treatment gives you value x, or the control x prime, will ensure that the treatment is probabilistically independent of the background level, alpha, for the unit, as well as beta, and the other causal factors, w. So that's what the point of random assignment is. And if you assume that, trivially that the effect size is just, really depends on, I mean, of course, if there's no, the treatment and control have different values here, so the effect size just depends on the average of beta. So if that means if the effect, if this is non-zero, then this term has really got to be there in the equation. You can't possibly get a non-zero value here unless t really does figure in the equation, the causal principle, governing the production of the outcome in the study population. So that's what you can conclude from finding a positive effect size. If you find a positive effect size, okay, then that shows that t really appears, that this treatment that's under test really does appear positively in the causal principle that governs the production of the effect. Okay. The causal principle that governs the production of the effect in the study population. Of course, any place that that same causal principle holds, you found out something about that causal principle, but it's a particular causal principle you found out about. What you know is the causal principle that holds there in the study population has t in it. Okay, so here's what the RCT argument looks like. If you were to start to write it out, the study satisfies, I shouldn't have used alpha, beta, and gamma because alpha and beta were parameters in that equation, but the study satisfies a bunch of conditions, including, in particular, this one that you've got t probabilistically independent of alpha, beta, and w. So t satisfies a number of conditions, the study satisfies a number of conditions, the effect size is positive in the study, therefore t plays a positive causal role in the study. And all that means, I use the shorthand, t plays a positive causal role in the principle governing the study. That's just shorthand for t's there in the causal principle, and moreover in the study, the average value of beta was greater than 0. So that's the RCT argument. So we have a good argument, RCT. It's a valid argument that has among its premises the evidence claim we were interested in, and then it has as its conclusion this one I keep going on about, that t plays a positive causal role under the principles governing the production of O there in the study. Now, to establish the evidential relevance of the study results to the prediction we're interested in, to establish E's evidential relevance to the prediction we're interested in, which is that T will play a positive causal role here, if we implement it, we need another argument, which is the effectiveness argument, in which this conclusion figures essentially as a premise, and our our prediction that T is going to work for us appears as a conclusion. I seem to have left out the mention that this argument here, I thought I had a slide on this, it might turn up later. This argument here that I said is mirrors things that you see by Holland and Rubin, and you also see by economists. It relies on Pat's probabilistic theory of causality. I don't write it out that way, but if Pat's probabilistic theory of causality is not a correct account of causality, it doesn't make a correct connection between probabilities and causes, then this argument's no good too. This argument fails. So in order to make the kind of connection between causality and effect size that you see in a randomized control trial, you better be supposing that Pat's got it right about the probabilistic theory of causality. So now here we are back at my claim that what I want to do is to now talk a bit about this effectiveness argument, which itself is very simple. Okay? The first thing to do is to look at the simple linear form. It's got this beta in it, and the formulation can be misleading. And I see that it sometimes is in the hands of some of my fellow philosophers who treat beta as a constant. But beta is not a constant. Remember the philosophical slogan that causes are Inus conditions, insufficient but necessary parts of unnecessary but sufficient conditions for contributions to outcomes. If you don't know the expression, don't worry about it, because what's important about it at this stage is simply that almost anything we pick out as a cause or anything that we pick out as a treatment is not sufficient on its own to produce the effect in question. That generally the things we designate as the treatments operate as part of a team in cooperation with a whole set of helping factors. This is true no matter how fully and how carefully you try to write out the protocol for the treatment, that you just can't get everything in. So the things we name as treatments, the things we call causes, are parts of a larger team that it takes, and it takes all the members of the team to have the right values in order to get the outcome. And that's these are represented in one swell FOOP by the beta there. Okay, maybe here's where. So if the oopsie. So if the effect size is greater than 0 in a population, in a study, that shows that the average of beta is greater than 0 in that population. Remember back here, that's what we actually had in the conclusion there. It's the average value of beta. If the effect size is positive, the average value of beta is greater than 0. And beta represents in one fell swoop all the values of all the arrangements of the helping factors. So if you get a positive effect size, that shows that the average of beta is greater than 0. And I guess here's where I mentioned Pat. If you recall the probabilistic theory of causality, it looks for probabilistic dependence between T and O in different subpopulations that are characterized in our notation by different values of beta. So Pat's got the idea of prima facie causality when T and O are probabilistically dependent on each other, but it's only real causation if that probabilistic dependence continues to hold once you've partitioned on all the other causal factors, and those combinations of the other causal factors are represented here by beta. Well, they're represented by beta and W, but W is dropped out of the equation. Okay. So what we learn is that T plays a positive causal role here, that principles governing O, and that there's a good distribution of helping factors here. So right, if the average value of beta is 0, or the average value of beta is negative, you're going to get a 0 effect size or a negative effect size. So all I mean by a good distribution is that if you're interested in getting a positive effect size, what you need to have is a distribution of the betas that will be just the right ones to allow the treatment to do its job. Okay. Now, one of the things that's important to note is that when we're talking about the distribution of these helping factors, they're the helping factors that are necessary here for the treatment to work. And one of the things, particularly since I've been working on social policies, there are lots and lots of social policies that are effective in different places, but that the causal principles are just slightly different in the different places, so it takes different helping factors in the different locations in order for the policy to produce a good effect. Okay. So here's the effectiveness argument. T appears in the causal principles governing O in the study. Oh, I know what's happened. Sorry, I've been waiting for another slide. This doesn't have the Harris-Cooper homework, does it? No. Okay. I sent a later version of these that has an example. You probably all got the idea of helping factors, but one of the they're often graphed. Epidemiologists graph them in what they call causal pies. So you have a graph of the causal pie, and it will have the salient factor, the treatment you're interested in, as one slice in the pie, but then they'll picture all the other factors that are necessary to be in place along with the salient cause as the other slices in the pie. And so I've got a case that's easy from the work of Harris-Cooper on homework. And one of the things we know about homework is it doesn't always work. And it's not just a matter of there are reasons why it doesn't work. In order for homework to be effective and to produce the kind of results, the level of results we expect, you need to have a supportive family environment, teacher feedback, etc. There are various different supporting factors that homework can be combined with to make it effective, but it's not going to be effective on its own. So you need these helping factors, and when you do a randomized controlled trial, what you're seeing in the effect size in the study population is the average value over the distribution of those background helping factors. And some of the helping factors, of course, and often in many cases, can be negative. I mean, it can be that you've got some factors that the treatment combines with and gives you negative outcomes. For instance, if the children are rebellious and resentful, signing homework can actually reduce their scores. So what you're seeing when you see a positive effect size is, again, the average over these helping factors. And if you see a positive effect size, that means you've got a good distribution. The ones that the positive pies outweigh the effects of the negative ones. If you get a negative effect size, it's the other way around. And if you get a 0 effect size, it could be that the treatment isn't effective at all, just it's not there in the equation, or that the negative and positive effects are balancing out. So here's the effectiveness argument that I want to couple with the RCT argument. We've got as a premise that we've learned from the RCT that T appears in the causal principles governing the outcome in the study. Now, this is the simplest possible argument. What makes that relevant to here? So we know it plays a role, causal role in the causal principles there. Why is that possibly relevant to what happens here? Well, if you assume that if it appears in the principles there, it will appear in the principles here, it suddenly becomes relevant. And moreover, you need to know that the support factors necessary for T to contribute here actually obtain here. In fact, what you need to know if you want a positive effect size is that you have a good distribution of them. So it's not just that they obtain in some individuals or other. It has to be that you have a good distribution. That is, there are the contributions from the good ones outweigh those of the bad ones. You don't need, in order to think that it's going to play a positive causal rule here, you don't need to know, you don't want, in fact, usually you don't want the same effect size here as in the study. You'd like a better effect size. Right? You want to have a really good distribution of helping factors. So this is the effectiveness argument. And my claim is that if the premises in this argument fail, then what happened in the study simply isn't relevant to what will happen here. So it's not just that this is a way to get from the study to predictions about here. It's that it's not just sufficient to get here. It's if any of these premises fail, then it's just an accident if you've got the same results. So here's why these folks are mad at me. We start out at the bottom with the effect size is positive and an ideal RCT, and the RCT argument leverages that up into the claim that T plays a positive causal role there in the study, and then the effectiveness argument leverages that up till T will play a causal role here. And it's the leveraging by these arguments that they don't seem to like to hear about. So I think another way to look at it is by one of these argument pyramids, where you look from the bottom up. We've got our RCTs in the bottom right-hand corner, and what do they support? They support that T appears in the causal principle there in the study, and that helps support that T appears in the causal principle for O here, but it only does that if we can have the additional premise that if T appears, actually it should be if T appears there implies it appears here. Sorry, I've got it back to front. Okay, so this is only part of the support. T appears in the causal principle there, and if you want to get to T appears in the causal principle here, you need that if it appears there, it appears here. And this isn't enough to give you that it plays a positive causal role here, because you need that we've got a good distribution of helping of some factors, and we've got to know those are the helping factors here. So this is my sort of picture of the argument pyramid that it takes to make RCT results relevant to predicting that T will play a positive causal role here. Now, they all recognize that you can't just go from an RCT there to here. But I never see any discussion of just what is it that will take you from there to here. You often hear these two situations should be sufficiently similar. The U.S. Department of Education's website, for instance, tells you that if you want a program that will work here in your school, you should find a program that has 2 good RCTs behind it in schools like yours. So schools don't need to be like yours. Right? What they need to be is to have this, if it plays a role in the causal principle in the study schools, it will here, and that you have the helping factors needed under the causal principle that holds for you. So the missing premises, all the way up in this argument, they might hold often, they might hold seldom, they might hold sometimes, but what matters for prediction about what happens here is that they have to be true for here. And evidence-based policy, you have to have warrant for that. And otherwise, the RCT result is no support at all. So this is what you get, a rather top-heavy pyramid if you don't have support for the other premises. Okay. So in conclusion, very brief conclusion, I thank Pat for his lifelong demanding rigor where it's needed, and I shall, trying as always to follow Pat's good model while running very, very far behind, keep up this demand with Chalmers and Rollins and others, and because I think they're building their predictions on shaky foundations. Thank you.
Pat has already indicated he wishes to reply.
Yes. Well, a wonderful discussion, Nancy, and thing I would add here is something I should have done in my probabilistic causality. So we can take this comment as the fact that what I wrote was incomplete. And there is a further argument here, and you should have asked me to come along to argue with Rawlings and Chalmers.
That would show that.
Yeah, that one scared them. I didn't.
That further argument, though, is fairly straightforward. That is one, in my view, what Nancy's saying, and talked about positive effect. Now, statisticians, of course, aren't going to be quite satisfied with that, and for good reason. And so what is really important, and I want to make a slightly extended comment here because it goes from education, what is really the second step is to quantify. And in fact, on the U.S. Department of Education, that they're what the gold standard is for education, that the effect size is 0.8. Now, you might say, what does that mean? Well, it has a very clear meaning. The 0.8 is a measurement of standard deviations for the mean. So we normalize and have one standard deviation in the two distributions, the control and the experimental. And in education, it's considered extremely, where the argument goes. See, it isn't enough quite, and this is, I'll blame myself rather than Nancy. If you have, say, an effect size of 0.005, let's say, and it always is positive, still, it may not be worth the effort to have that kind of effect size. If you go to physics, for example, or even more, where there's a great slogan on this, at operations research in the engineering school, they have a great slogan. Some of you may have heard it. 6 sigmas. Harvey, what does 6 sigmas mean?
I learned it from the annual report of one of the stocks I hold.
What does it mean?
And all I know is that GE has been a disaster. So
No, 6 sigmas. I like that. Harvey, we like to go back and forth. Love Harvey. 6 sigmas, of course, means 6 standard deviations.
Yes.
Now, almost never in education has anybody, or in medicine, had anything close to 6 standard deviations.
Right.
So that is really big time.
Yep.
No. So it depends on the discipline of what one expects. And of course, in physics, physicists don't, they hate p-values. In physics, that's the way to talk, is in terms of standard deviations. They don't need any more talk. A physicist runs an experiment and says, yeah, this differs from the classic prediction by 3 sigmas. Very good result. And of course, what a statistician can also do with the full apparatus is you want to attach a p-value. And there are criticisms of p-value. I won't go into criticisms of p-value here. To the effect size. So, for example, Nancy's exactly right on this reading of the Department of Education. You are really not permitted to publish results when you have simply a p-value. See, the standard example in statistics is something like chi-square. Then if you have even the smallest difference, you can produce a difference in the chi-square from the null hypothesis by a sufficiently large sample. So it's got like an epsilon delta argument. I won't expand on it, but you can get at least a small difference, no matter how good and how close the two are, unless they're just absolutely the same, the two distributions, which is very uncommon. So it is important, and that's why in the Department of Education manual, they now want you to have a column showing effect size, which the physicists take as automatic, and it's only come to be realized. And in fact, in a lot of psychological publications, Nancy, they don't give effect sizes. So the one thing this is about is, I should have added, for real use, the discussion of effect size. And it's going, as we like to say, which I claimed I did not do in that, it's going from probability through statistics and the analysis of data in a sharp way, to go on from positivity to effect size.
But there's something else to add about that.
I'm sure you want.
Yeah, one of the reasons that
Okay. Okay, need to start. The work that I'm going to talk about here is it's related to what Ray just presented, in the sense that is an effort to construct models to improve EEG analysis that are based on physical principles instead of just using statistical tools that certain powerful methods, but sometimes it's difficult. From the outcomes of the analysis, you have a clear idea, you account for what is going on inside the brain. So this work goes in this direction. So it's about EEG recognition. Marx talked about EEG recognition, and Ray again. The process that I'm going to use is very simple. Instead, so you record EEG. When you record EEG, what you have is a distribution of voltage on the skull. And you want to use this signal, this data, to estimate the distribution of the electric field. And instead of process the raw data, now I'm going to process the electric field. Why? So I want to convince you guys that this is a good deal, and if I'm not able to convince you, then I go to show results of empirical data, which I think it's more convincible. So this work is in collaboration with Marcus, Acacio, and Pat, of course. So first, let me tell a little bit, I know that Marcus used this picture, saying that, so let me tell you a little bit about EEG signals and some issues that I want to address by computer, by estimating the electric field. So here is a picture that was taken in our lab some time ago. So you see Michel preparing Logan for EEG studies. So Logan is wearing electrode net. We see several nodes in this net. Each node corresponds to a sensor, and these sensors record a voltage difference with respect to a reference site. Okay, so in this case, for this system, the reference is located in the vertex, which is on top of the head. So our studies in general. The subject is in front of a computer, not exactly in this room, this is just for the preparation. So have a room which with out isolation in a dark environment. And the subject sits in front of the computer, and he presents several images or some speech sounds, which are called stimulus. And you run several trials. Trials in general last about 1 second, and the stimulus presentation is about 300 milliseconds or 200 milliseconds. And this signal is recorded at sampling rate of 1 kilohertz. You can go beyond that, but usually you don't gain too much by using more data, because this means that you're going to use more data. You know, in this case, here you have 128 sensors. So you can see 128 sensors and 1,000 points per second. So it's a lot of things. So there are several techniques to analyze EEG. So what you're going to talk about is the classification or recognition of signals. And some experimental issues with EEG. First of all, the reference electrode. So sometimes you put the reference in the ear. So in this system, the reference is on top of the head. So there's no silent site to put the reference electrode. So wherever you put it, you're going to have a bias due to the reference. Okay. This in some analysis is not actually a big issue. But if you
want to do a spatial analysis, then that matters. Because imagine, for example, that you choose for the reference site, the site exactly where the neuron is being activated. Then you got the 0 in that site, but not going to see anything there. Another thing is that EEG has a low signal to noise ratio and a poor spatial resolution. Okay, so at least these two problems here you can address with the technique that I'm going to present here. Noise problem is you have always there are some signal processing techniques that you can do to improve the signal. So let's talk about a little bit why the potential sometimes is not the best quantity to take into account when you want to infer about brain function. So first of all, when you record EEG, you don't see from EEG action potential, for example. EEG is not about what's going on inside the cell, but outside the cell. It's about what's going on in the extracellular medium. Okay, so usually you model the cells by electrical dipole, like that, and it is all important that EEG is not sensitive to activation of just one neuron, one cell. So the activation of one neuron, one cell generates a very weak signal. So what you take with EEG is the result of the synchronization of thousands of millions of neurons. So you are picking activity of layers of main cortical neurons that have similar spatial orientation. So if the dipoles are random oriented, then this signal in general will not produce something significant in this call. And most of these layers, we believe that we record are the pyramidal cells, where the cells are oriented in the same directions. And the other thing that's important to mention is volume conduction. So when a cell activates, what happens is that it's going to push out ions of like charge. So these ions, you move away from the cell, and when they move, they push their neighbors, and so on. So this generates a current that ends up in the skull, and these ions you also interact with in the electrodes. So, and then you're going to see a voltage difference between this electrode and the reference. So, but that means that the potential is a coarse quantity. It doesn't give you information about direction from where the current is coming from, where it's going. So, and this is also shows that in some cases you can classify EEG signal with 100% accuracy, but not always. There are many limitations with EEG, but you can circumvent some of them using some physical principle. So I'm going to talk about the electric field. Just to simplify the discussion, Pat doesn't like this in my simplification in general, but I assume here, let's assume that the brain is a perfect sphere, okay? And the head is made of 3 spherical layers: the brain, the skull, and the skull. Okay, this will simplify the discussion. And the brain, every time that the brain activates, it generates electric and magnetic field. But these fields are not coupled, or they are weakly coupled. So the dynamic of the magnetic field does not interfere in the dynamic of the electric field, and vice versa. Okay? And also, most of currents in the brain are ohmic currents. You don't have capacitive effects in general are negligible. So with these things taken into account, the electric field is proportional to the current density, to the density of current per area unit, okay? And this constant here is what you call the electrical conductivity. So you don't have actually to assume that the brain is isotropic. You can, for example, afford that the conductive along the tangential direction, remember that we're talking about a sphere now, is not the same as in the radial direction. This is okay. But when you analyze this equation here, you're going to find that at in the area scope interface, exactly where you measure EG, in the outer scope interface, the radial component of the electric field is 0. So the scope electric field is a tangential field. This is important because it means that I can fully estimate the electric field from the scope distribution. Otherwise, that would not be possible because the electric field is related to the potential. According to the equation, I have to apply the gradient. The gradient of the potential gives the electric field. So each component of the electric field measure the rate of change of the potential in that direction. So to estimate the radial component of the electric field, I need some measure of the potential along the radial direction, and you don't have that. You only know the potential along the scope surface. So this is good. This is an important property. And also that the electric field is directly connected to the current density. You don't have such a relation for the potential. You can establish a relationship between the potential and the dipoles. But this involves a green function, an integral, or the whole sphere, and that means that the potential is really constituted. But if you do the analysis only using the electric field, then there's a problem. Okay, that the component, the radial component of the electric field is 0 on the scalp surface, but it's not 0 inside the scalp. So if you do analysis use only the scalp electric field, you'll not be able to take, for example, currents that are generated by radial dipoles. So what I'm going to do, so let's go to the next slide. So sorry. What we're going to do, our method is a combination of the electric field and the surface Laplacian. And we talked about these two methods before. So why the surface Laplacian? The surface Laplacian of the potential is the divergence of the electric field. What happened, and I can demonstrate that, I didn't put the equations here, but it is something that you can derive theoretically, analytically, is that although the potential acts like a low-pass filter for brain signals, the surface Laplacian acts like a high-pass filter. So it is a very good quantity to pick local activation. And here is a clear example of what I'm saying. So this is a simulation study. We need to have 3 dipoles. One has opposite orientation, it's oriented opposite to the other two. And this is what they have at the brain surface, along the brain surface. If you go to the scalp, what you see is a blue picture of this map because of volume conduction and because of the scalp, which is a very poor conductor. Okay? But if I can put the Laplacian, you see, my signal, what they have is highly correlated to what I see in the brain surface. Because this is true for radial dipoles, for dipoles that are oriented along the radial direction. So then the idea is, let's combine the electric field with the Laplacian, because the electric field, you pick tangential activity, the occurrence that flow remain tangential. The Laplacian, you take account you account for radial dipoles. So now I'm going to show some results of classification, which I'm going to compare what I obtain by classifying the signal using the potential, using the electric field, and using the Laplacian, and the combination that I talk about. Of course, this combination is not, I'm not proposed to sum the Laplacian and the electric field because there are different quantities. It's just that when you classify, each data point is a variable. Okay, so what I do is I concatenate the trials of each one of this quantity, and here, for example, if I try last one second, for this guy is 1 second, for this guy is 2 seconds because I have 2 components, and for this guy is 3 seconds because I have 3 trials concatenated. This experiment is exactly what the experiment that Roy showed before. So let's just talk about the average because I don't have plenty of time. So if you classify, for example, the syllables, so the same syllable, 8 consonants and 4 vowels. If you classify for the initial consonant, in this case, I got this initial consonant. Yeah. So chance level is 12.5%. With the potential, I got 36.9. With the Laplacian, 40. And with the electric field, the combination is 45.7. We always are going to see that we always improve the rate if I use the electric field. And I have results for 4 different experiments. The next one is involved 9 color-shaped images. So chance level is 11%. But when I classify the signal using the potential in average for 7 subjects, I get about 50%, which is far from chance. But if I process using the electric field, the result is 75%. It's much better. And now I have also an experiment involves 72 images of face, human face and non-human face, which includes 6 categories: human face, human body, animal face, animal body. And again, I process the signal, I classify the signal using different methods. So in red, you have the result for the classification of the 72 images, and in blue, for the 6 categories. And you see, I go from 10%, 11% with the potential, to 26% using the electric field. And for the categories, from 51% to 67%. And finally, is two-class experiment in which the subject is present in every other trial, either a stop sign in the computer screen, or he or she hears the speech sound of go, the go word, in English word. And he asks to, after seeing or hearing the sound, to make a mental picture of what he just experienced. Okay? And here I'm classifying the trials correspond to the imagination. Okay? So if I classify the trials for the stop and go for the student, I get 100% for all methods. So there's no room for improvement. But if you classify for the imagination, when you go to that field, you have a very small improvement. But then I can add something else. I can combine the electric field with PCA, because the electric field, I inflate the feature space. Because instead of 1 second trials, now I have 3 second trials. So I can reduce this space. And by reducing the space, I improve the rate, and then I see a good improvement. So from 74% to 85.5%. So the conclusion is that the electric field is very effective to improve the classification rates. The method solves the problem of reference because the electric field is a derivative of the potential. So then it's reference free. I have no problem with reference here. I show that a combination with PCA can provide more improvement. The method is computationally efficient. I didn't talk about how to estimate the electric field from the potential. I use a spline interpolation, and there are many things that I can do to improve this result because of this estimation requires some things that I didn't have. For example, I didn't know the actual location of the electrode. I assumed that the head is a sphere and it's not. So if you get more data, then I think you can do much better than I showed here. So thank you and happy birthday, Pat.
Arranged here at Stanford in 1960. The second one was in Jerusalem in 1964. And I gave a talk, and then after my talk, Pat came and asked whether I wanted to come to Stanford. I said that we had just decided to go to Norway and live there. And he said, I knew that, but still if I wanted to come a part of the time, I did not come. And of course that was what enabled us to stay in Norway because Norwegian incomes are far too small for support of a big family. But in any case, I assume that Pat had consulted his colleagues before he came to talk. We have heard here several stories about how he told somebody you're hired. But I think that I owe also gratitude to the colleagues of his, and many of them are here. David Nivison, to start with the oldest one, sits here and is almost as old as Pat, half a year younger. And then we have Saul Pfefferman, who was also here and must have been in on the decision. And we have Dana Scott. And we have people who are not here now, but who are still alive, or Kreisel is still alive, and he was here.
Yes, he's in Salzburg. He's in Salzburg. Kreisel is living in Salzburg.
Yes, that's right. He lives in Salzburg, and I gave lectures in Salzburg last year. And Kreisel actually came to the lectures, which was very nice. So he's still at least able to listen. I don't know whether, I've not seen anything that he's writing yet. But in any case, I have then enjoyed very much being together with Pat for all these years. And we have been teaching seminars together on all kinds of topics. I think we have taught more than 12 seminars together on topics ranging from parts of philosophy of science, freedom, medieval philosophy, intersubjectivity, and even perspective in the arts. So there's a wide range of topics that all are topics that Pat gets very much engaged by. And I think this is what is so typical of Pat, that he gets engaged by so many topics. And actually, even when he came to Stanford originally in '48, he was immediately made a professor also of statistics and economics.
Not economics. Just statistics.
Yeah, just statistics, but education came early. But one strange thing is that in 1948, Pat got a prize for the best work in the world in psychology that year.
58. Later than 48.
Later than 48, yeah. But but in any case, at the time when he got it, he was not a member of the psychology department. He was, so that prize went to philosophy, and the psychology department, of course, immediately acted by making him a member of the department. But what is so striking about Pat is that he gets so enthusiastic about the things that he's working on. He's very interested, he asks all kinds of questions, there's a lot of curiosity in Pat, and he's always very open. He listens to views, he likes listening to views different from his own, and this openness, of course, means that he gets this very broad field of work. It stimulates people who are with him, but it is combined with a critical power. One of the most common questions you hear from Pat is, what is the evidence? And I think that combination of openness, but at the same time a critical attitude to what we talk about, is a very, very typical characteristic of Pat. And of course, he has now written and worked in so many different fields. And although I've had so much to do with him over the years, I must admit that, of course, I have read only a very, very small part of all that Pat has written. And really a very sad admission is that I have not even read Pat's bibliography. I never had time to read it. But now, fortunately, it's out electronically. And Pat has been very good at organizing his bibliography so that you find it by field. So when I was now going to look at everything he has done in the philosophy of language, I could just concentrate on that part of his bibliography, because I think there are about 500 articles and around 50 books, plus a lot of books that he has edited. Maybe the number is higher now. It's a few weeks since I checked. But in any case, it's very, very impressive with all this activity over such a broad field. Now, when it comes to what I'm going to talk about, his contribution to the philosophy of language, I did give a talk on this topic when you were 70, 20 years ago. Then I did not say Maine. But that was because I had more time. I had 10 more minutes. And also because I think that there has been much more happening during those 20 years. So it's now impossible really to cover the whole thing. But I will distinguish 5 different areas of your work. Actually, you published a book 20 years ago, where you suggest that there are 4 main areas of your work in the philosophy of language, but one more area has been added after that book. The first one was there, psychology of language, especially children's acquisition of language. Second, work of a formal linguistic kind, including work on variable-free semantics, language and robots, and then language and the brain. That was not even mentioned in that book 20 years ago. That's where you have done a good deal of work lately. And we have heard already about that from Colin Krangle and Marcus Perreau-Guimares. And then what I really wanted to concentrate is this 5th area on meaning, because there you have done a lot of interesting work, and that's also very close to my own interests. These other things, I should mention that especially when it comes to the children's language, there you actually have registered a lot. We have just heard about all these diaries of children's linguistic development, and Pat actually carried out detailed studies where you're partly bringing children into experimental situations, but partly also just following what is going on in the children's use of language in very natural situations in their own lives. So there's a very lot of details. You heard earlier too, Pat emphasizes the use of data, and really not just giving loose theories, but checking those theories with data. So this is a very important and interesting field, which I'm not going to talk about. I'm going to talk about the notion of meaning. And here, a very recent article, 2007, there Pat distinguishes three kinds of meaning. One is meaning given by formal definition, and that's relatively unproblematic. It, of course, raises some very interesting logical problems, and there are problems. One of the first talks I ever gave after I finished my studies was on this problem of indefinability. There are certain things that simply cannot be defined in a certain system. These are really logical problems, and Pat has done some of that, but he's not really concentrating so much on that. He also has done a little bit of dictionary meaning, but the third area is what he has been working the most on, and that is meaning as associations. These are the 3 kinds that he distinguishes in that article from 2007. And it's meaning as association that we should take a look at. And that is that we have lots of associations connected with a word. And if you look in a dictionary, then maybe just one or very few features are mentioned. But I agree with Pat that we should really look at meaning much more the way we look at an encyclopedia. There's a lot of information connected with the notion. For example, horse, or perhaps examples, chair. It's not just one or a few features, but there's a lot of them. And I think that is also something that was emphasized by Quine. One way of putting his opposition to the analytic-synthetic distinction was by saying that I don't distinguish dictionaries and encyclopedias. I think that all these associations that are connected to the word are really very much on a par. There's no line to be drawn between some that are analytic and some that are synthetic. And actually Husserl, who is one of my heroes, and of course Pat and I also taught several seminars on him, he is very similar to Pat on that point. And his notion of a noema, which I've compared to Frege's notion of Sinn, is different in one important way from Sinn, because Sinn for Frege is much more like the dictionary definition, but the noema for Husserl is very, very rich. It comprises lots of different factors. There's no end really to the fact that it's inexhaustible. There are lots of factors that we're not even aware of. And these factors are then sediments from past experience. They depend on our interests, the situation we are in. There's some features that turn out to be prominent in some situations and not in others, and many other factors. And I'll mention one example now, and that's what we call one-wholeness. If you look at these three items, then we ask what are the features that we are paying attention to. And the features that we pay attention to are often reflected in our pointing out certain kinds of similarities. And most people would say these are similar because they're suitable for drinking vessels. And this one is different. That's a donut, and it's suitable for eating, maybe. But this kind of property that we then assign to cups and glasses, that are drinking vessels, that's just one property. Of course, there are lots of others, and what properties we focus on depends a good deal on what we're interested in. So if you now look at this and see how that changes, then you'll see that, well, these are really something in common, but what is it that are in common? They have one-wholedness. So therefore, a topologist, for example, would pay a lot of attention to that feature. So that shows how these features we pay attention to, and we could say go into the meaning of that notion, are really very, very much dependent both on background, sedimentation, and application and what is happening. And this is also exactly what Pat is interested in. This example is similar to one you found in Husserl, who was very interested in topology as a source of a lot of these notions that we are interested in. And now Pat introduces, and I have to be quick because he introduces one important notion in his approach to meaning, and that's the notion of congruence. He says that sameness of meaning is like congruence in geometry. So that he really introduces this notion, which has a lot of features over from Felix Klein, the important person in the development of German mathematics, who founded the Erlanger program in 1872 when he was only 23 years old. And that's the notion of invariance and the transformations. We saw how one-wholedness is invariant and the transformations with that donut and cup. And there's a similar ideas like incarnated intentional isomorphism, that is, that there's a congruence in structure between notions. And Pat says that two utterances are belief congruent for a person if and only if one can substitute one for the other in all belief statements of the person's sola veritate. That raises some problems of circularity, because in order to get it to work, you really have to include in those statements lots of tricky non-intentional, non-extensional notions. And Pat does also go into that a little bit, but we have to be very careful. And since we have so little time, I just mention one further feature of Pat's approach, and that is that he thinks also that we have to be charitable. We have to assume that people have coherent beliefs, and that means one's beliefs should be consistent with one another. At least they should not be obviously inconsistent. No person knows all the logical consequences of what they believe in. And here, since Jaakko is here, I would like to mention his very early work in connection with the book Knowledge and Belief in 1964, where he discusses the notion of surface tautology. That is, when we are charitable, we should permit inconsistencies when they are so far away that it really requires a lot of logical insight to see that here we have an inconsistency. And we have a doctoral student, Wes Halliday, I don't know whether he is here now, but he's written his dissertation on fallibilism and the limits of closure. And this notion of closure, of course, is and then connected with this, that we are not really willing to accept all logical consequences of what we believe as conditions for being able to believe in. But we should have certain kinds of limitations, and it's very tricky, as Jaakko first pointed out, to see how we are going to draw the line between those consequences that it's really natural to take into account and those that it's not so natural to take into account. Well, this was extremely quick, and it does not do justice to Pat's very rich work in this field, but I think that's what we have to end with, because now Nancy is going to start. Thank you.
Last question.
Yes, oh yeah.
So about congruence, sameness of meaning, I'd like to bring attention to work of some logicians.
Yes.
So first of all, there was interest in the question of sameness of proofs that Kreisel raised and was pursued by Doc Prawitz, especially in Mark-Mouleuf, and in terms of natural deduction calculi, reducing to the same normal form. So that was an interesting idea. It didn't come out completely the way one would have liked, but certainly a good idea. But as far as language meaning sentences, I want to bring attention to the work of Janis Muscovakis, who has also done work on certain kinds of normal forms in systematically developed calculi, which turn out to represent a considerable portion of natural language using the work of Montague. So.
Well, this was a very valuable supplement, and we want to see how Pat, in many ways, has been connecting his approach to language with things that are really important in analytic logic as well. And it's this emphasis on structure and things like that comes back in both fields.
Thank you. You want to say anything, Pat?
No.
Okay.
Enjoyed that. Yeah.
So, as usual, I failed in my administrative function, but we'll take a short break, and I guess try to come back a couple minutes before the hour, and we won't be too short.
Really,